Thank you, Jonathan. Good morning, everyone. Welcome to the second day of the AI Days. So today, like it was explained before, it's about use cases, innovation, and research. And we have with us a team from Boeing that worked with us for the last couple of years on one of the IPCs that you have heard a lot about. And I want to briefly introduce the content of this project, and then I will pass the floor to the Boeing team. So as you know, IPCs are one of the ways that we use to engage with industry and with stakeholders, and it has proven to be one of the most effective and successful ways to do that. You see on the slide the number of use cases that we have been considering so far in the AI roadmap. A good part of those are IPCs, in fact. So this has proven to be a modality really good to explore, to test new concepts, new technologies, and it's also a learning exercise for both parties. For us, to get familiar with everything that's happening in the AI world, to test our guidelines and to improve it, and for industry as well, like it was explained yesterday very well by Jean-Marc. So coming to the first IPC that we see today, the project was called Beacon. Our colleagues from Boeing will explain everything about it, but I want to offer here the EASA perspective about it. We signed the contract with Boeing back in 2023, so now it's a bit more than 2 years of intense work with the Boeing team, and the idea was to assess possible ways to certify a level 2 machine learning application that could be installed on transport category aircraft, basically CS25, FAR25. For this, we put together a team at EASA where I was the project manager and also dealing with the concept of operations. And then we had experts for AI, specifically human factors, safety assessment, and avionics. This is what we do typically with an IPC. We assess the needs of it, and then we put together a team taking people from the various areas of the agency, experts as necessary, so to ensure that we can support as best as we can the applicant of the IPC. And the objectives of this project were in particular to exercise, to test, and maybe even to challenge the guidance of the concept paper for level 2 in particular, and to assess 2 different applications for auto taxi. The first was at level 2A, and then the second was level 3, but it was more on an explorative phase. The main focus was on the level 2A application. Then in the course of the project, Boeing showed us also another application that was a bit different. It was about, it's called Safe Runway. It was about detection of objects or intruders on the runway before landing to prevent runway incursions. It was also a very interesting application that we were happy to see, and you will see a bit about that during the presentation. And after nearly 2 years of work, we had recently, a couple of months ago, what was an important milestone of the project, which was a live demonstration of the application at a Boeing facility in the US. We stayed there for a week, and it was really a great takeaway for the project. So we can consider so far the objectives of the project achieved, and as the main takeaways, like I said, we have for the first time a live demonstration of such an application, and also we saw that the level 3A has the potential for further exploration that we will be happy to consider in the future if the opportunity comes. So with that, I'm very happy to pass the floor to the Boeing team, for which we need to switch the presentation to another slide. But in the meantime, I can invite the first speaker on stage, Matt. So Matt was the project manager on the Boeing side for this IPC. Matt is an associate technical fellow at Boeing. Deals primarily with autonomous systems. He's engaging with authorities and with regulators to develop the standards and the certification standards for autonomous systems. And Matt, the floor is yours.
Thank you. So good morning, everybody. As Giovanni said, my name is Matt Yan with the Autonomous Systems team in Boeing Global Safety and Regulatory Affairs. And I was the principal investigator for this IPC between Boeing and EASA. So quick overview of what we'll be talking about today. We'll start off by, Giovanni already gave the EASA perspective on the IPC so far. We'll do a quick introduction to the project and what we were talking about. And then I'll hand it over to my other Boeing colleagues here to talk about the automated taxi system, one of the main focus areas of the validation and verification of AI systems. Then I'll hand it over to Dragos. We'll talk a little bit more about the safe runway system and have some technical discussion about that and what we looked at. And then lastly, I'll hand it to Emily, looking at the human factors consideration in our project. And then we'll finish up with a quick wrap up and some kind of next steps and hopefully a Q&A at the end if we have time. So, because it's early in the morning, give you guys something interesting to start off with. This was a video from the live demonstration that Giovanni mentioned a couple months ago at one of our Boeing-owned airports in the U.S. So there are two different systems on display here. There's the automated taxi system and the safe runway system. They're kind of interspersed in between each other, so it'll switch back and forth. But just give you a heads up of what you'll be seeing. There's two different systems involved here. So hopefully the sound works here. Let's try.
Go ground Boeing, name Bravo X-ray on the west ramp, requesting taxi runway 29.
Hey, Bravo X-ray, Glasgow ground, taxi 29 via Alpha Bravo.
29 via Alpha Bravo, a Bravo X-ray. Intruders coming in. Found one in track. They're stopping short of the intersection. And we're cleared.
Ground 1 entering the active.
I got a caution. Continue. Continuing. Runway traffic. Warning. Go around. Go around. Bravo X-rays on the go.
Copy, 202 sir. Got it.
If I can add something to this, we were watching the live demonstration from a control tower of the 60s that was in its original state. So it was quite an experience.
Yeah. So yeah, obviously, as everybody noticed, there's a couple of familiar faces in the video. So I kind of saved that as a bit of a surprise because I thought it'd be funny. But this was a really valuable, as Giovanni mentioned, this was a really valuable opportunity to be able to have EASA, our partners, come out to and view the systems in a live demo. I think both parties got a lot out of it, and it was a really good opportunity for both us and them, I think. And so thank you guys for coming out and doing that. Okay, so before we get into the details of this specific project, talk about this how this project fits within Boeing's overall strategy on regulatory innovation. So my organization, Global Safety and Regulatory Affairs, has a number of ongoing efforts in regulatory innovation where we partner with different regulators around the world in order to find, as we say here, find solutions that address open industry-wide regulatory challenges associated with innovation and emerging technologies. And so we like to find areas of interest for both Boeing and the regulators that are kind of like, as we say, new and emerging, and partner in order to help establish the regulatory environment so that, you know, both us, Boeing, and other industry members can hopefully take advantage of that and introduce new technologies to the benefit of everybody. So, you know, we talk about our strategic objectives or strengthening regulatory relationships, and I think the two that are most applicable to this project are the strengthen regulatory relationships and foster global regulatory alignment. I'll talk a little bit about that coming up. And so I mentioned this is just one of the projects we have going on or that we've completed in the past. The other ones we've done recently are we had another IPC with EASA with a different group of people looking at the ConOps for advanced air mobility vehicles in Europe. We've also done some work in the past with UKCAA and the Australian regulator looking at uncrewed aircraft flight in controlled airspace. And so this is just a few of the ones that we've been working on. Won't be talking in detail about these today. We'll be focusing on the IPC on AI, but just kind of giving you an overview of where this fits in with what Boeing's working on. So talking specifically about our IPC today. So we had a few main objectives when we started this IPC. We were looking to, in collaboration with EASA, establish the regulatory requirements, means of compliance, and V&V strategy for a machine learning-based system. We started with the EASA's AI concept paper, issue 2, is kind of the foundation of all our work. We used the experimental automated taxi system, which was shown in the video. These overview here were written when we first did the contract, and as Giovanni mentioned, we brought in the safe runway system partway through because we thought that would be a really good example to look at a few particular aspects for the concept paper, and Dragos will be talking more about that here in a little bit. So we looked at both the automated taxi system and the safe runway system. We also looked at a level 2A version and a level 3A version of the automated taxi system. And as Giovanni mentioned, we started back in, well, we signed the contract back in 2023. We started work in June of 2023, and we're just about wrapped up kind of in the documentation phase, and we'll talk more about that as we wrap up. So why did we propose this IPC? A few different reasons. Like I mentioned, this really aligns with Boeing's strategy and regulatory innovation, but specifically, we thought the exercise of trying to apply the concept paper to a 2A and a 3A system kind of off the critical path of certification would give us, both us and EASA, a chance to really sit down and explore these things without some of the pressures of being on the critical path. The work as we came into this, we thought would hopefully highlight some areas of potential refinement for the concept paper. Obviously, we've been talking about the concept paper is some initial thoughts, and some really good initial thoughts, but it's initial thoughts, right? And there's always, once you try to apply things, there's things that could be learned and improved in the future. We're hoping that the work here will lay the groundwork for our certification of other AI systems in the future. And, you know, when we started this, we had seen other IPCs and other efforts that EASA had taken with some of our industry partners, Collins with the Formula IPC, there's the DEMLEAP, and then the CODAN reports. And we said, there's all this good work going on, you know, Boeing would like to contribute to this growing body of knowledge. And so this would be our opportunity to do that. And again, we'd like to use the work that we've done here to help leverage and facilitate harmonization between FAA and EASA and other regulatory agencies around the world. So we've been sharing, while the IPC contract is directly between us and Boeing or EASA, we've also been sharing some of what we learned with our friends at the FAA and kind of discussing with them too. So look forward to working more with both FAA, EASA, and other regulators in the future. So different focus areas, I kind of touched on this a little bit. So we started with the application concept paper objectives and means of compliance. We also talked about the validation and verification approach, and then human factors and the use of system theoretic process analysis, or STPA, and how we could use that on a system like this. Additionally, like I said, we also brought in the safe runway system to look at kind of the performance metrics and the quantitative safety analysis concepts from the concept paper. And so Dragos will be focusing on that in his part of the presentation. So getting into the results of the IPC. So as I mentioned, Josh and Emily and Dragos will all be talking about specific parts, but there was a couple of different things that came up that didn't fit nice and neat in those sections. And so I'll be covering those here. So I mentioned that we started by looking at the concept paper objectives. And so we started with a review of those objectives and trying to apply them to the level 2A version of the system. We wanted to see, which objectives would be applicable out of the list to our particular system, explore if the intent of the objectives was clear, and if they were something the applicant could show compliance to, and ensure that the set of applicable objectives were sufficient to ensure that we had a system that was developed in a safe manner. So the themes that came up in the review, the concept paper objectives are intended to be an additional layer on top of the existing regulations, addressing the specific aspects of machine learning that are not covered in those existing regulations. And so 25, 1301, 1309, 1302, 1322, just to give an example, those are all still in place, as Guillaume and Giovanni was mentioning yesterday in the update on the rulemaking task. But, we started this a while before the rulemaking task, and that was a good learning that we wanted to share that came out of that. There's a lot of qualitative requirements in the objectives from the concept paper, and there'll be a lot more work probably on a project by project basis at first to see what is good enough for each applicant in their system when we start talking about those qualitative objectives. And that was a major theme that came up a lot when we were discussing. Continuous safety assessment. I know that's been an interesting topic as well. We've explored that a little bit more in phase 2 part of the project, but that's going to continue to be what exactly does an applicant need to do there, and how are we going to satisfy that requirement is something that came up, and I think will be an area of future research and topic discussion as well. Unsafe skilling. This was a topic that came up yesterday, and it was a topic that came up in our discussions of the objectives as well. What does that look like? What does that mean? What do we need to do? And what does an applicant need to do versus what does the operator need to do? So that was an interesting discussion as well. The list of objectives that are applicable to level 2A versus 2B. We'll get it, actually the next slide will go more into detail on that, but that was something that the line between 2A and 2B is quite interesting. And what happens when you have a system that has aspects that maybe could be considered 2A and 2B, and what do you do with that? And so we thought that, and we did it for this project, that perhaps the list of objectives need to be a little more tailored than even they are in the concept paper to each particular system. And so we'll talk a little bit about that. And the other thing too, this was a question for us and a question for other members of industry that I spoke with kind of at the beginning of the project, the ORG, the organizational objectives in the concept paper. How would an applicant show compliance to those on a project? And it wasn't clear to us, and it wasn't clear to other people we talked to. And in the discussions, it made it quite obvious, that wasn't intended to be at the project level. That was more for a DOA level. And so I thought that was good clarification that we'd want to share that came out of this as well. So this kind of gets us into the discussion I had about the 2A versus 2B and what objectives are applicable. So it also comes in the definition of what is an end user. And so specifically the system, and Josh will talk more about the system, what it does and how it's architected, but a quick overview here. One of the functions of the system, the automated taxi system, is that it receives its taxi clearance via radio, and it parses batch taxi clearance, plans its route, and provides a readback. And so it provides a readback outside of the human. So the human does not have to provide the readback, the system does it by itself. That's potentially taking authority away from the human because it's providing the readback, right? And so that was an interesting question because 2B is a system that kind of takes some of the authority away versus 2A is a little more cooperative. And so does that make it a 2B system or not? And so the other question is, if ATC is interacting directly with the system and not through the pilot, does that make ATC an end user of the system, just like the human flight crew is or not? And so that was a big topic of discussion around this. And so what we kind of came to the conclusion of is that because the automated taxi system in its current way it's designed is designed to fit into the current ecosystem without any changes, as far as the ATC knows, or ground control, they're not necessarily talking with a human versus a system. They do their job the same way as they do today. Nothing changes for them. And so based on that, we thought, and we decided with EASA that they're not an end user. they are a supporting user of the system, and therefore we don't necessarily have to classify them as an end user, and we don't necessarily have to do some of the work that the concept paper required if they were an end user in terms of the objectives. That said, and this is where we get into the discussion about tailoring the objectives. There are objectives in the concept paper that are limited currently to level 2B that talk about voice communications between an end user and the system. Well, if ATC is not an end user system, those objectives wouldn't be applicable, but they maybe should be, right? Because the system is communicating via voice to a person. And so we decided to include those objectives in our discussion because we thought that was the right thing to do for the functionality and safety of the system. And so when I talked earlier about the need to tailor some of the objectives even more so than what the concept paper does with because there's the concept of the level of the DAL level and the AI level, and that's how you determine which objectives are applicable or not. There may need to be, depending on the exact details of your system, there may need to be tailoring on top of that. So that was something that a big topic of discussion when we came out of this. And so this also gets into some of the discussion that I just shared about level 2A versus 2B, and that's taking authority away from the system or the user, sorry. So I won't go too much more into that since I already discussed a lot about it, but I will hit the last couple of bullets here. So we thought some areas of areas of future exploration. We thought that situational awareness and representation would be a good topic for some future research on this. Level 2B requires a shared situational awareness between the system and the end user, but level 2A does not. However, for the end user to effectively monitor and collaborate with the system, they must be provided with the system's situational representation through various types of explainability. So what exactly that is, how that works for 2A versus 2B, and what that would actually look like to the end user, we thought would be a good topic of future exploration. And also the impact of information availability on AI level. And so the question kind of came up, if the system has access to information the human doesn't, in terms of maybe sensing capabilities that the human eye doesn't have, for example, would that affect the AI level classification? Because the classification kind of considers, the situational representation, if it's shared or not, and how that works. And so that was an area of, we thought, of future exploration that would be interesting to either us or the industry as a whole. So that's kind of the overview of the project and some of the results, like I said, that didn't fit neatly into some of the other buckets. So at this point, we'll start talking about the validation and verification of AI systems. And Giovanni, I hand it back to you for the introductions.
Yes, and the next speaker is Josh Neighbor. Josh is an AI technologist at Boeing, where he leads the verification and validation for AI team and service as a machine learning engineer for various autonomous projects. Josh, the floor is yours.
Awesome, thank you. Okay, so I'm going to cover a lot of different areas that we looked at on this project. I'm not going to read through this slide, but I'm going to start with part of this was presented, I think, last year at the AI Days. And as Matt mentioned, we had a section, or we partially worked on the automated taxi system, and then Dragos later will talk more about the safe runway. But to give everyone a bit of an understanding of the auto taxi system before kind of getting into some of the results. This slide essentially summarizes our experimental auto taxi system that Boeing is using for research here. And the goal is for safe automated routine ground taxi while keeping the flight crew fully in control. And so the first system, or the system can receive a taxi clearance over the radio, as Matt mentioned. It then parses the clearance and turns that into a planned taxi route on the airport surface and generates an appropriate readback. And so once cleared, the taxi moves on the aircraft. The aircraft can move from point A to point B autonomously, managing its speed, turns, and stopping along the route. And throughout this, the flight crew monitors the system and can override or disconnect at any time. And so our focus here is on the reliability, predictability, and clear crew interfaces. Okay, so little bit more overview of the auto taxi system. So first, the crew is it's initiated. The system is initiated by the crew, and so the system does nothing until explicitly called for by the crew under the right conditions. And then once activated, the crew can continue to monitor the system throughout the entire route. Okay, so here we have our overview of the system. This is here mostly to show that it's a very complex system that involves a handful of different, what we would call AI-based subsystems. So we have our dialogue manager. So the voice commands come in from ATC, those get processed. We have our planner and decision maker for the system, and then we also have the perception component as well. Most of what I will talk about will focus on the perception component. Okay, so motivation for this project. Matt already mentioned a little bit about this, but to add to that, right, we have aviation is one of the safest forms of transportation, but AI and ML are coming in and promising to transform that a little bit and hopefully add efficiency, cost saving, and reduce human error. But we have to make sure that they are, I think, safer than the current systems out there. And so the purpose of this discussion is to share our progress and the lessons that we learned in the verification and validation of a safety critical AI system, and basically what we're working on, where the gaps are, and what we are continuing to work on to close those gaps. And so basically when we started this project a few years ago, I came from more of the perception and control side of things and knew very little about the regulatory side. So I started with, I think, what many people have already read is the concept paper, and then a lot of the key standards to get an understanding of this area. There's a lot on this slide, so I'm not going to talk to it a ton, but essentially at Boeing, we started this process with understanding what our current model development process was, and then how we saw, I think, the development process laid out by EASA and the current standard V kind of verification process, how we saw them fit together. And so we've kind of overlaid the V with the W to really show that while we have, I think there's new pieces with the ML side of things, everything still runs on software and is really well embedded into the system. And so this is essentially kind of the way we're thinking about it, but we go into this a lot more in the paper we'll be releasing, so I don't want to cover it a ton here. So as we were essentially thinking about the problem and thinking about kind of defining what is an AI system, what is an ML system, what are the differences, we really came down to this idea of approximate functions, and that there's really two types of functions that we've encountered: exact and approximate. So exact functions are those that can be enumerated, or can enumerate all valid inputs and outputs. And traditional certification methods work really well for this. This is kind of our current software. Approximate functions arise when the underlying problem is computationally intractable to solve exactly within practical time. And so those cases, we use estimators, heuristics, or learned models that can't be exhaustively verified. And that's, I think, the focus that we're thinking about here. And so tractability refers to whether a problem can be solved exactly in reasonable, typically polynomial time, but many real-world AI tasks like perception and complex planning are intractable. So traditional processes like DO-178C, as I mentioned, work really well for exact deterministic components, but AI and ML models, by contrast, provide approximate solutions for intractable problems, so we needed different assurance approaches. This, of course, doesn't mean less rigor. just means different evidence packages. So requirements tied to measurable risk, statistical and robust testing over representative and worst case data, uncertainty characterization, and then runtime monitoring with fail safes and clear operational bounds, or how we're kind of addressing this problem. So for us, we really think of this from a risk management approach. And so what's the probability that the function produces an output leading to an undesired or hazardous outcome? So in other words, the risk is the probability you produce some outcome times the cost, which we're saying is given by our environment or our operating design domain. And so correctly categorizing your operating design domain becomes very crucial in understanding your risk. And this really brings things to this risk-centered approach. So we need to first identify the risks, including the known and the plausible unknown failure modes of the system. Second, we want to quantify the likelihood and impact using statistics, simulation, and empirical testing across both our representative and worst case scenarios, as mentioned. And third, we also want to monitor the system with fallbacks and crew procedures to drive this risk down to reasonable levels. So how does that impact our auto taxi system that we're talking about here today? So our approximate function will require risk assessment and risk management through techniques such as design time analysis, empirical validation, and operational monitoring and mitigation. So adequately and accurately addressing this risk is based on our approximate function as well as the sensing and the compute on the system as well. So two other things to consider. So one of the exercises we went through with the EASA was taking our system and defining our AI constituent based on the auto taxi system. And so here is essentially a relatively standard perception stack, similar to the one used in the auto taxi system. So you have your sensor, in our case, LiDAR. You have some form of pre-processing. You have your inference or your model. You do some type of post-processing or tracking, and this leads to your prediction, which can be then fed into some type of decision system or your planner. So we spent some time with the EASA discussing how we want to define this because it does change some of the impacts based on where you draw your bounds, how you're defining your operating design domain, and how you're conducting your analysis. So this is kind of for the simple case, but oftentimes what you'll see in real systems are kind of these multimodal perception stacks. So in practice, right, this type of redundancy can help with robustness or these multiple sensor inputs, but then you typically add complexity to the system. And so thinking about when you have multiple sensors such as LiDAR and camera, where those are getting fused, where your pre-processing is, your different kind of inference models, and then how those lead to different decisions and how you're going to monitor and monitor those systems. And so there's quite a bit more write-up on kind of our thinking through of this process in the paper. So I'm not going to go over a ton of it here, but that's, I think, one of the ways we're starting to bound the system and think about our operating domain. You have to start with defining your constituent. Okay. So I think based on that, right now we're moving into defining our operating design domain. So we've defined our constituent, and now we go into defining the domain. I'm going to skip this slide actually and talk more about the challenges in defining our domain. So I think, as we mentioned, for our system, we have, I think the aviation environment is highly dynamic with rapidly changing conditions, making it challenging to define static boundaries for the operating design domain. And we like to say, or use the word complexity here, but the structure of this complexity can change over time, which is one of the challenges. So safe operating under all specified conditions for a high dimensional operating design domain is an ongoing challenge for us. As well, I think, as you probably all know, right, so the data requirements for the operating design domain also present difficulties for training and testing, especially for rare and extreme conditions. So ensuring that we have high quality, accurate data is essential, but also understanding that noise in that data could lead to errors as well. So understanding that your data set is accurate is also very important. And then I think the challenge here around this for high dimensional systems is completeness, which can basically not be possible through scenario-based testing. And so we really have to focus on this risk-based mitigation approach that we were discussing. So we go more into this in our paper, but we spent some time breaking down and understanding the exact operating domain and the operating design domain for the auto taxi system. And so now that we've defined our operating design domain and the AI constituent, now we need to think about the performance metrics in order to do some analysis on the auto taxi system. And so we've defined our performance metrics and by tying them directly to hazards from the operating design domain, and then we broke them into the different pieces such as our detect, classify, and track stages of the system. And so the important thing here is for detection, we want to measure how early we see an object relative to the stopping and separation margins. And we want to think about our false alarms here, our noise tolerance, and the performance in different weather and different conditions. And then for the classification prediction step, we aren't just looking at accuracy, we actually care about the impact, such as your false negatives, false positives for critical cases, and making sure we can identify things such as our aircraft, vehicles, and people. Okay, so the bottom line here is that we need to choose thresholds and safety margins and validate them across representative and worst case scenarios, and then report those results with confidence intervals so that the planner can make informed and risk-based decisions. So we want to talk a little bit about how we think about this with potential scenarios. So if you have basically a loss of perception, you have a static object on the runway. Now we want to start thinking through some failure cases so we can use this to turn this into kind of some performance metrics and understanding of our system. We briefly used STPA here, which is a system approach to process hazards. Emily will be covering this a bit more, so I'm not going to go into a ton of detail on what STPA is here. But essentially, we're starting with a high-level hazard that we're going to focus on here. And so the fact that the airplane could exceed the proximity to an object, so get too close to an object, is the hazard we want to focus on a little bit more. This can be caused by a couple different things, but we're going to focus on for a very simple situation here, essentially like a change in direction. So not the aircraft not seeing or perceiving the object and not being able to change direction in time. So this leads us to what are our unsafe control actions that could possibly lead to these scenarios. And so one would be that the autonomous executive does not provide a change in direction when a static obstacle is in the field's path. And so now we have our unsafe control actions, so we start to write requirements around this. And so we now say that the autonomous executive shall be able to detect, classify, and track an object of some size and at some distance. And so now we can start to do some tests to understand what that size and what that distance would need to be. And we go into quite a bit more detail on the paper on trying to quantify what the smallest object we think we need to be able to track is safely, and then using that to understand, your LiDAR system. So I think the density of the feedback from the LiDAR, as well as your compute, how long does it take to actually come up with indication to tell the aircraft to stop. And so you can start to put some numbers to this. If you say you want to guarantee that you stop with some safety margin of 3 meters from your object, at some speed how long it's going to take you to stop, depending on certain conditions on the tarmac, and then some processing time or your D delay. So the time it takes to process the input to your system to know to send the command to stop. And so going through all these example scenarios, you can start to back out specific numbers and values for your sensors, as well as requirements for your system. And so we kind of talked through what are the smallest obstacles that could cause danger to the system, what kind of danger would that be, and we go into more of that in the report. But essentially we kind of took this idea and used this to get a better understanding of our perception failures and kind of classifying them into several reasons. And so here, to understand our perception failures, we've separated them into 3 tiers. We have critical, functional, and supportive. So critical perception here we're defining as this is what's required to avoid accidents. So for example, a detect and avoid of an obstacle or an intrusion. So misses or late detections here would translate into a safety hazard within this critical perception range. So if something's too close. You also have a little bit further out in range, you have your functional perception, which we're defining as kind of supporting your mid-range planning and decision-making. So you have time to actually make those decisions. Essentially, maybe like there's an object coming up, but you have time to pull over to the side, or you don't have to just slam on the brakes. You actually have time to make some type of nuanced decision. And then you also have this supportive perception region as well. And so this gives you additional situational awareness, such as like recognizing other aircrafts or other things out there. And so, we can quantify this, what we're calling these action windows. So how much distance and time we need to react. And this can be based on essentially our system, the speed, the braking distance, and system latency. So this could change depending on the objects or how you're kind of defining your system. But these are things to keep in mind as you're defining the system. Okay, almost through. So here we're talking about safety, uncertainty, and risk. So as we move towards the certifying of AI-enabled systems, I think we need to think about how we define and measure safety. And so I think one of the takeaways from this project is, safety is not the property of any component, but it's an emergent property of the entire system, including its operational environment. And so, we see uncertainty coming from 3 main sources: the sensors, the algorithms, and the handoff between perception, tracking, and decision-making, at least for this perception case. So, for example, what does it mean for a system to hit an object and not detect it? So what properties, size, materials, speeds, or positions could lead to a case like this? And then think we should represent this uncertainty probabilistically. And so our risk management approaches, these need to quantify the probability of a hazardous outcome. And this requires us to decompose the system, analyze the hazard trees, and focus on the parts of the state that can lead to unsafe outcomes. So as we know, for these high dimensional input spaces, they can kind of be a moving target. So as in like the automotive industry, we're always thinking of yesterday's safety problems, but new anomalies and edge cases do consistently emerge. And so our challenge is to anticipate and address these in our system design and our validation. So I think to sum up most of this, we believe that risk-based methods grounded in well-defined operational design domain and robust performance metrics are essential. You also have a piece of human factors and explainability that are critical for ensuring that the pilots, the regulators, and the investigators can understand and act on the AI systems or the outputs. I think a key question for many of these high dimensional input systems is how do we know we really tested the system enough? And right now, I think there's no single answer, but we can use statistical analysis, simulation, and empirical testing to build some of that confidence. But I think there's a lot of work left to be done in this area. And so ultimately, this is a collaborative effort. I think industry regulators and researchers have to continue to work to evolve these standards and share kind of our lessons learned. And so I'm hoping we're doing this through our presentations here and our paper that the hope is should come out in the next couple months. I think that is the end of my presentation.
Thank you. Thank you, Josh. So we hand to the next presenter, who is Dragos Margineantou. Many of you, I'm sure, know him. Dragos is a Boeing Senior Technical Fellow in Artificial Intelligence Chief Technologies, and he is the technical lead of AI research and engineering at Boeing. So, Dragos, the floor is yours.
Thank you so much, Giovanni. Thank you, Guillaume. Before going into the safe runway, first of all, I wanted to acknowledge everybody here. First, EASA, FAA, and everybody here. After finishing my PhD in machine learning, I knew virtually nothing about aviation and its interactions like this, and close interactions like the ones that we have with EASA, with the FAA, with NASA, with the academia, and with industry, that brings us all together. And let's be frank, so this is not only a Boeing cause or an EASA cause, an FAA cause, but this is to bring a better life and safer life for humanity. Aviation was that dream and will continue to be that dream. So as Giovanni mentioned, while we were working on the details of the risk analysis of the auto taxi system, we exposed our other types of work that we did with our experimental airplane. And indeed, because of several safety incidents that were listed in the press, we came at one meeting and we showed what we did on detecting incursions at landing. And we thought that it would be good to go more on our statement of work and talk about the assurance and the path for certification of systems like that. And the video that you saw earlier was a mix. Basically, let's acknowledge the flight is a mix of all phases. We defined phases for pilots and for humans, but it's basically all phases. And if we are to insert these technologies, they should work flawlessly together. And you can say, I land and now I wait and switch between systems. These have to execute flawlessly, and this is the path that we are taking. So the overview of my portion, first I'll talk about the problem of runway incursions. And yes, with the activity now online and social media and so on, virtually every risk incursion is in the press, and you've seen some of them. Then I'll talk about our approach, our goals, our challenges, and also our entire system, which has a large number of AI-based components and but it's a system. It's an integrated system that has to work in the real life, in the real world. And then I'll talk about the analysis of the system that we exposed to our regulators and that we exposed in the demo that we had at our airport. So we call it Safe Runway because that's what it should be. And just a motivation. So from the FAA Runway Incursion Database, so this is publicly available data. Over the last 22 years, roughly about 700 out of 16 million flights per year result in an incursion. Now, those of you who work in machine learning, in AI, will say, oh, this is very rare. Like when you report in a conference that, your accuracy is less than 10 to the, or around 10 to the minus 3, you should be happy. Well, in aviation, we're not happy with that, right? So it's a rare event, which we want to make it even rarer if possible. So roughly based on this data, it's about between 10 to the minus 3 and 10 to the minus 4 probability of an incursion. 2 years ago, the New York Times had a piece on how airline close calls, and it's about incursions. They basically mentioned that incursions is one of the highest risks. And if you think about it, there is nobody to blame about it. The airplane is moving at high speeds, especially at land. And there is a limit here. The limit is the human perception. Yep, okay. Yes, right, I got it, yeah. So, yeah. So the limit is the human perception, right? And we, with our technologies, we're here to break those barriers. So it's not that we want to take anything from the human pilots. We want to assist them to be even better for a safer aviation. So how is it done today? With 2 pilots in the airplane and all the training of the pilots. So the pilots are trained. They're air traffic controllers who monitor the situations. There is an assessment done by the pilots during landing, a very busy time during the flight. There are visual cues. There are radio communications. There is a global situational understanding that is attempted to be established between all the entities here. And you'll see, if you go through the examples in that database, you'll see situations where maybe the traffic controller had some uncertainty and the pilot had some uncertainty, but together they came to the conclusion there was an incursion. Maybe only one of them saw something. There is also radio communications. There is ATC to pilot dialogue and so on. Together, pilots and traffic controllers right now are trained to avoid situations and collisions that can result from incursions. And now, when we defined our approach, we carefully defined from a computational perspective what type. So it's aircraft vehicles, utility vehicles, general aviation, humans, animals. There could be luggages dropped on the runway. Yeah, it happened. So all this can be a hazard. We all know there was a case in Alaska where a bear was hit at night, so nobody was at fault. It was probably an access, bears swim and access the airport. It was in Yakutat about 4 years ago. So basically we divided the problem and we basically tried to tackle it in its entirety. So here you basically see one of these scenes, and this is what the pilot sees. You barely see the runway. Now talk about having a luggage on that runway, or an animal, or a car. So computationally, because this is what we have to do when we approach the problem, translate the real world problem into a computational problem. And yes, here perception plays a big role. And yes, this is basically what a camera sees. There is a car. It's actually, this was a big car. We also have smaller cars. You saw there was an SUV. This is what it sees. And this is what a pilot sees, or a camera. So we have to make this assessment. We have to make it continuously during approach. And yes, we have challenges beyond the challenges that autonomous cars have. Thank you so much. Okay, I'll switch. Thank you so much. And you will see here some challenges for your favorite computer vision or deep learning approaches. Deep learning approaches in computer vision count on texture and geometry. There is virtually no texture and minimal geometry there. So we had to tackle this in a research way. And we also had to think about the risks, and we'll talk more. Not only the false negatives, so not detecting something. We cannot bother pilots with false positive. The trust will go lower, and we have a high standard there. So in numbers, we worked with our pilots and with the regulators to see how low do we want to go on objects. We basically go down to about 2 meters. So a car from 3 kilometers in our image is 0.001% of the image. Take your favorite small object detection public data, and it's much larger than that. So we had to deal with that, and yeah, it's humbling, but we have to do it. At 1 kilometer, it's a little bit larger, 0.01%. Okay, so the goal was, and we were here roughly at the time when COVID started, 2020. And the goal is basically to detect and alert accurately, both minimizing down to 0 the false negatives and to an acceptable numbers the false positives in the alerting of these kind of incidents. So before that, this was the first question that I had was, and I went online to look, let's see how many incursions we have in publicly available data. Guess how many? Basically 0. These are on our airplanes today. We don't have computer vision level cameras. Yes, pilots see them. Yes, each one of us can imagine that, but there's no data. So I want to, before our meeting with Guillaume and Giovanni, I thought of illustrating this problem from a computer scientist perspective. And so we had a lot of knowledge between us and the pilots. They can describe, yeah, I was there and that vehicle crossed the whole short line and it was away or it was close, it was white, it was moving like this. But let's acknowledge, and this is not only for runway incursion, for every single computer science problem we have on a domain right now. Think of your favorite problem, and it could be cooking steaks for your favorite guest. We have knowledge, and that's our knowledge, for example, about how an incursion can happen. We have data, and when we say data, it should be data from the sensors that we will use when we will make the decisions. And now, this is basically the basis for our decision making. Where we have data, yes, we can use our favorite machine learning tools and so on. We build something redundant. Green regions, we do statistical testing, all that. We have these regions where we have knowledge, but we have no data. And in aviation, we have many of those. Those correspond to accidents, incidents, which you cannot, many of them, you cannot possibly recreate. We cannot recreate an accident. And also in medicine, we cannot force people to smoke to show that smoking causes cancer. So these are the known unknowns. We know they are there. So those are, for example, the incursions or the close calls that happened in the past. And then we have the unknown unknowns, basically knowing that at any point when we execute this, something new will happen. For all of us here, the rest of today, I guarantee you that we all will see a situation that has never happened to us before, and we have to act, and most of us will act safely. So that's the challenge for our computational system. They will always exist, and they have to be handled at runtime. So at the beginning of the problem, the incursion problem, we were basically like this. Available knowledge, yes, pilots could describe situations. Data virtually zero, and a lot of unknown unknowns. So we started to collect data at our airports with our experimental airplane. And we started to have a data strategy, which I recommend to everyone to have a comprehensive data strategy. Basically, we want to increase the green and see how we deal with the blue. We know that the green will not be all up there. We can't have data for all the situations, and we'll have to handle the blue. So the thinking about the data and knowledge in summary, and talk to me separately if you want details, we started with some data in the wild, and we started collecting them. And that's not for training. It's first for understanding the problem. We just wanted to understand, how does a car look like or a vehicle look like when we approach from 3 kilometers, 2 kilometers, 1 kilometer, 500 meters, and so on. And then, yes, that data, real data, is costly. And yes, we are at the point where we look at synthetic data, generating data in between the data points. So if we've seen enough cars, we can move those cars and so on. But importantly, in our case in aviation, is that the data has to be physically relevant, and simple Gen AI approaches will not apply. It has to be physically relevant. We can't, let me give you an example. Clouds. It's not the problem of the clouds when we approach. Our problem is the clouds produce shadows on the runway that are actually very hard to recreate synthetically. A car coming from a shadowed place, which is much darker than a strong sun place, is actually an interesting situation. Then the shape of those clouds can be anything. So that's just one, and I can give you more. So we had to have that. And yes, data first for understanding, then for validation. If I give you a box, UFA, EASA, how do you validate that? And then yes, about training our perception models. So our engineer's challenge was to identify the dimensions that are informationally relevant for the task. And that primarily in our case is about the sensors. And don't think about the sensors only your camera, radar, LiDAR, sonar, whatever. Sensors is also ATC. The spoken dialogue is not only for clearances, but to provide perceptual input. Internet, long-term distance, right? Pilots have access. If there is a storm in Chicago, they see that the storm is coming, they document themselves, and then they reroute, right? The means for collecting and generating and managing this data, huge underlying task for everything here. And then the means to handle that low density and no data. I think ultimately this certification challenge will be about the last bullet. We have many regions where we in aviation cannot take risks, cannot produce accidents, cannot harm people, but we will have to be able to have our systems act in those situations. And that's why we, at the beginning, will need to be extremely conservative. So here I'm showing you roughly at high level the architecture of our system, but overlaid on it, I want to show the problem of the dimensionality. So many of you mentioned complexity, dimensionality. So very high dimensional, the input. Any input for our situations, all the dimensions in the image, multiple sensors, spoken, and so on. Why don't we build just a model to go down to a decision? Because that model is extremely complex and has to run in real time, and it's not computationally tractable. So first, there is a totally symbolic carving of the scene. Basically, we detect objects in all over the image, but all that matters is around our runway and close by. And we use airport maps for that. So it's a detailed thing, but it's a symbolic thing which can be certified. It's not, and it's something deterministic and static. Then there is the object detection component, which can have multiple detectors. They can be fused in certain ways. They can be combined. But the important thing that we need to think about them is dimensionality reduction here, right? From all those inputs, all those pixels, all those radar returns, we get to a lower thing. Here are the cars. Here's what matters in that image. And then a very important step on which we increasingly focus more with the regulators is the step that very few people talk about, but it exists in virtually, well, in every system. Post these detection systems, there is a reasoning component which for images is mostly tracking, combining the tracks. It's going from those few dimensions to one dimension at the output. Should I go around or not? That's a one-dimensional thing, binary thing, right? And I want to emphasize on this because we tend to forget about it, or we tend to say, yes, it's only a Kalman filter. It's way more than a Kalman filter, even for images. And that's where all that probabilistic reasoning is happening, logical reasoning, probabilistic reasoning. And it's not to be confused with the previous step, and you'll see why it's important. So about that step, Marvin Minsky, one of the fathers of AI, said in the 80s, you don't really understand something if you only understand it one way. And that's very true for us people. If this room goes dark, all of us will be safe. We find our way out. For most computational systems right now, we do computer vision one way. There is one detector. If that fails, we're in the air. We do speech recognition in one way. So aviation is used to redundancy. Most of the systems in Airbus, Boeing, you name it, Embraer airplanes, think about depressurization. There is a highly redundant independent system. So in mechanics, electrical engineering, and so on, we have that. We have to build that in our computational systems. And that's where that fusion comes in. And I want to emphasize on that. So that's why on this, yes, we focus on ADS-B, but we fuse that with cameras. And yes, we are aware that if we add more sensors, we can do even better. We have our computational challenges and doing in real time and so on. We did what we could best, but that's very important. And even in the long run, once we'll have these systems, in our lifetimes, Guillaume, right? We'll have these systems run, I'm sure there will be many sensors that will be fused the right way, and the systems will be redundant. If a camera will fail, you will not be unsafe. So that's our thinking, and that's how we should do it. So the mantra is understand the problem one way, another way, yet another way, as much as you can afford computationally and with the resources on board, and that will give us this multifaceted understanding that gives redundancy and robustness. So our goals for our safe landings is basically to assist pilots in this safety critical task. And yes, as you'll hear from my colleague Emily, yes, this is a human-computer team. It's something that I came up to speed. At the beginning, I thought, oh, we'll present the scene and we'll show the tracks to the pilots. Well, pilots are busy during landing. We have to do very careful alerting. So I learned a lot from the alerting from other safety systems that are on board, namely TCAS and the other ones. Desired, zero false negatives, obviously, to detect all incursions. And also, in many other computational tasks and in machine learning, false positives can be tolerated. Here we talk to traffic controllers at SeaTac in San Francisco and Denver. You can't go around, you can't have 5% of your flights in an hour go around because you'll fill the airspace. It's actually a safety situation. So really small false positives, false alarm, and enhanced robustness through multiple sensing. And yes, we know our location and so on, so we have our own chip. So roughly the situations that we have presented to EASA and we have in our tests is basically one of the common scenarios of incursions. So when the traffic is on the runway, the airplane is far away, these are common situations, then the traffic goes out, right? There's another airplane, it clears before the airplane lands. The other one is traffic is outside the runway when the approach starts and traffic comes in. It may clear or not, but at the beginning it's not there. And probably the most challenging for decision making is when the traffic is on the runway, and especially when the traffic is static. And you will also learn if you study animals, static objects are the hardest to detect. A fly on the wall, if you turn on the light, will stop for safety reasons for the fly, because it's the hardest to detect when it's static. And yes, in our case, you saw our Boeing airport, we're very proud, it's very well maintained. You saw there are not many rubber marks and so on, unlike, very busy airport. And you saw it has two types of asphalt, gray and dark, also white. So a black car on the dark asphalt was virtually impossible to detect by our pilots. Also, the aim pads and the piano keys are as wide as a car. And when we park a white car on those aim pads, it's not visible. It's completely not visible. So we had to deal with those. And those were our most challenging cases. So our sensors, ADS-B, most of you are familiar with ADS-B, automatic dependent surveillance broadcast. It's what's used by FlightAware for the positions of airplanes. It has, in the air, it's mandatory. It's a rich source, but it comes only at 1 hertz. So also on the ground, it's not mandated, and it is also highly susceptible to spoofing. I want to mention in that video, during the demonstration with EASA, we had actually an unplanned glitch. ADS-B went off on the incurring car. So we were happy. We said, wow, look, now we have cameras. So it went like that, and in reality, we know that that can happen. So that's why we have visual perception. Visual perception also has its downside. The detection range, field of view, and so on, they are inversely proportional and they are challenging to handle. And also, it's high compute cost. You all know all the computer vision tasks require special compute. We have to do that on the edge. Air power on any airplane is very limited. So in our analysis, we tested visual-only detectors. So this is only cameras. We tested the detector, which we did not present live in the demo, but we have and we presented in experiments, ADS-B queuing. That is, we have the ADS-B input, and we queue the vision to look at that location. And hybrid fusion is basically camera and ADS-B together, and they are fused, and they detect. Obviously, you'll see hybrid fusion is much more robust and much more accurate. Computationally, it's also the most expensive. So we always, remember also in all this, engineering is also the science of making compromises. So we always, when you engineer a system, especially to run in real time like this, you have to make the compromises and in order to stay safe. So this is basically a video and you've seen a little bit of it, but this is what we want to see. This is one of the ideal cases. And in it, you'll see also some of our alerting. So what's in light blue is inside the runway safety area. What's not is outside. If it comes in, it becomes light blue. One is basically, we have the ADS-B track on that vehicle. We don't have the visual track yet, but we're far away, so we approach. Also, please note how the camera moved. It's on the airplane. This is real thing. So this is how your camera will move. And yes, we may lose the runway and catch it again. That can happen. At our airport, we have these strong side gusts, which cause us to lose that insight, and we factor that in. And what you'll see at some point here during the landing, we'll get the visual track here. Now we got the visual track, and then we have the hybrid fuse track, which is the rhombus. Also, we have a true three-stage alerting, right? A caution, a notification, a caution, and a warning. Warning is red. We try to match the types of cautions and so now it's yellow. We're close. We start to have the caution in yellow, and as we go closer, it's going to be a warning in red. You have here the altitudes and so on. Now you'll see the airplane takes off for safety reasons. Obviously, we are not landing when there is an incursion, so we go down to about 100 feet AGL. So that's our experimental setting. Okay, so results. And for these, we considered that 50 meters AGL would be the threshold for us to make the decision. However, we monitor this as we advance, as you saw in the video. At the beginning, when we worked on this, we did not have ADS-B on the cars. We put it later. So that's why about 64% of our cases do not have ADS-B. That's the earlier data. About 41% of our data have no incursions. Those are normal cases. We don't want an alert. About 59% have incursions. And so here's our cases. So when there is no incursions, 41%, those we don't want alerting. Zero, so this is the distance to the intruder. So if the intruder is towards the end of the runway, it's more than 4,500 feet. So this is the percentage of cases. We try to cover as much as possible. We have flown the airplane in different seasons. We also flew it in winter. I think some of you have seen those images. Very different, very challenges. So that the winter falls into it was fall actually, but there was snow on the ground. Summer conditions, spring conditions. So we want to see that because in many of these, in the image, the colors, the textures, the objects do change and may influence the decision making. So we had over all our test conditions, one false positive, and yes, we'll go into that case. We'll go into those errors. So basically we had 3 errors, one false positive, and then, one false positive and then 2 false negatives at 2,000 meters and beyond, and 3,500 meters. I was very happy that virtually right now we're very good at something that's very close. So basically for our airplane, even if we don't detect these, there is no collision risk here. These are far away. For a Caravan, yes, we have to improve. And yes, at high distances, so this is very long distances at the end of the runway when it wouldn't be, even for a 737 or an Airbus A320, it wouldn't be a risk. We go bad. So yeah, and we'll have to improve, yes. So visual only. So this is only with the cameras we make, obviously, those errors that I mentioned. where is the 0.99? Well, it should be 1, but we do Bayesian correction. So we do a Bayesian correction based on the probabilities that we compute, and we assume that, and we look at the probabilities inside what's computed. So we never say never, right? We made these errors here on visual NADSB and actually on hybrid fusion. That vehicle was detected. At the very limits, so always this is experimental flying. We always have Boeing Fire with us. So this is how a fire truck looks like from 13 kilometers. It was parked at the end of the runway. When we start the approach, this is how far it is, and we detect it very well. Talking about the fire truck, yes, it's big. You'll say huge, yellow. Let me tell you, when it came on the runway, in the center of the runway at the beginning, we had problems with that, and so did the pilots. We have airports, runways are basically a number of vertical lines, and we match that in our patterns. Even in real life, when a car comes along the road, and if it's a small car, you have here smarts, right? So those are harder to detect. So even the fire truck, in some situations, it was hard, and we had to work to improve the detection. So this is that case. The fire truck was there at the end. As you see, we have other cars around, sitting, being parked, moving. I wanted to mention that given that we do tracking, cars do overlap, so they may go in different directions. We want to keep those tracks and know that it's the same car. And this is how close we get when we start to have solid at AGL 49. As for analysis and evaluation, in batch system evaluation, we do 56 metrics of detection and tracking, which we disclosed with our regulators in runtime. So online evaluation, 6 metrics, and in real time, we have a visualization system. You saw Giovanni and Guillaume there in the tower. In parallel, we displayed what we have on our system, so basically how our system, so it's this rich display. And we had the opportunity to look into the details, how we match the tracks and so on. As you see, this is one of the images with the winter. These are the windows that are computed and then tracked and prioritized. So specific metrics of interest, you saw 56 metrics. And basically it should cover, and it's not that we pick them and, oh, let's have as many metrics as possible. Each one of them provides some piece of information that's useful. So just for tracking, we have multiple objects. So there is a very good paper on multiple object tracking where they list relevant, so multiple object accuracy, precision, not performance. What multiple object accuracy is basically how accurate your track is. The precision is basically a continuous value, how far you are from the ground track, an average of your individual predictions. There is also track quality, track continuity, association. I think we created more than 10 metrics of our own that we thought are relevant. And an in-depth alerting on these metrics and so on, so these will be reported. And so I know we're here for machine learning, right? So something that you'll find stunning, you saw that we're very accurate in our alerting. So those of you who work on individual models, please don't overbeat them. This is our performance at 75 meters. Our recall is not perfect. This is corrected by the tracking. We have many, many frames, and the track, if even humans miss frames, but the tracking will recover them. So this is the individual. I wanted to show this to see that alone, I mean, you would not be happy with such a performance. The system, however, the tracking will recover as long as you don't have too many of those in a row. So this is at 75 meters AGL. And I'll conclude with the analysis of those failures that we saw. So what happened? One false positive in May 2022. And so this was a false positive. It was in the distance. And it was an alert on a marker sign at the distance. And yes, it was the first time we were at that airport in the spring. And it was very good contrast between the marker sign and the grass, the green grass. We detected that and we alerted on that. So that was the false positive. We went into the analysis of that. And yes, since then we improved. So the way to improve on this, two ways. Marker signs are fixed. So now we know where the marker signs are. And so we also know on the runway where the darker spots and the less dark spots are. But also we noticed that, oh, the green grass is an issue. So we had more data collected in that region and so on. So this was the false positive. The critical false negative was at 50 AGL, right? The intruder is estimated at less than 3, so it's in that between 2,500 and 3,500 meters. And yes, it was, we did not detect it. We had already ADS-B on it. This is detected by the fusion. So vision alone misses that. It's that case that the fusion actually fixed it. Also, the ADS-B queuing was not fast enough to do it, so the fusion fixes that. And the margin of failure, so this is the failure that we believe wouldn't be a collision, but we want to detect that. That was in September 2022, and we did not have ADS-B on that intruder. We had on another car, but we didn't have on all our cars. We found it and we lost it. It was one of those cases that we detected and we lost the track, we detected, so we didn't alert. So, and again, this was a marginal failure. I look for, yeah, wrapping. All right, so in summary, we talked about our carefully architected system for incursion detection. I provided you a system architecture overview, and I think I provided you enough motivation for us all to work on these things, because basically we enhance the pilots. We want, and this is necessary for having that safety, given that we have airplanes that move very fast. Again, it's a system. It's not only a single model. We talked about detecting, tracking, fusion. I hope I made the case for fusion and multi-objective, multi-sensor combinations, and provided you a snippet of what kind of analysis we provide to regulators. And yes, we have to improve on that. Notice the large number of metrics that we monitor, and I think it will be even more. So thank you.
Thank you, Dragos. And we have now the last but not least presenter, who is Emily Howard. Emily is a Principal Senior Technical Fellow in Human Factors Engineering, specializing in human information processing, perception, and cognition. Emily, the floor is yours.
Good morning. Thank you, Dragos. One disclaimer, we're going to go back to the automated taxi system, because that was the primary focus of our IPC. And so most of the human factors findings will be related to that. I only learned about runway safe at the demo back in June. So love to dig into the human factors issues of runway safe, but that will have to wait till another time. But from the IPC, I'll start with just the key takeaways. And our final report will be published hopefully in the next few months or so. So these details will be available. But the starting point is that, and I think the whole focus of this conference is we are moving into new concepts for aviation in the introduction of AI-based systems. And with these advanced automation applications, that means the role of the human is evolving. And nevertheless, whatever that role is, we still want to apply human-centric design principles throughout the development. And it's important to understand the interaction requirements as part of the human interface. And I'll talk more about that, what that distinction means. How many of you have heard about STPA before today? We mentioned a little bit. Okay, good. About half of you. It'll take me about another hour to explain what it is. So, but I will point you to some other resources. I will say I've used it a number of times. I think I started over 10 years ago learning about this. Every time I use it, I'm just amazed at how useful it is. And I'll leave it at that. And so we used STPA on this particular project. I came in trying to decide, how we were going to quickly bring up the human readiness level, which is something I'll talk about in the next panel, to match the technology readiness level of the automated taxi system. And I proposed STPA. EASA was very excited about the opportunity to observe the analysis, in situ. Couple of key takeaways. STPA helps you to address the non-normal yet possible situations early in development. And we've talked about how important that is to get those edge cases, how the human has a key role in managing those non-normal events. And STPA can also be used to show regulatory compliance as one of the safety analyses that you can use to support your application. A couple of other things. We spent a lot of time testing this technology, not necessarily thinking about how we would integrate it operationally. Those test user interfaces do get developed, but they don't necessarily replace the need for an operational user interface. And the last point, which I'll touch on briefly, is the observation that particularly as we get into level 3, and we are now replacing human intervention or excluding human intervention, I will say, we need to understand what we are losing. I know we often think about the benefits and the gains. Well, we're preventing human error and we are reducing latency and making things more affordable because we're not paying for human salaries and so forth. But we don't always know what we're losing, right? We don't spend a lot of time understanding the positive contributions that humans make to the safety case. We do spend a lot of time understanding human error. I maintain that we need to start putting more investment into understanding human agency and the human benefits. So just to elaborate on that, the role of humans and machines teaming together are evolving from the early days of the human as the controller with all the responsibilities for all the vehicle and mission functions, moving to maybe more of a mission commander, where the human performs key mission and vehicle functions, but the vehicle has more autonomy and has more ability to perform tasks independently, almost to a supervisory role where the human is really just required to monitor vehicle and mission functions, to lastly, which is sort of the contingency management. This is the level 3A, that upon alerting, the human will be allowed to intervene and potentially override. I maintain, and again, we all think that's a good thing. We're decreasing human workload, and workload is bad. So why wouldn't we want to just automate as much as possible, increase autonomy? Well, because workload isn't always bad. Some of you may know, and this is a notionalized relationship, that human performance and workload are not linearly related. Very high workload, we understand, right, can degrade performance. But when you think about it, very low workload also can be used with complacency and distraction and so forth. So decreasing workload unilaterally isn't necessarily the goal. And understanding the complexity of how workload and performance relate to each other is an important principle of human-centered design. And that has implications for the interaction design. We don't necessarily want to take the human completely out of the loop, right? If it lowers the workload too low, it can actually degrade performance. And so you can kind of see, you know, from the spectrum of different roles that we're sort of moving into some of that danger zone of very low workload and very low performance. The other piece is that contingency management, even though it's sort of potentially its own role in and of itself, has always been a responsibility of the human operator. It's just one it's embedded. And what that really comes down to is that those contingency management, those non-normal tasks, are a really useful place to begin your design process, right? Because they are critical. The human will always have some role and responsibility in doing those contingency management, non-normal responses. So take some time in your design process to understand those. And this is, again, kind of not how it's typically taught, I think, in most systems engineering programs. And this gets into the idea of interaction design, which is important as a subset of the overall human interface. A lot of people think, we'll design the human interface at the end, or we'll test it first, and then we'll use the test user interface to become the basis of our operational user interface. Well, that isn't necessarily the right way to approach it, because a good interface depends, first of all, on getting the interaction right. And the interaction design goes, which I define as the who, the what, the when, and the how well. So who and how, you know, who are the users, who are the stakeholders, and is a maintainer required to have responsibility in the system, as well as the operator. Air traffic control, whether they're an end user or not, they still have a responsibility and a task to perform. What are the tasks? What are the information and action elements? When are those tasks required or desired, and how well in terms of precision and timeliness? Those requirements go deep into the system architecture. This isn't about the last thing that you build in your solution. These are fundamental decisions that you want to make right up front. And so that's why the interaction design is one of the first things, and getting those requirements correctly identified is one of the key steps in your development process. The whole interface then adds on the where and the how, the graphical elements, the visual elements, the buttons, the alerts, the tones and things. Like, yes, the interface does include that, but it rests upon having a good interaction design, which is why we say human factors has to be integrated early and thoroughly. Because if you wait until the end to say, well, we'll just put the buttons and the icons and the symbols later in the design, you've probably missed some key interaction requirements. And so you begin with interaction design decisions. So early human factors engineering involvement is key. And so Josh presented this slide. I just repeating this. This was our level 2A concept of how the automated taxi system would work and what was the flight crew responsibility associated with the level 2A. We then used STPA as a way to create those interaction requirements that I just described, focusing on the non-normal events. And that turned out to be a very powerful technique for then rapidly understanding what were the human factors requirements to go in conjunction with the design of an automated taxi system for level 2A. So in traditional STPA, we define the losses, we define the hazards, then we model the control structure where we see the ground traffic control, ATC, offering, taxi commands, the flight crew, the autonomous executive, the airline operators, the idea that there's a database that the autonomous executive uses. It has to know which airport it is. It has to have the map details, and there can be problems in the system. So making sure that we think about the contextual interactions that or surround this autonomous executive for the automated taxi system. And then go through traditional STPA analysis. Josh showed you a couple of examples. So starting with what are the unsafe control actions? Again, the non-normals. One of the actions that the flight crew is allowed to take is to modify the route. Well, we came up with different cases where that might be unsafe, where might not be it ideal for the flight crew to modify the route. One would be they provide an invalid route, or they provide a modify route when, or they do not provide a route when needed. And again, these are straight out of the STPA process where there are different classes of UCAs from either being provided, not provided, out of sequence, or wrong duration. And so you can look more into that. And I put a link here. There's an upcoming workshop on STAMP, which is the overarching approach. STPA and CAST are the two techniques happening next month, and they're virtual, and the registration is free if you'd like more information. So just to kind of recap, we've seen the systems engineering V. Mostly our flight deck design process follows the classic systems engineering V. We did not follow a flight deck design process on this project. This is an R&D project. We had to just sort of quickly jumpstart and come up with the human factors requirements. And so we used systems theoretic process analysis as a way to jumpstart into that. Which not only helped us by creating those HMI interaction requirements, but also supported the functional hazard assessment. And as Josh mentioned, also supported in the verification and validation planning. And again, tracing from the UCAs, the unsafe control actions, to the causal scenarios and classic STPA, then led to requirements where, in this case, we have an example that the design of a system must ensure complete and correct situational awareness, including the current state of airport NOTAMs, right? You need to know you have the current map, right? And that's one of the key, that's a requirement that might have been missed had we not done the STPA analysis. We also talked about STPA as a means of compliance. I won't go into all of these, but either full or partial, STPA turned out to be a very helpful technique to verify our support to the concept paper objectives. Moving ahead to a level 3A system, the automated taxi system really didn't change much from phase 1 to phase 2 of our study. But the STPA changed quite a bit because we now have a completely different human role in the system. Now we have a multi-vehicle supervisor monitoring autonomous vehicles that are all capable of auto taxi in a group of 3, similar to some of the concepts that we're seeing for advanced air mobility. And so, again, now the MVS is expected to passively monitor the behavior, intervenes only upon alerting, have a direct data link and a means to talk to air traffic control, rapidly build situation awareness. So again, starting with the ConOps, right, we can start to then use STPA to drill down, okay, what are the HMI requirements, the interaction requirements, if you will. So again, we have the same autonomous executive as before, but a very different system model because we're now looking at a level 3A application of this technology. And so you'll have different requirements and different possible hazards to different non-normals that you'd want to look at. Again, I talked about how the test interface can inform but should not replace the operational interface. So this was part of the ground station that was used to monitor the auto taxi system in our demo that we did in June. So I just wanted to show, yes, we can design it, but this is what the test team came up for. It doesn't necessarily meet all the requirements that we came up with in our STPA. And my last slide is to go back to the point with the observation of, well, as we move into level 3 systems, and we are really asking humans to perform a very limited oversight and almost passive role, we have to understand what are we giving up. And so it led to me to propose an additional objective for a level 3 AI system in the style of the concept paper, where we are aiming to reduce human interaction compared to current or comparable system. We should design AI-based systems with a detailed understanding and retention or enhancement of all the human contributions to operational safety and performance. So that's just something to think about. Again, we have a lot of data on what humans do wrong in our systems. I think we need more data on what they do right. Thank you.
So I know we want to get to questions, so I'll make this quick. So just wanted to say thank you both to EASA for inviting us here today and for coming out, like I said, coming out to the demo that we did earlier this year. Also like to thank the Boeing team, both those that are here in person today with us and the large number of people that worked with us back in Seattle and other Boeing sites that couldn't be here today. And also thank you all for listening to our presentation. And hopefully this was interesting and gives you something to think about as you go back to your own organizations and you work on your own systems. Last but not least, I'd like to say, I mentioned this at the beginning, but, when we started this IPC, we saw the other work that had been done, Codan, MLEAP, formula, those kind of things. We wanted to add, like I said, we wanted to add to that body of knowledge, and hopefully we did that, and hopefully you found this interesting. And speaking of those other projects, we'll have a report similar to those where we'll be releasing it publicly. We're in the final stages of getting it edited and approved for release, so hopefully the next couple of months we'll have something for you. And there'll be some announcements when that is published and available. So soon is what I can tell you. So that is it. And so wrap up with Q&A here.
Thank you, Matt. So let's start now with the Q&A session.
And yes, when you test, that's a real aurora. It's not generated. When you test, you get to see these kind of things.
Coming soon.
So please use the slide to submit your question, but you can also use the microphone that is being passed around. So we are happy to take questions both ways.
Thank you for sharing the great work. In the beginning, you mentioned there's no data or limited data available. So I'm wondering how much data have you collected for training the model and tested the model? Is there opportunity to leverage the autonomous driving world to speed up your development?
You saw, it's not about how much in machine learning, it's about the data distribution first. And it's not about only the training. I hope I made it clear. It's about understanding and validation. We covered all those cases that you've seen in detail. And as experimenting advances, we collect more. However, I knew that this question will come. It's important, but it's not everything. So I want to mathematically, when you have the machine learning 101 class, you're taught that the world is your data on which you evaluate. For us, it's not that. The real world is way more than that. That's why I emphasized on the probabilistic aspect of making the inference on those cases. You heard the autonomous executive mentioning, in regions where we have low confidence, we fall back on systems that are not learned. For example, you saw a situation, there was a photo in which we lose the sensors. For that, you don't need data. Don't go for machine learning for that. You should be aware that it's an unknown situation. So do a plan that minimizes your risk. George's key word in the presentation was risk. We collected data. We'll collect more. All our experiments show that what data we need to collect, but that's not the central question. The central question is, how do you model? So we have on every subsystem and on our entire system always a probability estimate of how good we are. We go very conservative, and when we're outside of that, we try to fall back on something that doesn't rely on data.
Thank you very much for your talk. So I have two questions. One is more technical and the second one is more assertive. So the first one is, while you are showing in the video the approach, there was different figures indicating different methods. Like one is the hybrid one and the other one is the only visual camera based. I wasn't able to identify the difference you were showing in the video during approach in terms of different approaches. Was it that one of them was a bit faster to detect the object? And
yes, so ADS-B, if the ADS-B comes in, you have that early. You saw that in the video. I had ADS-B from the beginning of the approach, if ADS-B is in. Visual is later. And we do also report something intermediate. So on tracks, we have 3 levels. One, a tentative track, a likely track, and then we latch in. And EASA has seen that in the demo. I didn't want to overwhelm, but we have a high confidence track once we go through these steps. And indeed, ADS-B, if you have ADS-B, is good because you have it at the very beginning. So that was the yellow thing at the very beginning. Just the circle was ADS-B. The rhombus was so then we had the visual, and then we fused them. So, yeah.
And do you think that having the Kalman filters and like fusing will it be considered as a hybrid AI or?
So we do probabilistic fusion. It's more that, so on individual tracks, we do Kalman filter, but then we do probabilistic fusion. We took all of them and we tried to match them. Other sources of error can come. You have the ADS-B, and if the visual is a little bit off, you may make, when we look at that, you may make an error that you think it's 2 tracks. And we've seen that, for example, as it was heard in the public, the accident of the Potomac, it was humans not knowing which one was which. So we monitored that one as well. So it's Kalman filter plus probabilistic fusion and continuously monitoring the confidence on each of the tracks.
Thank you.
Until you have confidence that you latch on a track.
Thank you.
Okay, then let's go to the slide of questions. First one, in the end-to-end process, where is the most difficult resource-consuming phase? Data management, model VMV, system VMV, others?
Excellent question. There's one more in there. So data management is not seen and not mentioned because it's dirty, but it's necessary. And when I say data management, I'm talking here about, so you saw we could go back now to 2022 and say, how would our system perform? That's why we didn't have ADS-B, because in 2022, we didn't have ADS-B on all cases. And more, we envision on the data that we collect today, we envision that, maybe in the future, for sure, we'll have another tracking system and so on. So we collect as much as possible. But in the data, one thing that I'm sure all of you who do practical work know, is the ground truth. The ground truth is what's there. That's also noisy in our case. We label internally, but also with external entities. And yes, we had houses labeled and so on. So we have to go through that. So all that is data management, is costly. But if you understand it, it's not something that you have to think about it and set it in place and do it right. System V&V instead is hard. Now, yesterday, I had a question here, and it didn't make it. One big question for us is, and it's not answered, at system level, we know the requirements. Stay safe, detect the car, and so on. We do not know how that requirement trickles down at the level of model. You saw that our model itself is not perfect. The system is much better. So now, how does that, so that's why we had discussions this week, ourselves and others. The requirements on individual models are different. I'm not saying they are less or more. They are different, but you should keep in mind what's at high level and try to infer. That's the hardest thing. And what you build around that model, yes, we work on having that model even better and the recall even better. How much do we put in that versus how much do we put in the other steps? That's challenging. And then there is one more in aviation, and EASA and the FAA acknowledge, and that's a safety thing as well. I'll tell you what. Every time we develop a system, which actually we can prove it's safe. And by the way, we have a video on YouTube on in-air avoidance. We prove computationally and mathematically it's safe. We go to our pilots. We don't even get to EASA. Pilots say, this is not how we do it. For example, we overtook an airplane, flew in front of it because we estimated the speed to be low. Pilots don't do that. They go behind. And other things. So I call this showing airmanship, showing it's the culture of aviation. We have to insert ourselves in that. I'll give you such an example from auto taxi. At the beginning of the work, I said, I don't care if I taxi on the center of the runway. I'll be safe on the left. Our pilot said, no way. When you are seen going like this and so on, we think that that's unsafe. So that's not intrinsically a safety thing, but in that world, and we had discussions with our EASA partners on, they actually consider that unsafe. So it's not that you risk something yourself, you risk something at the multi-agent system level. And that's extremely hard. That's going to be extremely hard for all of us for whatever we tackle. We cannot rethink landing and do it the way we want because computers do it like that, or avoidance in the air. We had to do avoidance the way pilots do it, follow lines the way pilots do it, and that's sometimes lost in the discussions.
Thank you, Dragos. Okay, so being mindful of time, we are running a bit late on this session, so we will take another 10 minutes to process a few other questions, but please, let's try to be very straightforward in the answers so that we can manage as many questions as possible. So let's go to the next one. How do you assess the safety of the system? I'm referring to the safety objective of the concept paper with the related mock.
Every safety question that is there, we translated into a mathematical form. In auto taxi, something that you probably didn't notice on Josh's slide, there was a navigation database. And I've talked to our Airbus friends yesterday and so on. It's that we translate the safety is something vague. Humans understand it. We translate that into a formalism at system level. As I said, at model level, it's still work to be done.
Thank you. So next one, what is your general feedback on the EASA AI assurance framework? Not demanding enough, just necessary, too demanding?
I think we work together. I wouldn't, it's, what we do is too complex to just say a word. I mean, it could be misunderstood. I think both EASA and the FAA want the best. And we come, and let me tell you, within this work, we discover new things that have to be added or things that may be missed out. Maybe it's a little bit of everything, but don't take, I mean, if I say not demanding enough, oh yeah, or no. We're on the right way. This is, I have the same dialogue with our pilots and with our safety people in Boeing. It's pushing forward with a single honest goal to be safe. And we want to translate that formally and into regulatory requirements. I think one place where we have to work more on the system level, and we had these discussions, system level versus models, because you saw there is way more than just models.
Thank you, Dragos. So let's go to the next one. What if there is a failure of the system that commands the braking system when the airplane is taking off? Is the failure still classified less than major?
We didn't do any takeoff here, so we haven't worked on takeoff. I think the questions on braking and acceleration, you saw that we control basically direction, braking, and so on. If it leads to a high risk, yeah, it's major. So it depends. I hope Josh showed you the horizons. If it's something that you don't detect 2 kilometers from here and you move in a car, that's not critical. So it has to be analyzed on a case-by-case basis. And yes, if it brings the risk of a collision, loss of human life, major damage, it's major.
Okay, so next question. Did you compare the performance obtained with the AI system and without human visual detection only?
Yes, you saw it. Virtually all the static ones, humans do not detect or detect much later. Yes, we constantly compare that. So that's why I said we enhance the human. They acknowledge. Now, when we do these tests, the pilots also know exactly where the incursion happens. So obviously it's like queuing. They look there. In many cases, they look there and say, I can't see it. So, I mean, to do a fair comparison, safety-wise, we cannot do it to not tell the pilot where the incursion is because that's unsafe. So that would be a fair comparison. Yes, we compare it, and obviously at the long distance, we detect much better than the human pilot.
Okay, next question. Did you train on real or synthetic data or a mix? What feedback would you give on the qualification of the simulator? Sim to real gap.
Amazing question. Most of the training on real data. I mentioned to you for synthetic, I'm talking here for the landing, but also for the auto taxi. We as a world, as a community, not Boeing, we are not there on physically relevant images. I'm just talking here reflections from a puddle from the sun. You saw in some conditions we have the sun in front of us. We try to stretch what we have, and we work not only ourselves, we work with some startups that have the cream of the crop coming from the Teslas and SpaceX. The imagery that they generate are either too easy or difficult but non-realistic. So it has to be physically realistic, not to appear to the human eye. And that's very hard. We have all to work on data for perception. It's a huge gap. It's a headache. We'll need that. We need to cover that. And that's going to improve a lot in what we do in our systems.
Thank you. So next one. What is the proposed approach to ensure the system developed can generalize to any airports? Associated variety of runways, vehicles, obstacles, weather, others?
Excellent questions once again. So we do testing at other airports, but in those airports, first of all, busy commercial airports don't even want to talk to us to create incursions. I mean, it's a mess. But what we get, we have testing at those airports, but those cases are all of them actually clear runways. They clear. In SeaTac, Portland, we see complex situations. I sit a lot in the lounge, Delta Lounge at San Francisco. Crossing runways extremely complex. Just watch that and you realize how complex this task is. It is a big consideration. We know it. And I think synthetic data plus going and testing and then seeing and generalizing to those will be those. So yes, we are on that path at the very beginning. No claims for being able to do it. We were happy that in some airports we actually do. So we go and we test parallel. You saw we have parallel runways where we are. With crossing runways, it's going to be complex. And that's where ADSB will help a lot. Yes.
Okay, thank you. Then we take the last question, and then I'm afraid we have to stop as we are running really late. So will you conduct further study whether and by how much the automatic taxi system reduces the workload in comparison to a fully manual taxi operation?
Yes, yes, we do. We continue on that, and we'll continue partnering. We talk with both our regulators. There are even in, so yes, we admit that this will be an advisory system yet. It can be an advisory system in many ways. First of all, perception. Many of us have already cars that advise us what we see. There is one thing. Then there is alerting. Hey, there is a, and then one more thing that we haven't talked, we talked last year about localization. I strongly believe that providing an advisory or correction where you are, especially where you're lost. See the Milan Linate accident in 2001. One wrong turn in the fog led to an accident. So that's not about obstacles. It's about just an advisory, turn-by-turn advisory. So we look at all these. It's going to be gradual. You saw in the cars. First, you had just a display of, hey, there is something there, and then the alerting. But with the alerting, we are very conscious about having false positives. So we have to be very precise, and we can't afford to have alerting that has lots of false positives. So we look in all those directions, and then all of them will come together. So that's the thinking.
Okay, thank you very much, and thank you to the Boeing team for this presentation. I want to extend a thank you to the larger team because there were many more people involved than those that you see here. So great work. Yeah.
First of all, I will just make you a small and quick note of who are these beautiful people here around me. So I guess I will skip Emily because she just spoke. She's part of the Boeing team. And of course, you know her very well already now. So I have here also with me Carmen Bruder from DLR. Actually, she's an aviation psychologist at the German Aerospace Center, and she's there for more than 50 years doing research in human technology interaction with focus on human factors in aviation, of course. So user-centered design and of AI-based systems, collaborative work in control rooms, and eye tracking of attention processes, it's part of the fields that she studied. So it will be very interesting also to see from DLR what is the research results that you have. So on my left side, I have Lee Glazier from Rolls-Royce. So yeah, actually Lee created the civil aerospace digital governance system, helping digital project teams navigate an agile and compliant route through regulation, legislation, policy, safety, and ethics. So yeah, well, we created the Rolls-Royce framework for governing AI ethics and trustworthiness, collaborating with human resources, ethics, data scientists, manufacturing, and the trade unions, European Workers' Council. So lots of stakeholders, different views. We will speak about that for sure. And then also on my left, I have Denis Bernard from Airbus. Hello, Denis. Hello. So Airbus engineering, airspace engineering, I'm just doing, did a small fault. So Denis is coming from Airbus. He's in aerospace engineering. He holds a PhD in computer science and actually is in Airbus being an expert regarding AI for human system interaction. He also co-leads the SG8 group, so on human factors, of the WG114 on artificial intelligence in aviation. And last but not least, here on my right, I have Andrew Kilner. And Andrew, it's one of my colleagues, and already I think that you already know him, so I will skip this. He's basically working in the field of human factors over 30 years now, nah, Andy? It's a lot. Yes, so this is a quick shot. Yes. This was a quick shot. I will just close this bio notes saying that Francis Brasier is not here today. You can see her on the slide, but she had family trouble, and unfortunately she had to skip our panel. So we hope all the best for her and for her family. Good, so let's go for this topic. We'll try to see here different opinions, different practices, and we hope that at the end we'll have still a bit of time for your questions. So maybe, Guillaume, you can help us there a bit? Yeah? So, good. So, Emily, we just heard your team a bit before the coffee break, and I would love that maybe you could step in doing a bit of an overview of what Boeing is doing in terms of human factors and how do you see this? I know that you prepared a bit of a slide. Maybe we start with the video, right?
Please.
So, Guillaume, can you just go a bit into the slides? Another one, please. Another one, please. And let's go for the video. So, should be the second one. Yeah, video link. Exactly. If technology is not making weird things. Yeah, there we are.
Welcome. In this video, we will review the public policy recently released by the Human Factors and Ergonomics Society around responsible use of artificial intelligence. In recent years, we've seen a transition from human-operated devices and services to autonomous robotics and AI support features, such as robots that clean our floors, taxis with no drivers, and ChatGPT. Advances in AI have made it possible to synthesize realistic human speech, and even realistic human appearance, all generated from data samples using AI. In fact, I am an example of this. My face is that of a real person, animated using AI to provide the narration for this video. I can even change the language I speak at the click of a button. Je parle des centaines de langues, dont le français. Artificial intelligence has the potential to greatly enhance our lives, but it also has the potential to cause harm, which is why the Human Factors and Ergonomics Society has released a set of guardrails to help us navigate this new territory. Let's look at the first 4 guardrails for human use. Just like we might see with food, labeling is necessary. Consumers of products derived from AI need to be informed about the source so they can make personal decisions about reliability. Use of AI to alter facts or create false information, and not denoted as fiction, may be considered fraud by legal standards. AI recommendations may be laced with invisible biases, erroneously presented as fact. Those of us developing AI must work to expose and eliminate bias in the data. And if we can't eliminate it, we must tell consumers it is present and may impact AI's reliability. Developers using AI must fully understand and accept liability for their products. We must not blame errors on users and always hold developers accountable. This guardrail helps us promote accountability and responsible development of tools. Now let's review the remaining guardrails, highlighted as especially necessary for safety-critical applications of AI, such as healthcare, transportation, power systems, and military operations. AI must be capable of describing the rationale for outputs in an easy-to-understand way, so users can make informed decisions. Consumers of AI products need to know the status of the system and its condition of reliability to know what level of confidence to have in it. Realistic situations and representative users must be involved in testing AI efficacy, including validating its use in unusual but possible conditions, such as fatigue, low attention, high stress, and other factors. Critical systems must alert users when necessary for manual control or other overrides. Systems must be designed to revert to a safe state if they fail to perform properly. Safe fallback strategies should not require human operators to perform beyond human limitations. Users need to know about all AI system capabilities, behaviors, and limitations for proper and safe use. And finally, autonomous AI systems must demonstrate adequate performance in realistic conditions, including possible hazards that may impact operations. Artificial intelligence is changing our world every day. The safety and effectiveness of AI depends on following these guardrails for human interaction with AI. Get more information and read the AI Guardrails for Human Use in full at hfes.org. And thank you for watching.
Thank you. Guillaume, can you go back to the slides, please? Right. Good. So, Emily, I will pass the floor to you. What is actually the future expectation for these 3 AI level?
The future expectation for the 3 AI levels?
On human factors.
On
How do you see this?
Oh, level 3.
Well,
Well, if you go back to the previous slide, I took a quote from the National Academy of Sciences. You know, humans struggle to perform oversight of automation due to both cognitive limitations and inadequate design. So we have to start by saying this is hard. It's hard because humans are not particularly good, from the reasons I explained earlier, to, you know, if we're asking humans only to occasionally intervene to the very low workload producing non-normal events, there are high risks associated with that. We have to find ways to overcome that, and also pay attention to design. And we do know good human-centered design principles. We've learned from decades of poorly designed automation how to overcome these design limitations, but we have to apply them, and we have to engage and ensure that human readiness levels, the fit for human use, is considered early and often in the development process. Otherwise, we see risks. So one other plug for the video. I know the video was based on a paper that was published in October of 2023. So the content is not necessarily new, especially for the members of this audience. You all, I think, are familiar. But when you think about the millions of people, eventually billions of people who will have access to AI, I think a video like this can be very useful in just educating the average person on what are the pitfalls, how will AI be used to their benefit, but also possibly to their detriment. And so we made this video as a way to take this academic paper and make it more accessible. And just to show the power of what AI can do today, imagine what it will be capable of, in the future. The last thing I'll talk about is the idea of human readiness levels. I've mentioned this, but this is a new standard that was also generated by the Human Factors and Ergonomics Society, and it's designed to parallel the technology readiness level scale, and just to show in that risk matrix that when human readiness or human-centered design principles are applied along with technology development processes, you get good results. But if you let the technology move too far ahead, you move into the high and very high risk areas. And so the key is to make sure you are attending to human-centered design principles in concert with the development of your technology.
Very well, super. So, Carmen, can you talk a bit about the Loki project?
Yes, I will do. At first, I want to say that I like to starting on specifying the human side at first, setting the scene. Human oversight means to ensure meaningful human control where and when it is needed. That is written in the EU AI Act, and to prevent risks, not only safety risk, but also health and risk, and to prevent and fundamental right risks. And for this, it is necessary to clarify the requirements for human overseers, the human who do this job, with respect to roles, responsibilities, and the requirements for meaningful oversight. That is in addition to Emily, the same approach. So, and please, the second slide. And what is my domain where I'm coming from? That is, I'm a project leader and also member of the DLR project Loki. And Loki is about investigating guidelines for the collaboration between AI-based systems and human operators. Clear focus on human operators as end users. And we do much more than here on the slide, but to focus here, we have two applied use cases, ATC use cases. We have also a cockpit use case, but it's not focused here. And addressing investigating future use cases to be, on the one hand side, the collaboration between a human air traffic controller and the digital controller. We call him Dirk. And you see here the rough concept, but I go no deeper in. But we also, at the beginning of the project, we also assessed with air traffic controllers the expectations and requirements with respect to a more advanced, more future use case, that is a 3A use case, human overseeing the work of a digital controller called DICO. And you see here, there is, on one visually, you see there is something new. On the Loki 2B use case, you have a human in the loop, as both working collaboratively together. But now with this human overseeing aspect, there is not a real deep integration of both of them. There is an interface, and that is switch to the next slide, please. And there are a couple of terminology in the literature, and the one is called human in the loop, human HITL. That is a capability for active human intervention during overall the whole decision cycle. For operation, it means human can decide, intervene directly. When we go further on and transfer to human in command, that is what happens with 3A from my perspective. There is a capability to oversee the overall activity of the AI-based systems, not directly, indirectly. The human user is in the side. He has to oversee the overall activity and control activities, record activities. And so we need the requirements for all forms and phases to fully understand the capacities and limitations of our AI systems and be aware of possible biases, not only the biases of human side, that's really also very important, complacency, automation biases, primacy effect, familiarity bias, all these things, also the AI-based biases. So, and then switch to the next slide, and that is my main message. And when we are starting with investigating, the question is too huge and it's much more in the future, and we are and dealing with human oversights, what is the relevant research we found. And there is at first, I think, a very, very good framework from my perspective, which gives us a guidance to the humans' needs to effectively oversee high-risk AI-based systems. See below. That is work by Professor Langer and his colleagues. And that is, if human overseer have to oversee, have to work in such a 3A, under 3A conditions, he have to have epistemic access. That means he has the sufficient knowledge, expertise, and motivation, not only of the task and the AI-based system, also of the whole decision situation. That is the first condition. The second condition is he must have self-control. He must be able to not distracted by fatigue or other things. He must be in full control, that he can decide for any path of action and follow through. And that is really also very, very important. He must have the causal power, and that must correspond to the system he is responsible for, the power he gets. So we can set him in a situation where you have to monitor a complex situation and he can only switch the system out or not. So it corresponds not. So has power to establish sufficient and causal connection to the situation. And that, as he calls as moral responsibility. And for effectiveness in human oversight, they add a fourth condition, that is fitting intentions. Fitting intentions means the intentions of the human for their role, to fulfill their role. And there are a couple of factors influencing these four conditions, all well described. And there's also explainability is one of them, but there are also other ones. Some can addressed by system design, some addressed by training of the human or selecting the right persons and so on, but also by organizational and design and the society. So, and that is what I think could guide us a little bit to discuss all the important things.
Thank you for the insights, Carmen. For sure we'll have questions about it. Very good. So we will continue then. Next, please. Thanks. All right. So I hand over now to Lee. It will be interesting to see his practical cases from Rolls-Royce. So what messages do you want to convey?
Thank you. Hi there. First slide. Thank you. So I'm just going to talk through one slide. This content is pretty obvious, really. So if the actions are going to be overridable by the human, then the human must know that the AI system needs to be overridden. That's a blindingly obvious statement. So I'm going to talk about how we've developed our AI quality assurance frameworks to include methodology by which we will identify to the human for a 3A system that it needs to be overridden. So this is based on an AI research project that we've been running for around about 6 years now. It's a 3A project looking at fully automated inspection of a component. As I say, it's been running for about 6 years, and everything I've created in the quality assurance governance of AI has been based on that project. So the project, we've treated it as safety critical. It's not a safety critical component, but we've treated it as safety critical to develop all of our governance processes. And there are 6 frameworks within that quality assurance process, one of which is the ethics framework, which some of you may have heard of, the Alethea framework from Rolls-Royce. That's our ethics framework. And yes, I did sit down with our union, trade unions and our workers' councils to develop that, as well as other stakeholders as well. And that was released publicly about 5 years ago now, almost. So we've been on this journey for quite some time. And in there are 5 functions that we monitor to identify whether there's been a malfunction within the AI system. And those monitors look at data going in, the system itself, what comes out of the system. And the idea is there that we're monitoring these 5, and you can monitor every minute, every 10 minutes, whatever you want, whatever's appropriate. So those monitors are in there. And I like to use the term, we know the term human in the loop, we just heard it mentioned, human on the loop. I like to use the term human near the loop. So this isn't a person just sat there watching a system, waiting for an alarm to tell them to override. The system itself will flag up that there is something that has caused, appears to be a malfunction, and then a human can have a look at that. And we're used to doing this. If you walk into our office is where the data is coming off the Rolls-Royce engines that are in the sky now. So on average, there are 3,000 Rolls-Royce engines in the air supporting 250,000 people on average. And all of that data comes into our office. And if any of those systems start to slow down, the data starts to slow down, then a big red light comes on the screen that's on the wall in the office. So our teams are used to that sort of monitoring. Big red lights go on. But they're not looking at something waiting for the red light to come on. It comes on. So that the human factor side is very well controlled on that. And as it says there, it's these 5 monitors. We're really lucky in Rolls-Royce. We've got a safety critical software system, no AI, that has been certified by EASA. And in there are these 5 monitors. And I took that safety critical software system through our safety board. And then I was asked, what could we do for AI? And I just thought, wow, we could actually just lift from a safety critical software system these 5 monitors and put them on an AI system. And that's what we've done. And we've proceduralized that for any safety context AI. And as it says there, if you do override, then there's got to be a safe fallback for the system to carry on running. So that's absolutely important. We heard it mentioned by Boeing, the systems engineering approach. How many times did we hear that from Boeing? And our whole quality assurance frameworks have a systems engineering approach. We look at the whole system, not just the AI in it, but all of the systems interactions to make sure that they're covered by the quality assurance process as well. Even for level 3B, exactly the same. So if it's not going to be a human that overrides, but it's going to be the AI that overrides, if there's a malfunction, then the AI needs to be able to detect that there's been a malfunction. And we use exactly the same 5 principles, 5 functions that we monitor on a level 3B system, exactly the same. So fully autonomous 3B, and you have to have a safe fallback as well. So all of those, I think those things are obvious. As with AI, the difficulty is always the implementation and the productionization of these systems. But those 5 principles that we were able to take from a safety critical software system is basically how we've done that.
Okay. Thank you. I will bet that you have lots of questions for sure. All right. Then we continue with Denise. So I was wondering what the working group is doing in terms of level 3 systems. And is there a difference between one level and the other?
You will be a bit disappointed because the group is not working for the moment on level 3 AI system. But the good news is that probably the method used in subgroup 8 for the assessment of the need for new regulation could be applied also for level 3 system. But just for those who don't know the subgroup 8 of Working Group 114, subgroup 8 has been created in order to assess whether new guidance related to human factors is introduced by the deployment of AI system. And presently, the subgroup is engaged in a diagnostic phase where, based on some use cases, we try to understand whether the existing standards and guidelines, including the concept paper from EASA, are sufficient or not to detect and mitigate or prevent classical human factor concerns. So to do that, we are using the following methods. We are starting from a list of human factor concerns. In front of that, we have a list of use cases. And for each use case, we wonder whether we use the list of concern as a checklist. And we wonder whether each concern will appear or not on the use case. And if it is the case, if we are confident that the use case, the concern will be prevented or mitigated adequately with existing standards and guidelines. So for the moment, we are finalizing this diagnostic document, but for the moment, only on 1B, 2A, and 2B use cases. Nevertheless, the list of human factor concerns that we are developing can be used also as a checklist to assess level 3 systems. So for those who are not aware of what we are doing there, the concerns fall into basically 5 categories. First one is human performance, vigilance, workload, all what is related, correlated to the state of the human, depending on the interaction with the system. So second family of concerns is about system interaction itself. So the communication between the system and the human, and the interaction must serve the concept of work, which is our third family. In the concept of work, we will assess in particular if there are concerns related either the cooperation for level 2A system or human system collaboration for level 2B. And then we have other 2 families of concerns, which are a bit higher level. Operations and mission, which is about is there any concern regarding the correct performance of the operation and to take into account the context of the operation. And a higher level is about organization. And here we talk mainly about training needs that may result from the introduction of AI system. So as I said today, we are not covering 3A system, but we can anticipate that what could be in which families of concern we will have more issues related to 3A system. So first, we anticipate that there will not be, at least in the short term, purely AI system at level 3A. We anticipate that most probably there will be hybrid architecture. So this analysis has to be done much more at the system level than really at the level of machine learning component. Nevertheless, it is still applicable. So whereas for level 2 systems, the main concerns we have found are mainly in the family of interaction with the system, in particular when we are using natural language, and the impact of this interaction on the concept of work, which are the core business, I would say, of levels 2A and 2B. Here we can anticipate that the problems that we may have to think about are much more at the level of human cognitive performances. Because the key point of level 3 systems is the cognitive capability of the pilot to detect system failures and to take over from the system. So to summarize that, we think that the system, to summarize that in terms of qualities of the system, we anticipate that this kind of system must remain interpretable and predictable, even if they are an additional step toward automation. And in fact, we will find with the system the classical human factor problem that we find when we increase the level of automation. It's how far the pilot will be able to take over, and but we have also another kind of problem, which is in the normal life of the system, that we anticipate, and maybe it's subject to reflection, but we anticipate that the concept of operation of level 3A system will not be strictly applicable. We anticipate that pilot will have the need to somehow monitor what the system is doing, even if they are not forced to do so. We anticipate that pilot will have to sometimes confirm the level of reliance they put on the system. And then that leads us to consider the importance of explainability for such system. And explainability here will have to satisfy diverse cognitive needs. When it is in case of alert, we will have to ensure that we should grasp the attention of the pilot, to update the situation awareness of the pilot so that he is able to decide and to act. And in normal life, the cognitive needs that we will have to take care of are about understanding what the system is doing and why it is doing that. We can summarize that in terms of justification of what the system is doing in order to either confirm or adjust the level of reliance that the pilot puts into the system. And very important point, if the system wants if the pilot wants sometimes to monitor the system must remain predictable. Because this is how pilot monitor a system. They expect something from the system, and then they see whether the system is acting in conformance with their expectations or not. So this is what we can anticipate about what the cognitive needs that will have to be filled by explainability in level 3A system. And I will finish by a last point, which is much more related to an implementation choice for those level 3A system. So we understand that explainability is very important, and we may have the temptation to implement explainability through conversational systems. And this will blur a bit more the frontier between level 2 system and level 3 system. We can anticipate that we will inherit all the requirements related to natural language and conversation that we apply today on 2A and 2B systems. So this is what we can say about level 3A system from the perspective of subgroup 8.
Yeah, okay. This is very interesting because one of the questions of yesterday, if you remember, was linked to the cognitive skills or ability. Yeah, how could we foresee that in the level 3 AI, this would actually impact cognitively the humans? So good to have this input, Denis. Let's see how it develops further. Yeah, great. Thank you for that. So, and then we'll continue. Guillaume, if you don't mind. Yes. Yes. So I will give the floor to Andy. So, dear colleague, how is the agency saying things about this oversight topics?
Yeah. So I get the chance today. I represent myself and not Renee. So that's quite unusual. So we go to the next slide, Guillaume. So what I'm going to do is present to you kind of the proposal that we're putting in the next version of the concept paper. which is a proposed view of what a level 3 AI system could be or could look like. So what I'm saying here is our straw man. We're happy to take comment on it. We're happy to take discussion on it, and that's kind of part of the session today is to launch this and get a little bit of initial feedback as well. So within level 3A, what we're thinking about is kind of safeguarded advanced automation. Again, Guillaume made the point a little while ago about autonomy. We're not talking about autonomy. We're still talking about advanced automation, and we're talking about the introduction or the use of AI to kind of enable this advanced automation. It's still overridable, and we still have kind of full authority. What does that mean? Well, full authority is available because if the system alerts the end user, then that's when the end user can take authority for the system. So authority upon alerting. And we've heard a lot of people say, well, when does alerting take place? You have to have alerting if you want the end user to intervene. And will the end user be able to intervene? And we say, well, there's no point having alerting in the design of your system if you're going to alert it so that it's too late, or it's not in a timely manner, it's not in a way that we can do. So realistically, if we're going to have alerting in order to delegate a case to an operator, it has to be one that can be taken on board and used. So in this case, this is why we justified that there's no active monitoring. So no active monitoring, yes, we're going to have somebody in the loop. They're going to be competent and capable and checked out and type rated or whatever you want to call it. But largely, they may be monitoring multiple systems. They might be doing other jobs. So monitoring is going to be limited. It's going to be restricted. And so the quality of that alert has to be sufficient that it enables the operator to stand in and also to know that what's going on, that they were actually obliged to intervene. That's not to say that the operator has to intervene. It's to say that they have the ability to. So if they're presented with a system status and it's just the AI has kind of got an understanding that it's getting towards the edge of its preferred operating envelope, then it may early flag up an end user, and the end user comes to look at it and say, well, actually, no, everything looks fine there. So we're kind of building up this concept of an intervention-only approach. If we're going to have an intervention-only approach, then that means that this knowledge, this situational representation, we don't call it situational awareness if we're talking about computer-based systems, the representation of the situation has to reside within the machine. And what we're asking then is if the system has that situational representation, it has to be able to share the important elements of that upon alerting, but it has to be able to communicate. We're not making any great claims about what that communication should be. It's up to the individual operational deployment scenario to determine what the most appropriate means and methods are. But as well as it says here communicates when requested, that would suggest that the level 3 AI can only communicate when it's requested. No, it will communicate when requested. So if the operator wants information out of it, he can do. But as well, the 3A system should communicate effectively and openly with the end user when it's required. And ultimately, what we're looking for is the AI system to achieve the goals that are shared between the operator and the system. What does that mean? Well, sharing within an operational environment, if you want to land an aircraft, the goal is to land the aircraft. There shouldn't be an additional goal that's brought in either by the end user or the system. So in each stage of an operation, there's a set of goals. And if you talk to human factors people who've been doing task analysis for years and years and years, and now Emily's made it even bigger and better with STPA, you'll be expressing the goals when you establish the requirements for your system. So what you're wanting is that your system delivers the goals that we're expecting to see. So again, just to kind of reinforce, we're not talking about autonomy, we're talking about a set of goals that the system will develop within an automated system. We're compliant with the EU AI Act, and it's been developed, or this approach has been kind of done very much with that in mind. And again, this approach, I'll talk a little bit more about an architecture in the next slide, has also been kind of reinforced as well by our scientific committee. And it's a shame that Frances not here because she's a very vocal member of that and spends a lot of time challenging us. So it's quite entertaining. So again, I think that's enough on this slide. If we progress to the next one. So this kind of just gives, again, an overview of what we're expecting some kind of architecture or model to be. And you'll all be drawn immediately to this red box that says operational oversight system. This is the concept that an AI system is going to be doing the maths, it's going to be running itself, it's going to be doing operational interventions and running a system. But how does it know that it's getting near the limits of its model capabilities? How does it know that it should be bringing in some degree of help or support? And this is where this concept of an operational oversight system, and again, it's a system might be a person, it could be a computer, it could be another AI agent. We're not making any claims on that. But the idea is that this system will be the thing that monitors operational performance, and it will start when necessary to alert the user. So if you're in en route airspace and you're working over the ocean, for example, you've got minutes to decide how to take action on something. If you're in a highly charged TMA environment and you're doing air traffic control, you've got seconds. So the operational oversight system has to have an understanding of the operation. It's not just a generic thing that's created. And again, this comes back to what Francois was laboring yesterday about this concept of an ODD. You have to know what your operation is. You have to know where you're deploying. So we have now we have a system that's monitoring the AI-based system and can alert the operator. The operator will necessarily have partial situational awareness, not full situational awareness. And again, the timeliness of the intervention of the operator has to be based on the ability of the oversight system with the AI system to say, we're at the edge of the performance envelope. That's going to give us then the operator has a chance to kind of intervene and take control and manipulate the system that we want to see the positive outcomes. So when we're looking at this kind of the stuff that's feeding into the operational oversight system are all of those things that are listed on the right. They're the typical things that you'd expect the pilot to be attending to or the air traffic controller to be attending to when they're managing and operating the system. So that's it. I don't want to say a great deal more because it all gets a little bit tangled up, but realistically, that's our overview of what we're proposing as the EASA for a level 3A system. And we're going to continue to develop kind of the objectives and the AMC, the guidance material that will surround that. And we're in a position where we're prepared to kind of accept input as well and take guidance. Thank you.
Thank you. Lovely. All right. Thank you all. Lots of nice, good inputs. And let's jump into the Slido because I bet that you have some questions. Let's try to confirm it. And of course, we are open for your questions also in the room. Yes. Good. So let's start. So level 3A already exists under traditional means software. So there are many aircraft functions. The question is, what are the new uncertainties and risks with ML? Who wants to take this one? This is not a question, Gary. It's a comment. And we welcome, of course, the comment. And from the panel, somebody wants to reinforce or to give a bit back information to Gary?
I can kick off, and then I'm sure someone else will jump in. I think you're right. I think many systems, anybody that's sat in a super new cockpit can look at highly automated systems, and really the pilots are now system monitors and system controllers. That's automation, and automation does align very highly at the top ends with what we're trying to achieve in terms of AI. But a highly automated system doesn't contain AI necessarily. AI is AI and automation is automation, and AI can be an enabler of automation. What we're trying to do is establish what those new risks are. And that's just kind of the purpose of one of these forums. It's the purpose of the research projects that we're running and so on. So machine learning is part of it, but the interpretation of what's going on with machine learning and its interpretation is the second part of it. And that's what we want to do.
Okay, I think I will ask also Lee and Denis to say something about it.
No. I've just 6 weeks ago, probably now, very recently wrote the Rolls-Royce AI product safety policy, fully aligned and intended to be aligned with some of the imminent new requirements that are going to come out from EASA, hopefully in the third issue of guidance. And working with our AI scientists and engineers, it was really fascinating. This is a really provocative statement. If you are introducing AI into a product and you're introducing AI into a route that isn't a route to hazard, then we don't believe you could turn that into a potential route to hazard. So that was a really interesting light bulb moment. What we realized is that the thing that changes is not the impact, it's the likelihood. So you're just really looking at probabilities. So AI hopefully makes things safer in terms of probability and likelihoods, but it won't actually change it from being non-hazardous into hazardous. Now, that's a provocative statement, and if anybody can give me an example, because we couldn't find one, so we actually believe that that is a true statement. So it's all around probability, and therefore you're not going to change it from non-hazardous into a hazardous unless hazard is based on probability, which it can be, I understand that as well, but it is a probability impact.
Thank you, Lee. So let's continue with the questions. So the following is from Gabriel. Is there an approach to analyze both human plus AI errors? Will human error notion evolve to consider human errors induced by complex AI errors hardly to detect? Who wants to reply to this one? Maybe Emily, maybe can jump in. What would you say?
Thank you. I mean, the first thing that comes to mind is this is where STPA has some advantages over other analysis methodologies in that you can take very complex systems, and we all agree AI is incredibly complex, and model it in a way that sort of helps you manage the complexity through hierarchy and abstraction, as well as showing the relationship between the software and hardware components of your system and the human in a very tightly coupled series of control loops. And so, that's kind of its superpower of this methodology, is to allow you to look at these very novel, untested, unknown system possible behaviors. Again, using experts, your analysis is only as good as the experts who perform the analysis, and STPA doesn't have any advantage over any other method. However, it exposes the complexities and those complex interactions in ways that's much more systematic and easier to follow. Trying to make sure I entered. So, will human error notion evolve to consider human errors induced by complex AI is hardly to detect? I mean, yeah, I think we are changing our understanding of human error and our whole approach to blaming the human, as opposed to maybe it's the design of the system that induced the error, as opposed to the human was bad, the human failed, so those are some of the other changes that we're seeing in our analysis methods, is to really look at the context. And again, STPA is one approach, but the idea is, why would it make sense for someone to make the response that they did? And when we look at the system context, you often find much more insight than to just stop at human error as a cause of a problem and more of a symptom of a bad design. So I think we can continue that path in the world of AI. I think we have to, because AI will start to behave in ways that we can't yet anticipate, and we have to use methods to try to put some structure around that.
Thank you. Next one is for you, Carmen. How do you suggest to manage the balance between overtrust and no trust at all? There are both safety critical scenarios when it comes to HAT systems.
Thank you very much for this question, because I leave all the things out, how we do things. So I can explain something. What we do is we have a user-centered design approach. Both we have workshops every year with the air traffic controllers in each step of the design process, not only on the interface design and task, but also on what they expect from the conditions to introduce the system, what they need for training. And that's what we also did in the last workshop, was to ask the controller, after showing them our prototype, they're interacting with the prototype, and we asked them what they need to know to calibrate their trust adequately. And we inform them what is calibrated trust, and that trust in the system depends of the situation, and the system reacts differently in different situations, and so on. And that was very and highly helpful for us. They gave us, because they are all very domain experts and also involved in many development projects, and they gave us so many advice. What they need when introducing the system with respect to training, but also to operational design, system design, to calibrate the trust adequately. And so that is really a big issue. And we have also a validation campaign at the end of the year with ADCOs, in 2 days, different scenarios. And so after this validation campaign, we talk as well about what they need for introduction. And then in the follow-up project, we will focus on these topics, how to introduce such systems, what is needed from the organizational perspective, but also from the training aspects. So that is what I can answer to this.
Thank you, Carmen. So I will invite Nasdaq and Guillaume to reply to the next question. So are EASA and FAA sharing harmonized views regarding requirements for human factors in AI/ML? Please.
Yes, that's that's one question for me and Nasdaq indeed. No, of course, as Nasdaq explained yesterday in his presentation, we're working on it. So this is a different topic. It has human factors touch on it. So definitely it's not the same expertise involved as the people we are engaged for AI assurance. So the path is open. We are connected and we are discussing, and we'll strive to harmonize, of course. That's where I think two elements very important from EASA perspective. The levels of AI, again, it's one scheme, one thinking. It doesn't have to be forever there, but at least it helps us putting things in boxes. Sometimes they are a bit blurry, in particular within a box like 2A, 2B, we can, of course, discuss a lot, but it helps really seeing use cases coming. And with each use case, we can say, are we missing a box, or can we really fit this? And that will help harmonization for sure. And the second element is what I was saying on my presentation on day number 1. We shouldn't distinguish too quickly AI enabler from the automation aspect. Doesn't mean it's the same, but just it's extremely interconnected when we think levels of AI. Clearly, it's system level thinking. It's even operation level thinking. When you classify a level, it's not like traditional classification we would do for classical software of what is automation. We have really an umbrella picture above that with this scheme. So I think it can help. I don't know, Nasdaq, if you want to
Nasdaq, please.
Say anything.
Yes.
The only thing I would add is, because I know Kathy Abbott would be mad at me if I don't identify this. So yeah, we are separating human factors, and I think from the factor of personification, as I highlighted yesterday, that's the big key element that Kathy Abbott is really honing in on. Let's make sure we don't start personifying AI in all these different levels. Let's make sure the human element really understands that it's not a fully intelligent being.
Thank you very much.
Thank you. So I will take another question, and I think I will ask Denis to reply, and I will go for Fatih's question. So to overwrite the output of a 3A system, for example, clearance, the operator needs operation contexts with the alarm. How identifying the set of info needed to overwrite safely?
So it's a bit difficult to give a generic answer to that because obviously it may be very case by depending on the case that we are considering. What is sure that the user needs not only to understand why the system is not able to manage the situation alone, but also to have all the input in particular about the situation to decide what to do next. So we are really in a decision-making scenario. The good news is that, as it is already specified in the concept paper, the work on explainability must start by a need analysis. What are the cognitive needs of the users at each step of the operation? And the set of information is one of the outputs of this analysis.
Okay, so, well, we could continue for sure, but we have to stop. I thank you dearly to all of my panel members, and I hand over to you, Janet.
Thank you very much to all the panel for that. We're now going to move on and hear the story of a second IPC. So for this, I'd like to welcome from Lufthansa, we have Martin Recklin, Marcel Bauer, and Ursula Samatulska. Thank you.
Yes, well, you can, as you prefer. Really, as you prefer. You have nameplates and seats, but if you want to be standing, it's up to you. Yeah. Okay, thank you.
Yes, yeah, no worries. Sorry for that.
No worries. So that you can.
So present from there or from the next one?
Yes.
Steht. Okay, we stand. We stand, we sit.
You can go sequentially.
Yeah. Okay. Oh, wait, agile. All right. Okay, thank you. No worries. No worries. Hi, everyone. You can hear me well, right? No? No, I need to turn it on? No, yeah. Flexible. Thank you. It's still growing. Okay, perfect. All right, thank you so much. Hi, everyone. No, still, maybe like this. Perfect. All right, so hi, everyone. Thank you for having us. My name is Ursula Samatulska. I am the Senior Director for Innovation and Regulation within the Lufthansa Group. And together with my colleagues who are currently sitting but will be standing when we talk, together with Martin Rickling, who is Senior Manager for Digitalization and Application Strategy, as well as Marcel Bauer, who is our expert on regulation and authority liaison, both within Lufthansa Group. We like to talk to you about our IPC we have with EASA and the use case of Gen AI, and tell you a little bit about what has been going on that, and discuss with you and see what questions you have. All right. So, yeah, that's us. All right. So to give you a little bit of a backstory, of an insight, Lufthansa Group. So we are a global multinational corporation with various companies. There are, of course, our airlines, Lufthansa Airlines, Swiss, Austrian, Brussels, Eurowings, our regional airlines like City Airlines and Air Dolomiti. But of course, we also have other companies, our MRO company, Lufthansa Technik, Lufthansa Systems, so various cooperation. And we really do believe in the value of working cross-functional, cross business units and coming together and cooperating. And we do that in various ways, in various functions. And one of the functions we do that in is in technical operations, and especially within the airlines. And together with also our Lufthansa Technik company, we have formed a technical fleet management. In that technical fleet management, we come together to cooperate and work jointly on technical operations topics. And from like an airline group perspective, why is AI important to us? First of all, at the end of the day, it's always about safety, right? Safety is and remains at all times our #1 priority, and that's untouchable. So for us, looking at innovation and looking at what AI has to offer, it's about how can we find new layers and new chances to enhance what we already have and make it even better. So it's really about finding new ways. How can we make processes more efficient? How can we enhance existing standards? And how can we create supporting layers and make processes leaner? And there was a lot of information within the last days, within yesterday and today. So, looking at the different levels and really looking at possible scenarios and use cases for technical operations of airlines. And those are just pictures, example pictures, but there is endless possibilities, whether you just look at how can I make information more accessible for a mechanic? And by doing that, how can I bring things up to speed and support eliminating human errors? Or how can I support documentation, planning, analysis? How can I support by having extra layers in terms of loops that run constantly and support prediction, prevention? So I think there are so many layers, and especially for us, having Lufthansa Group as a whole and the different airlines, there is various potentials. Also for us and me and my role, it's so important to come together and do not, only collaborate internally, but also talk to the industry, come together with you, and especially with the regulators, because at the end of the day, I opened it, and that's, I think, the most important part of it. It is about safety, and it's about jointly creating and jointly collaborating and putting input to a regulation, whether it's, now softer, but to a regulation that's at the end of the day is safe, is trustworthy, but is there to, support the industry, support us as companies, and really understand our needs. So that is definitely something we as Lufthansa Group really value and appreciate. EASA and the other regulators being that collaborative and being that agile and really wanting to see, what's out there, what's going on in the industry, what are their everyday struggles, what is the struggle of a mechanic who's, who needs to quickly know what to do in terms of troubleshooting, in terms of tasks that he needs to perform. So one way of doing that, and that's why we're really glad we can present it today, is through our innovative partnership contract we have with EASA. And we have that specifically for the use case of generative AI. And I will not jump into many details because I know Martin is eager to do so. But the idea is that through guidance, through equality gate, through support from the regulators, from EASA, we are challenged. We are able to present, our needs, our use case, but we are also challenged from a regulator perspective with your with your experience, your technical experience, with your guidance, and by doing so, we are able to jointly create better, right? So it's always mutual. I think it helps the regulators, it helps you as EASA to understand the pains and the needs, and also it challenges us in a way where we know more about what's possible now, how can we, support regulation development, but also what are the risks and what are the limits. And at the end of the day, by doing so, we jointly create safe and trustworthy regulation. And with that being said, I know you're all eager to find out more, so I think Martin will tell you a little bit more. Thank you.
So yeah, let's dive into technical operations and what we do in AI with our domain. I'd like to give you a short overview of how we try or how we innovate through practical use cases in the field of airline technical operations. Oh, yeah. Thanks. Oh, that's better. Our goal is very clear, drive innovation through practical use cases while uphold safety and the regulations and gain experience. And gaining experience, especially with new technologies, is very important because we all are new with this technology, and our, let's say, technical staff, very experienced, highly skilled, needs to gain experience how to deal with it in the future. And because this is new, we started early with this endeavor. So one of the, let's say, first use case, and I will also come into that a little bit in a minute, is an AI-assisted troubleshooting with GenAI, and which supports the experts in diagnosing and solving fault effectively. The second one is, you have heard of that as well, and it's pretty common also in other industry, predictive maintenance and condition-based maintenance, where we try to predict faults, where we try to, let's say, move a little bit more away from a fixed interval scheduled maintenance in a more on-condition-based maintenance, where this is also possible physically, of course. And then as a third, intelligent optimization of work packages. So you can imagine there's a lot of planning going around maintenance. Parts needs to be at the right place. The aircraft needs to be at the right place. And the packaging of all this work package is quite extensive. This we see especially also AI as an enabler to optimize those workloads, especially for planning. And then the last one, but not least, the typical one is the topic of digital twins and simulation technologies. So since we have, let's say, a lot of data gained during technical or flight operations, since we know a lot of the aircraft itself, how it behaves on a daily operation, there is the opportunity also to kind of mimic and reproduce a digital twin out of it. And rather than to test it in a real environment, we can test issues and anticipate faults on a digital twin rather than directly to a live environment. So now I will go a little bit deeper in our use case for aircraft troubleshooting. And first, let me set the scene. So imagine you are sitting here in a typical airline maintenance operations room. The team is monitoring a lot of displays, dozens of displays, and it seems like the more displays and screens, the better. What they do is looking at each of them and monitoring flight operation and monitoring aircraft systems almost in real time. But suddenly an aircraft fault occurs while an aircraft is coming in, hopefully at its destination where maintenance is available, and the parts which needs to be replaced or to be troubleshooted is available. And in order to avoid cancellation and minimize delays, the fault needs to be resolved quickly. Some cases are simple, you know exactly what to do, and other cases are quite complex. And therefore we have, let's say, a lot of experts gained years of experience knowing the aircraft by heart, knowing the fault by heart, and knowing also the documentation and manuals where to look very quickly. Especially, let's say, a younger expert doesn't have that experience, and experience really matters in this case. And also when we look at the future, especially in our field, it's not clear and not, let's say, natural that we have that experience just around the corner. So typically what an expert has to do, it has to identify the fault, it has to confirm the fault, get an overview of the situation before starting then the troubleshooting. And with the troubleshooting, the expert is consulting various tools, analytics tools, is looking into the manuals, into the procedures. He does this, or she does this, his due diligence in order to define the rectification or the corrective actions. This all takes time, and based also on my own personal experience as an aircraft system engineer and as a maintenance technician, getting together all the information is not always easy. And in order then to get the aircraft then back ready for the operation. On one hand, we tend to do then this kind of trial and error approach where we replace parts or initiate investigation maybe which is not really needed, and with, let's say, proper or more targeted troubleshooting, we can avoid this. So now imagine if you would have kind of a Gen AI assistant on your side. Instead of manually searching through different databases, the AI performs a smart search into the various tools we have available in our internal company database. This brings the most relevant information together in order to support the experts and to make a better, more informed decision making. So this Gen AI assistant is already in place. We are testing it heavily across the group and with our key users, and the feedback so far is quite positive. Again, as well, it's about expectation management as well. So how do the experts work with such systems? How do we interact with the data? So it's going into a conversation with the data, which for all of us still is quite unusual. And we are all starting also privately using ChatGPT to get answers for our daily problems. So we recognize this very early, and the fact that young engineers or young technicians in the future might use their cell phone and ask ChatGPT directly, we rather said we want to provide this in a secure environment. We want to explore this technology and provide reliable information, secured information within our controlled environment. So how do we do that? So at the beginning, when this all was new, we had kind of a choice to make. Rather, we train a large language model by ourselves. So we just put all the data into it and train it. But this would need a lot of, let's say, computational power and financial power, which we don't have, and is then also even not sure enough. So the approach we choose is this kind of retrieval augmented generation architecture, which aims to, as this means that a large language model here in the middle doesn't just invent answers from its own training data. Instead, it retrieves the most relevant company content or information first, and then formulates a comprehensive response based on the documents or content it has been provided or it has retrieved. The key here also is not to replicate any, let's say, procedures one by one, or any, let's say, engineering expertise in one extended answer. It's more about giving a short overview of what the information, what of existing information is available, and to give a first shot for the technician or the expert to then continue further on. With this framework, let's say the RAG architecture, we can significantly reduce hallucination reduce hallucinations. But because an LLM is still very probabilistic, the question remains, how can the end user trust the AI, and how is it safe? So how can we ensure that any hallucination or any made-up content is still in there, and it's only based on factual basis? So what we have had is we started also collaboration with a research master student, a brilliant mind, who was looking into measures, how we can ensure more, let's say, boundaries and layers into a factual check of the generated response by the AI. So one concept is the source check. So with every response we generate out of this RAG system, we also provide responses. We also provide the source. However, the source needs to be verified as well. So we have a huge database, feed it with a lot of information, and how can we be sure that the source is correct? Therefore, we have implemented a source check as well in order to see if that really matches if the source really matches the document in our database. A second concept, which we are also developing for our next phase, is a so-called verification agent, and going more into a modular architecture with the technology involved here in this field as well. So agentic AI word is just a buzzword. We are thinking about the concept of a verifying agent, which is contextually checks the generated response of the AI on its content based with the source which is available in the database. So if something doesn't match, it would flag or give the end user an indication that if that is something is wrong, or even is capable of reformulating or assisting the end user in reformulating its prompt so that the user gets a better response. So not only this one improves the, let's say, reliability of RAG system, but also building confidence to the end user how to use this tool. And confidence and trust is something which is a key element, especially for very skilled and highly skilled experts, which do not trust or challenge the chatbot very, very extensively. And therefore, these kinds of, let's say, measures or transparency measures is very important in regards also to the change management for this technology. I would like to hand over the words to my colleague Marcel, the expert regarding regulations and the whole concept paperwork we did within our IPC collaboration with EASA.
So thank you, Martin, for the great insights, also on the technical view. Yeah, let's have a look now at our approach from the concept to compliance, also hand in hand with the EASA team, Guillaume and the other colleagues. At the first step, we defined the concept of operations, including the identification of the high-level tasks, as well as the definition of the OD, the operational domain, including with a focus on the human in the loop, as per concept paper issue 2. As we already talked about, the airline tech ops, it typically includes 3 main parts. So there's on the one side the line maintenance, the part 145 organizations, and on the other hand the troubleshooting support, which can be either part 145 or part of the KMO. And the third step is the systems engineering, who deals with deep knowledge and so on. So what are the goals for the 3 parts? For the line maintenance, it's master complexity within the clear boundaries. So our controlled environment with all the documentation and the approved data and so on. For the troubleshooting, With its technical case management, we aim to reduce delays and avoid cancellations to be ready for the ops. And last but not least, for the systems engineering, we want to improve the knowledge management and the experience sharing. So important for all three cases is that the AI supports the technicians, not to replace them. In all cases, the human makes the final judgment. So the second step was then the AI classification as per concept paper. We determined the level 1B through our workshops with EASA for our use case. As you already know, 1B is the human assistance, the automation support to decision making. That means data analysis and information summary. The decision making suggestion to support the final judgment. Human is always in the loop, and the responsibility ultimately rests with the end user, with the human. So, and the third step was then the operational risk evaluation, so the risk assessment. It's the important part of the change management process, and it was therefore very important to identify the threats using this application, assess the hazards, and develop suitable mitigations to ensure that the specifications and the concept paper guidelines are met. So where are we now? Where are we today? So obviously, as we heard, there's no AMC or guidance material for the application of Gen AI in approved organizations like 145 or KMOS. And that's why with this IPC, we are co-developing safe pathways to trustworthy AI adoption. What was our approach then? So we were mapping the trustworthy AI building blocks and the classification of our Gen AI use case to level 1B. The main challenges were the assessment outcome, focusing on the definition of the OD and the ODD boundaries for our use case, as well as the operational explainability and the adaptation of the concept paper for Gen AI applications in general. These and more identified challenges are used to develop new guidance. So, and what about the future challenges? So it's very important that we build AI competences across all aviation stakeholders and establish practical validation frameworks for AI-based operational tools within these approved organizations like 145 and KMOS. And last but not least, also clarify the responsibility and defining a common organizational approach to help the organization implementing these systems. And that's what we also have learned from yesterday. These organizational approaches will find its way to the soft law approach and guide to the next regulations. And having said that, thank you very much also for the EASA team for the cooperation, and thanks for your attention.
Thanks, Marcel and the team for the great presentation. It's, as you said, another innovation partnership contract. So you see different types of subjects and topics, but also different level of advancement. We are nearly closing the Boeing IPC, whereas we are fully engaged in the one with you on Lufthansa Group. So everything you presented is also perspective for probably next EASA AI days with even results of all our considerations. So we can open the Q&A session. Let me put the Slido on the screen. Yeah, that should be working. Yeah, I will help you moderate it from here, and let me turn for the participants online, the panel view. Exactly, perfect. Okay, so if we go in the order of popularity of the questions, let's start with this one. How did you manage the hallucinations, especially for the source retrieval and the verification agent? Using LLM as a judge always results on leftover errors.
So yeah, this was basically one of the main scope of our master thesis, how to, let's say, reduce hallucinations and how to deal or how to measure the retrievals. What we also have built in is an active feedback loop for the users themselves, so they can or they have to rate the feedbacks or the generated answers. They have to feedback them, and this feedback goes then back into the system. And with that, we also then continuously improving the generation of that response in the backend.
Thank you, Martin. The next question is on the kind of data and LLM that you used in the troubleshooting system. Real historic data, question mark, generated, question mark, technical data scenarios, question mark also. Several questions.
Yeah. So yes, of course, we use our own maintenance data to support the troubleshooting. As if, let's say, a technician has to anyway or would look into the system for historical data, GenAI therefore is very, let's say, good into finding relevant or similar issues there to provide a historical overview. Generated, no, I would not say that we just generate any kind of synthetic data in order to support the knowledge database there. So this is typically not the case. And technical data scenarios, so we also rely on our own, let's say, engineering databases, which we have access to. That's years of experience noted and stored and accessible. And the point is really making that accessible for all, let's say, technicians and experts within the group.
Thanks, Martin. Okay, moving into another question. Is your AI model ChatGPT or similar, but firewalled from Lufthansa retrieved documents / internal database?
Yes, exactly. I knew that question would come up. Of course, our system is purely, let's say, in a secure environment from an IT perspective. So we are not accessing any public domain. We do use ChatGPT models, which we can use internally, and we started there, with different types of models which are available.
Thank you again. Okay, regarding now the trustworthiness assessment and the classification on 1B, did you perform the end-to-end assessment? If yes, can you please share the outcomes?
This is something I can hand over to Marcel.
For you, Marcel.
So during the workshops, we based on the concept paper and the guidelines and so on, and it was part of the assessment, the end-to-end. So insights, next time.
more to come. So we do a bit of incentive for next edition. Okay, let me accept the next questions. Okay, turning to another one. Is there any KPI increase such as quality, lead time, workforce than applied LLM? And would you share to control AI hallucination from LLM?
So
probably how to control. Sorry, I was trying to complete the second part, but I'll let you go, Martin.
I mean, basically, the control of AI hallucination is mostly coming with let's say, a strict prompt engineering in the back. So instructing the LLM what it is allowed to do and what it's not allowed to do. This is something which we have to do or can do with especially the RAG architecture. Regarding KPIs increase, we could say that, I mean, it's an assistant standing on the side, and whether it was then, let's say, helping at the end to a case or solve a case is very dependent on the situation there. So this is very hard to measure in a qualitative way, or more in a quantitative way, but also if feedbacks coming from the key users themselves, like personally, where they say it's really helpful, then I guess that's something which we can say we did a good job.
Thank you. For the GenAI chatbot, have you seen any impacts on over-reliance on the LLM and skills degradation among experts?
Over-reliance on the LLM, I guess we are not quite there yet, especially because the database somehow is limited to, let's say, our own company database. So, and regarding skill degradation among experts, yes, that's quite a big topic within our project, and also when we are, let's say, onboarding more technicians or experts to the tool. And therefore, we are very clear. The expert or the human expert remains still in control and still has to verify what kind of, let's say, information the tool has found or retrieved. And it's me personally, I'm thinking it's really about how you, as a designer or as let's say from a UI or UX perspective, present those information to the user. So to make it still, let's say, or not, let's still make it force the user to think also about what it's presented or what has been generated there.
Thank you, Martin. Next question was from Romaric. Which metrics did you use or invent to measure the performance and trust on your RAG? Did you rely on trace eval, LLM metrics from RAGAS, or deep eval or homemade?
Yeah, we were looking within the master thesis. We are looking in various, let's say, eval or evaluation metrics. Especially, we looked into RAGAS as well, and more of them. The more, let's say, usage we have on the system, the more also we can then evaluate later on and apply those metrics. And that's, since we are kind of in the beginning, we do not have, let's say, that much of data to, let's say, have reliable or, let's say, interesting insights there. But for sure, we are preparing metrics since the beginning in order to also then going into a direction where we can provide confidence levels to the user when an answer is generated. At this point, we also can mention that we continue our collaboration with academia there as well. So especially on the evaluation metrics, how can they be applied? How are they, let's say, how they make sense? And overall, we are monitoring the entire behavior of the chatbots on a regular basis.
Thank you. So another question, very interesting, from Vincent. How far would you say that the design of verification agent requires strong aviation experience and skills? Would it be possible to design without your experience?
Yeah, it would be not possible to design it without our experience. And that's a very fundamental thing here in developing such a chatbot, because you have to a lot explain not only to the developer how we work and how our domain is functioning. Let's say, the knowledge, all the business understanding needs to be baked in such systems, which is let's say the most important part and work in this project.
Thank you. Another one, probably a bit more technical, on maintenance, as I see standards popping up. So do you think that the use of simplified technical English from ST 100, for example, in maintenance documentation is an added value to the process of AI gathering data?
Absolutely. Yeah. I mean, especially in Europe or in, let's say, the German-speaking or Italian-speaking or part of Europe, English is not our mother tongue, and we clearly use simplified technical English and have that also a lot in our, in the say, maintenance data. And the challenge here is as well for an LLM to understand this kind of language or the specific language of the maintenance personnel. And any, let's say, kind of standard or glossaries or own, let's say, technical vocabularies is helpful to or is actually needed for an LLM to know in order to understand the real content of the data it is using.
Thank you, Martin. So let's maybe take another one from the Slido, and then I will turn to the audience if you have burning questions to interact also in live here. So let's take first the next one. I see it was popping up for a while. It's on, again, from Vincent. You said it is in place. Does it mean people use it in real daily live operations at MCC2?
No, not, I mean, on the side. So how we designed, let's say, also from a ConOps perspective and the operational domain, which is very important to set those boundaries, is that we use real examples, of course, but we always ensure that the main, let's say, our work is still based on the traditional tools they use. And especially if the tools is not working or something like that, then the experts are still able or must be able to conventionally look in their tools, which is always available to them on the side.
Thank you. Yeah, so turning to the audience, I don't know if someone wants to raise a live question, either not accessing the Slido or for whichever reason. Sometimes it's better like this.
Did this IPC help the EASA to build an opinion on reusing general trained models? Because that would take away a big burden on the industry in several use cases, as we remember from Wiki.
Yes, so I take the question, and thank you, Stefan. Yeah, definitely, yes, that's the intent. So we engaged, as was just presented by the team on Lufthansa Group side, we engaged into investigating the possibility of using them. So definitely, we are also using this project as an anticipation for what guidance it would require, how to treat large COTS models, and so on. So this is really feeding the overall effort. Now, of course, it's one use case. We need to see more for sure to get to something a bit more widely usable or a bit more generalized. So it's a start, but it's also, and you will see the connection to the first panel of discussion this afternoon. It's also for us a bit of a testing the water on where we see this boundary of qualification, as I was showing the case 2 on the first day in my presentation, testing the water on where we see this qualification level, what are the criteria to determine if there is a need for AI trustworthiness on such a tool or in a more general way on other tools that Lufthansa Group is anticipating. So it's it will ease, but if you have other use cases, for sure we are really happy to take them on board to test also a bit wider the generalization of what we are dealing with. Last element, but it was really well explained by the team and by Martin. This is an ongoing effort, so definitely we will have many more elements to provide at the next stage. But it was really important for us to show this is going on, and it's a very different nature of IPC than what we were engaging on in the past. So IPC, Innovation Partnership Contract, I think everyone knows now, but we use so many acronyms. Yeah, thanks for the question, Stefan. Yeah, Tiziri, and then I will turn to you, Stefan.
Yes, thank you. Thank you, Lufthansa, for the answer regarding the classification of your tool as for the generative AI assistant, which is 1B. It is so clear. So based on this, I have a question for you, maybe Guillaume, because in fact, when it comes to the AI trustworthiness assessment process for 1A and 1B classical machine learning, lots of the requirements can be verified with metrics. We can have some verifications between brackets, sometimes guarantees. It is feasible. But when it comes to generative AI, there is a lot of uncertainties about even the hallucination, or just it is not feasible because it is a very large model. But also sometimes there is some unpredictable behaviors and skills of the AI when it is trained on a lot. We cannot assess completely what this kind of AI can do and when they could fail, in fact. And this is maybe a research question to deep dive for generative AI before thinking about maybe the certification or even the qualification officially of this kind of models.
Yes, thank you, Thierry. It's a great question. So starting answering, and I think I can turn to you, Martin, to complement if you wish. The first element when we engaged together, of course, was looking at what LLM brings as additional challenge. And can we at all think with, let's say, the concept paper guidance we have to even try to qualify a LLM? And clearly the answer is no. So it's a very different nature of models. François talked about it with a couple of slides yesterday, but globally we consider them now as, let's call them large codes. So they would not fit the current guidance W shape, forget about it. They would not fit classical codes guidance as we know it in system development, software development. So we need to think a bit beyond let's say the boundaries that we have in current guidance. What does it mean? Again, more to come. I will not have the answer today, but definitely all the problematic you mentioned are taken on board by the Lufthansa Group team. That's where I saw clearly on the slides from Martin and Marcel the notion of first a verification of the source. Then you have also the agentic logic of a verification agent. And surely we are very interested in seeing how far we can go even in the logic of criticality thinking in terms of large codes. What exactly should we put in a concept paper or next version? Martin, I don't know if you want to complement.
Yeah. Especially, I mean, with the LLMs as a black box, we do not know how they are trained, with which data they are trained, how the weights are baked into, and also how the architecture are of those very large language models. And then, of course, we have, let's say, built the framework in a way that it is modular and flexible, so that we can also benchmark other LLMs to see. And the question here is also also from a research perspective, whether we should go into using completely open LLMs in order to understand that better. That would be an area of interest also with our next, let's say, a collaboration with potentially with the ETH. And as of now, we are more, let's say, focused on the output. Focus on the output. It's generated, kind of assessing the generated answer as if we would, let's say, test a human. Yeah.
And maybe to add up on the last part of your question, Thierry, yes, research will be needed. There is no doubt on that. We don't claim. I mean, this is where you see a bit the difference of the tools. An innovation partnership contract can start something, can also show a path for a given applicant. Why not? But definitely after we raise all the problematic like we had in the MLIP project where you were participating for machine learning application purpose, let's say, related to the W, we had to investigate very carefully specific objectives that were challenging. I guess we will exactly land on the same path, proposing some methods, some directions, and then definitely research takes the ball and brings this much farther, and that's extremely dynamic and very important. Research and innovation, it's really both. And maybe the last element is I was also mentioning, and that's a discussion we have internally at EASA, the way to take, let's say, service experience into consideration. And that could be another case because You heard it's already running, but it's not deployed in a way that it's the final operational tool, yet it's running. So you can gather, and you gather every day, feedback from your experts and your maintenance staff to see how they use it, where are the hooks, etc. And I think that's something you can talk about if you wish. You have a huge feedback, a number of metrics, and etc. in the background. We can see how much can be leveraged from that for a certain type of operation. That's another thing to think, provided, of course, we need to qualify it. That's the question for this afternoon. Thank you. Stefan, yes, you wanted to raise a question.
So I was wondering why this needs to be qualified, because I mean, it's an interesting project, and I think it does give us some ways of looking at using an LM. But from a safety perspective, I don't think there should be a safety impact here other than maybe human factors, because at the end of the day, in maintenance operations is you still will have to look at whether the dispatch computer says go or no go or go if. So that means if someone followed the tool and it hallucinated and said, oh, you just have to, oh no, tighten a screw here and everything's good, and you missed out some procedures. If the right system wasn't fixed, it'll flag up. We also have ICA, and I certainly hope we're not suggesting that we stop following the ICA provided by the manufacturers, instead just let us get driven by an AI. So I think the only worry then would be the human factors. If someone stops reading the actual instruction, just says, oh, I got a summary from my tool, and therefore I'll just follow the summarized one, which might skip some of the steps otherwise. So I don't know if that is also something that we've been using to tune, is how do we actually do these safety assessments and really try to say what is a safety impact and where do we cover it? Because I personally would say this is something that should be possible to use operationally without any approvals. With maybe the maximum bit is how do we have that human factors aspect, is how do we stop people then start using that instead of the actual manuals?
Martin, if you want to.
Yeah, as part of our safety culture in Lufthansa Group, we perform basically on any introduction or any, let's say, issues or items an operational risk evaluation, which Marcel has presented. And we also did that for that project too, and couple of times, so not only once, more than once, and to identify those risks. And I fully agree, it's really about, let's say, the human factor aspects, that the human is not just taking those answers for granted. And there are, let's say, clear boundaries or clear procedures in place. The people or the trained staff, the licensed staff are trained, let's say, very intensively on that. You know that probably as well enough to always, let's say, rely on approved data. And also here, when I'm looking at those questions, we do not say that such, let's say, generated AI response is then, let's say, usable one by one, copy paste and make it a maintenance instruction. That's not clearly not our goal, because that would be, let's say, too extensive. So the real, let's say, approved data is always to be considered and reviewed. So, and what we more try to do is, let's say, finger pointing into those, let's say, procedures which are available, or giving background information on a certain technical case which is available and can be found better with this technology.
Yes, and again, it's not, there is no claim that this needs absolutely to be qualified or certified, but not, again, not anticipating too much on this afternoon's panel of discussion. The keyword is ConOps. It's in which concept of operation this tool will be used. The same tool could be totally fine with no qualification, exactly all what you just described, or used in a way that actually you rely upon the output. You really want this to be correct, and then you have to lean to something. Let's call it trustworthiness of AI.
So from yesterday, we learned the learned model, AI model, is preferred for deployment. But in this case, will you consider to apply like a learning on the fly by leveraging the human domain expert to correct the errors from your AI model, and particularly those hallucinations? because it's hard for you to correct any ground truth data. By leveraging on-the-fly learning from the domain expert may help you improve your model performance. What's your thoughts around that?
Yeah, I mean, an automatic, I think you mean an automatic process based on the feedbacks the human provided to in order to improve the system or the retrieval itself.
Yes, because when the user are using it, they may help you correct the errors.
Yeah. Currently, since because we are at the early stage of exploring this technology and have to gather first experience with it, the feedbacks are mainly manually processed, like from the project team themselves, to better understand what the user needs and how we can improve then the system itself. I mean, you can imagine then in 2 years when we gain more confidence and experience that it can improve itself in a way of understanding the user better. But that's something which it's not today or right tomorrow. So,
Susan has a question. Yeah.
Yeah. Do you do any accuracy testing of this before you plan to deploy it fully? Or yes?
Yeah.
How do you? What kind of accuracy are you getting?
I mean, from the RAG system, we have implemented some metrics in order to measure the retrieval accuracy. How much, let's say, the relevant content is matching the queries, and how much content is there. So, for example, when I go now a little bit deep into the technology where you have kind of a vector space, you do kind of cosine similarity search. So everything which is really related to a case, and yeah, to make that experience also with the data, with especially in our domain, is very interesting and challenging too.
So, are you human checking that accuracy? Having like one of your experienced guys check that?
Yes.
And what kind of accuracy percentage are you getting? Can you say or no? I understand if you can't.
Currently, we cannot say that. Yeah.
Okay.
No.
Thank you.
Thank you very much. So we have just a few minutes to go. So let's take 1 or 2 more questions from the Slido and then close the session. Because some were very popular. So let's go for Romarik's next question. How do you deal with the fast evolving LLM lifecycle and ensuring non-regression?
Yeah, we started with the 3.5 of ChatGPT model, and that was not at all, let's say, sufficient. And with the evaluation or the evolving of those, let's say, LLMs, meanwhile, we experienced that we even get better understanding and better results. How to deal with that? For sure, there will be coming new models, even open source model available, smaller models available, and we are looking into that. And the focus is then really on the output. So if the output is degrading, then we have to surely think about which model we use then.
And one of the last ones we can take. So can you describe observed situation where the answers were generated using knowledge in the LLM rather than in the provided documents, leading to hallucinations? A specific case, I don't know if you encountered some of those.
Of course, we try to tweak the system in a way that it could hallucinate or, let's say, invent some question answers which are basically really not true. But so far, I haven't observed such a situation, and which makes me personally confident that it only generates, let's say, content based on what it has been provided to.
Thank you. I would say one last one. How do you prevent or detect AI lock-in in a scenario where engineers stop exercising foundational skills or lose them due to over-reliance on RAG systems? That's probably a bit early to say, but I don't know if you have thoughts about that.
Yeah, I mean, that's one of the key risks we identified, which is addresses de-skilling. And of course, we highly respect the expertise of our staff. And it's, as I said before, it's also about how, because we involve the experts very, very much since the beginning in the development of such a tool, and to gain their experience, and also involve them in giving them the opportunity to shape also such a tool, because at the end it's them who are using it. And like if they are not involved in such a process, and then they will not use it at the end, then all the effort makes then no sense. So designing a tool based really from a UI or UX perspective, that they also are challenged, that they are also are tasked to verify or even still, of course, use then the actual procedure, or look into the actual procedure into the original document. I don't believe makes them lazy or over reliance on those systems.
Thank you very much, Martin, and everyone, Ursula and Marcel, for the presentation. Thanks to the audience and online for all the nice questions, and heading over to you, Janet. Thank you. So let me come to the floor to introduce the panel that we've set up for this topic. I think it's a topic that was introduced over the past 2 days or 1.5 days, where we discussed tool at some point. You've seen also in a presentation I was doing on the first morning that we see different cases. What I said also at that time is there is still a bit of a scope discussion related to the rulemaking activities on this specific topic. That's why we wanted to go and take the chance of a panel of discussion to start, I would say, engaging on the topic, to also see what's going on, what comes to our way related to these tools. We see kind of a wave coming. Now, does it mean the wave is too high? We don't know at this stage. We cannot quantify. But is the wave non-surfable? That's exactly what we want to find out. And of course, in the background, and that was my message on the first day, we always are very careful on when to pull guidance and when to say that guidance would apply. In particular, here in the case would be AI trustworthiness guidance that you've seen they briefed in the day yesterday. So with that said, I will welcome first Tiziri Belkacem from Airbus Protect here to the floor. So Tiziri is a distinguished AI leader in digital consulting at Airbus Protect, specialized in the application of artificial intelligence within safety, cybersecurity, and sustainability domains. Your journey began with a PhD in computer science, where your research into deep learning and natural language processing laid the groundwork for your future contributions. And you then honed your skills as a research and development engineer, leading innovative projects that bridged the gap between academic, research, and industrial applications. So you're driven by passion, I can testify on that. And you joined Airbus Protect in 2022, where you've been instrumental in tackling complex challenges in, again, the scope of safety, cybersecurity, and sustainability as a data scientist. And you led successfully activities in the MLEAP project, this machine learning application approval project that was conducted under the scope of Horizon Europe with under the leadership also of EASA, and that served as a key research project for the EASA AI roadmap. Since 2024, you're the leader of the AI activities in digital consulting at Airbus Protect, and you have spearheaded the development of robust AI and machine learning solutions designed to meet the stringent demands of the aviation industry, ensuring that every AI system is not only innovative, but fundamentally safe, secure, and sustainable. Tiziri, thank you. The floor is yours.
Yeah, now it's active. Hi, everyone. Thank you again for this great introduction. Just a few words. Airbus Protect is a subsidiary of Airbus Group, specialized on cybersecurity, safety, and sustainability, with across the BUs, digital services, and artificial intelligence that came as today here. So, when we talk about AI-based systems and safety on the same topic, these two topics bring to the floor, in fact, a lot of differences between the development of AI-based systems and the classical systems, that I mean non-AI-based systems. So on this slide, I try to summarize, in fact, the key challenges that would justify the selection of the tools and the verification of some means of compliance in a measurable and a quantitative, qualitative way. Regarding the development and the validation for the classical, for example, systems, we always deal with deterministic systems and behaviors that are completely handled with a top-down processes. We have the requirements well defined. Whereas for the AI-based systems, we come with an iterative and evidence-based systems where there is a high dependency with data that defines the quality and the performance of the AI brick. And regarding the risks and the failures, these are the words usually used on safety domain, and typically for the safety assessments, we talk about failure modes, the identification of the different failure modes that are very traceable and predictable. There is such a deterministic behavior and the risk assessment is well defined. Whereas when we talk about the AI, there is such an emergent non-deterministic behavior, some errors gap, and then we do not talk about failure as a system, as a physical component, but about some lack of performance or maybe some non-monitored errors, the uncertainties, and depending on the AI that is used, you can enlarge this list of issues that comes with AI in general. And finally, regarding the comparison of the regulatory frameworks, when it comes to the classical software and hardware systems compared to the AI, there is more advanced things on the classical systems that exist since too many years ago compared to the AI that is being integrated a bit slowly than the classical systems. Based on this key comparison, we can identify these, let's say, 4 key challenges, where the first one deals with the incompleteness of some requirements list or maybe non-completely applicable from classical systems to AI-based systems. There is several questions that need some answers today. There is the problem of some AI that are black box behavior based, the data dependency that is the key for the performance of AI, and some verification of the performances. How we can deal with all of that. So, on the previous AMLIP project, as introduced by Guillaume, we have developed a use case agnostic approach that deals with several steps, several challenges regarding the complete development of AI-based systems. And we have made a comparison on the different key steps of AI-based systems development with several tools, starting from the ODD coverage with the key principles of completeness and representativeness, and then the requirements of the AI itself, where we rely completely on some key requirements that comes from the system level, and then list of open source tools have been used. And finally, even for the verification of the performances with respect to the generalization and robustness, also relied on a list of key open source tools that have been used and where you can get access to complete toolings still on the public report. It's so nice. Yeah, it's so nice, as the project, as the weather. And then coming to the W-shaped learning process, here I will enlarge a little bit the scope than the AMLIP project. Here, what you see on the screen is 100% of open source tools providers and libraries, such as the different DIL libraries that are under development and optimization within the group of activities with Romaric Rodin on Anity in Toulouse. But not only, there is a lot of open source tools that are under development, and some of them can be based on AI core. And this AI core is the key discussion, is the key element of our discussion today. Going from the different steps, we have some tools that are great to use to help us, all us as the AI developers, to optimize, to shape the AI itself, to verify the learning, verify the performances, and then go to the next steps for the certification. But the key question is, sorry, I went too fast. I think we have skipped one slide, but I can continue without that slide. It's okay. So the key list of questions is that how we can ensure that these tools are qualified and we can trust them 100% when it comes to the ODD verification, for example. We can rely on a list of accessible tools. It is good. It is open source. So we can put our hands on the toolings and perform some customization. But when it is non-customizable, in fact, 100%, we cannot verify something inside of it. If the tool is including some black box function that we cannot verify, we can choose to trust this tool, but sometimes when there will be some non-deterministic or some errors on the AI model, we will raise two main questions. Does this error related to the lack of performance of our model, or the tools that we have used during this whole process to verify the quality of the AI or the quality of the model, to say that no, there is something missing on the data and it is not about a lack of performance. And this is very dependent, in fact, on the models that we will be using. And when we select them in order to verify the means of compliance for level 1 AI, level 2, or even in the future for level 3 AI, we should be careful about the quality of the tools, because it is not only about the data, not only about the model, but also about the tools that we will be using. And thank you so much. We will discuss later.
Thank you. Now, thanks, Tiziri, for drawing this first connection actually to tools that are known today as development and verification tools, but some can be AI-based, so we have to look into this. And I confirm that our collaboration was less rainy than that, clearly, in the past years with Emily. No, great stuff. So now I will welcome someone you know, again, Martin Rickling from Lufthansa Group. So you were presenting before, Martin, but I will introduce your bio. You're currently Senior Manager of Digitalization and Application Strategy for the Technical Fleet Management at Lufthansa Group in Europe since January 2023. In this capacity, you oversee the digital transformation initiatives across the group airlines, focusing on the integration of cutting-edge technologies such as drone inspection of aircraft and mixed reality applications in maintenance. You're actively exploring the potential of generative AI, as we could see earlier on, to revolutionize technical operations within the aviation industry. And prior to this role, you were serving as a continuing airworthiness engineer for avionics at Swiss International Airlines, Switzerland's largest airline and a member of the Lufthansa Group. So thanks for taking the challenge of speaking again, knowing that we saw the solution you were working on, but probably putting it in the big picture of what Lufthansa Group anticipates in terms of even ramping up in terms of automation. That would be extremely fruitful, I would say, to get this input for the panel discussion. Thanks, Martin. The floor is yours.
So thank you, Guillaume, for this introduction. And as I was speaking before, we were giving you a glimpse into, let's say, our application or Gen AI use cases at TechOps. I would like to give you an impression also on what this could lead to, or what we see in the future of such applications in approved organizations. And therefore, we have this kind of approach of step-by-step approach following the AI level definition from EASA, where we clearly are at the moment in this kind of level 1, or already kind of going to the direction of level 2, human AI teaming, where we have the first use case, or cognitive human assistant, as explained before, is about really access to the knowledge. The human is verifying the data, and the tool is used as an assistant. After we then, let's say, explore a further scope when we go into the direction of human AI teaming, level 2 towards level 2, where Gen AI, for example, is supporting in the decision making, then the entire, let's say, scope and also the entire considerations regarding safety is then looked at very, very differently. So AI acts as an agent, which then suggests already kind of suggestions or even provide some templates for the user. So then the human is in control and then can initiate next steps. So clearly our position there is going through all those stages is very valuable and important in order to gain that experience, in order to know how those tools, operational tools, affect our operations and also affects the regulatory environment which we are in it. You can see here now the next step towards then level 3, which we also discussed this morning intensively as well, or touched. It is then advanced automation, or even then autonomous AI, where at the end then a human has the role of an oversight function, monitoring the AI, or if it is then going full into the direction of autonomy, where basically you have AI integrated in your operational tools, where you not even recognize where AI is really baked in. The human is then more acting as an auditor of those AI-based systems. And this clearly is very important then to define the ConOps and the domain where you're in. And there are applications or operational tools which do not necessarily need to be qualified or approved as such, very simple ones, but there also can be applications or use cases which might have a safety impact based on the risk assessment the applicant is doing. And here clearly to say is then we have existing regulations and boundaries in place, especially in Europe with the EU AI Act, and referring to that when aviation is, let's say, classified as high risk per se, then this leads a lot of, let's say, uncertainties, and uncertainty is certainly something which we within the industry cannot work with when there is no clear boundaries, especially within our controlled environment. So looking ahead, how do we ensure safety and compliance in a chain of AI-driven actions in the various domains and fields we have here, as an example, in the TechOps field, within engineering, within TechOps, within line maintenance, but also other domains for an AOC or an operating airline.
Thank you, Martin. Thank you very much. And with that, I will welcome our third panelist for this panel of discussion. So, Erwan Prudhomme, you studied statistics at a French university. After graduating in 1997, you began your career with the Canadian government, and then started your entrepreneurial journey in 2005 with a clear ambition to build useful, reliable, and secure decision support solutions using data science and AI. In 2019, you founded Sifwasset with one client, the French civil aviation OSAC. Sifwasset develops advanced analytical models to calculate risks in critical environments, particularly in the aeronautics sector. Your solution, the Semaphore Risk Monitoring, is designed to support a risk-based oversight approach. It's been used by the French authorities since 2019 to optimize and secure oversight across the entire civil aviation ecosystem. So here also it's interesting to turn towards authorities using AI-based systems to get also the lessons learned and all what you can tell us about this journey. Thank you, Erwan. The floor is yours.
Thank you, Guillaume. I have 5 minutes, or perhaps 7, but I'll to tell you how we built a RBO program using data science and AI. C4SAT is a small company. We are 20 between Paris and the rainy coast in Brittany. Only data scientists, and we only do data science, whatever the industry. So, for example, of course, civil aviation, but also nuclear industry. So the first main issue was to build a RBO program, but why do we need, especially in France and for OSAC, do we need to build a RBO program? It's because, first of all, we have constrained resources, not that much inspector, and the idea was not to hire a lot of inspector and more aircraft and the ecosystem of the civil aviation to inspect. So the idea was to calculate a risk per aircraft for each aircraft in France in a daily basis calculation, and then to pick up each year for the 350 plus aircraft to be inspected, to pick up the riskiest, but also to ensure that this sample is representative of the fleet. So the main idea was there, and so we developed an aircraft scoring. But the aircraft scoring take a lot of KPI, of course, but also one which was the scoring of the organization around the aircraft. So CHEMO, Part 1, 4, 5, etc., etc. And the idea also for this RBO program, applied to the organization, but also to be able to extend or restrict the inspection time, but also the depth of the inspection for each domain that is inspected by the authority. So again, the idea is to calculate for each organization risk. But how? It's a basic AI data science project. So first of all, you define the risk. What do you want to measure? And then you have a lot of, you have to bring experts together with the data scientist to identify all the KPI you need. And then you have to ask where are the data, if it's good quality, and to bring them all together and ingest all the data. This is the only part where sometimes we have some AI with NLP. Why? Because the idea was to avoid at the maximum using AI for those kind of project. But in general, as a data scientist or statistical, in an old-fashioned way of saying things. So as a data scientist, we use AI only if we need it. So it is a project, we have to calculate a risk. We can use it almost without AI, except for few things like turning comments into pure data. Then we normalize the information and calculate probability and severity and then a risk. This was possible because of one thing is that we use a core team, data scientist and business expert. And in all our project, we have to use those two sides of the same coin. So here is one screenshot of the RBO tool, which is interesting. One of the questions is how does it contribute to improve safety by design, but only by giving a score? Because when you show this to the organization and say, you see there is one red dot, but this is one of the organization, and you can then deep dive into all the scores that lead to this specific measure. So, of course, they want to be better than the other one. To be honest, the first tool we designed, it was red up to green, and the French civil aviation said, no, you cannot be, you cannot say that some are red. So it's from blue to green, but the idea is the same. This is the first part. The second part is that by design, you improve the quality during the time because everybody wants to be better than the other. And last but not least, we stretch also the dots, of course, and the data distribution, because otherwise it's a lot of dots altogether. And this is how we can focus also, how we improve safety by design, because also the inspector can focus on the critical area always, because for each domain of an organization, we have a different score, and then we can focus during an inspection the effort on one specific part. I think I've said almost everything. This is the feedback of OSAC, so the French Civil Aviation, regarding airworthiness. Perhaps a last word. If there is any issue on an aircraft now in France, the first thing OSACs do is to look at if the aircraft is on the list, and then they can justify either if they have been inspected it during the year or not. Thanks a lot.
Thank you. Thank you, Erwan. And to complete the round of presentations to introduce the topic, I will call my colleague Maxime Albertini, who joined EASA in 2022 through the Junior Qualification Program after gaining experience in DOA management and small aircraft certification. You're now airworthiness expert focusing on rulemaking activities for aircraft continuing airworthiness management and maintenance. Your current work includes diversified projects such as introducing digital personnel licenses and developing AI trustworthiness for approved organizations. In October 2021, you graduated from the Specialized Master ASAA, which is Certification in Airworthiness for Aeronautics, taught jointly by the ENAC and the EASA Super-Aero in Toulouse, France. And before that, in September 2020, you graduated from a master's degree in aeronautical maintenance engineering at the University of Bordeaux, with several professional experiences in the aeronautical maintenance sector. So Maxime, glad to have you in the AI program team with your experience and expertise. Thank you. The floor is yours.
Thank you, Guillaume. Good afternoon, everyone. So I would like to start by giving you a short perspective on those operational AI-based tools we've been mentioning since yesterday. And we've seen a lot of initiatives coming in, and we can say that they're going to be very diverse, touching upon many domains of aviation. And the first thing I'd like to do is give you a very short definition, although we already touched on this, about those tools, which would be that they are those which allow the organization to perform the activities for which they were approved by their competent authority. So those activities which are regulated by EU aviation regulations. I would like to give you some examples so that you can grasp a bit the extent of those tools. Starting with production, for instance, you could have a tool which would do an interpretation of non-destructive testing results on a newly produced part, and then tell you if you need to either scrap it, rework it, or it would be fit for installation on aircraft. On the side of design, you could have auto-coding tools as well, for the purpose of software development and harnessing the usefulness of LLMs at some point. For continuing airworthiness, we also had initiatives regarding aircraft digital twins, which basically would allow you to reflect the status in real time of an aircraft based on maintenance documentation or also manufacturer documentation at all times. And that would allow you to trigger actions as necessary, including maintenance. We also have troubleshooting assistance, as we have seen with the IPC from Lufthansa earlier today. On the side of our operations, we may have or anticipate tools doing an assessment of the landing severity on some occurrences that will be based on operational data, and that would allow also to trigger some actions like maintenance again. An example on air traffic management, where you could have training tools doing simulation, training simulation for students, and also explaining the training syllabus and the content of the course for air traffic controllers. And that's very transverse. It would not apply only for air traffic controllers, but also other disciplines like aircraft maintenance engineers, for instance. When we come to authorities, because they are also in the scope of those operational AI-based tools in our view, you could have occurrence management, for instance. So if you have occurrences happening, let's say on a localized area geographically, you could map this and understand the cause of those occurrences. An example is GNSS spoofing with the current times, where you could, as an authority, really map those occurrences and understand which area you should avoid. Or risk-based oversight, just as presented by C4SET in their presentation. Just a sneak peek on what we've been trying to do at EASA as well, and that is trying to harness a bit the usefulness of LLMs for our own purposes, internal purposes. We have several projects going on, and one of them is an LLM-based query assistant. So we receive every year a lot of queries from the industry, authorities, and also private individuals regarding the interpretation of the European regulations. So we have experts answering those queries with tailored replies because they often are regarding, let's say, very niche cases or corner cases. And that means basically a lot of time spent on answering those queries. The idea here is to use instead a large language model, which would be trained with a specific set of training material, including our regulations, any guidelines, standards, or FAQ we have issued in the past, and user instructions, as well as the whole data set of queries we have been replying for in the last more than 15 years, actually. So that's almost 10,000 of them. This generative AI model will draft a reply, which would be reviewed in turn by an expert, and would allow for time efficiency and also to search in the history of replies. We're doing that first because it helps us in a way, but also because it helps us also understanding the challenges which come with LLM, notably the accuracy of outputs and the interest of having strong data governance, especially in our AI training material, as I just mentioned. Now I'm coming to the, let's say, main slide, which was the topic touched upon by Guillaume several times and all the participants during these last 2 days, which is our prefigured risk assessment concept for those operational AI-based tools. So the idea here is to, as an organization, assess whether you need or not to qualify an operational tool. And for that, you will need to go through 3 main gateways or questions you need to ask yourself as an organization in order to understand whether the tool shall be qualified or not. The first of them would be to understand if this AI system or tool is reducing, automating, or eliminating a process which is inherent to your approved organization scope. So if you are using this tool to perform your organization activities as approved by the authority, then the answer would be yes, and you would move on. But if not, we would consider that there's no need to qualify this tool. If I can give you an example, imagine a tool used for human resources management purposes, which are not related with, of course, approved activities like training of staff and similar issues, then you would not need to qualify the tool. When we come to the second question, it is to know if all the AI-based system outputs are being independently verified, and if you are capable, of course, to detect and mitigate any potential error. If that is the case, so you monitor every output, and you know that you can detect the errors that the tool can give you, so the staff is trained and is capable to do it. If yes, then again, no need to qualify that tool specifically. To give an example again, we may think of assistants for which you would review the outputs. We basically at the scale of level 1 AI in that case. So not to say that all level 1 AIs would not need, AI tools would not need qualification. That remains to be precise, but that's basically the major direction we're taking with these questions and the potential answer. But if you don't verify every output, then you move on to the next question and the next step of actions to take. The first thing is to characterize the AI application, as explained by my colleagues, with the concept of operations, and to classify the AI. And then ask yourself the question and do an assessment if there's any operational safety risk linked to the use of this tool. And also, what hazard does it contribute to? And we may think of the hazards which were also already identified through the safety management system of the organization in some cases, for instance. If you consider that there's no risk, no safety risk, and this has been thoroughly assessed and justified, then again, no need to qualify that tool, certainly. If there is a risk, and then based on the operational assessment that you have done, the idea is to identify the safety and performance objectives that you need to fulfill and assign the proper tool qualification level, or TQL. And the goal here is to have a TQL which is proportionate to the risk. So we want to ensure proportionality in the requirements that you will have to comply with for qualifying the tool. Now, of course, with tools, as well as for product certification, we would like to benefit from the framework designed for AI trustworthiness. So that means AI assurance, human AI teaming, and ethics for AI as well. So we still need to clarify the scope for those tools with the European Commission. This is work ongoing to determine how we can handle those tools. But basically, we think that safety-related tools and solutions used by organizations would greatly benefit from the AI trustworthiness framework, that we have been discussing yesterday, mainly. And a final word on oversight for those tools and approval. Here, because we are at organization level, it could be that the main thing would be basically process oversight, a process developed by the organization to explain how they follow the, let's say, the sequence of events I just described in the previous slide. And the authority would do an oversight of this process, mainly, to ensure that the process is correct and is thoroughly followed. And they would verify that maybe with sampling for some tools, some sampling, some cases, but it would not be to verify and qualify each and every tool from the authority. It would be following a process as it's done already for many other organization activities. So that's it from my side. Thank you.
Thank you, Maxime. So yeah, maybe before even going to the Slido, you have it. You have the QR code again here. So thanks again to all 4 panelists for really digging into some aspects of the topic. I guess your questions will raise other aspects, and that's really welcome. Maybe before going there, let's raise 1 or 2 questions from the top and hearing your thoughts. In particular, what is the new risk we anticipate with this type of tools? And again, we are in operational tools under an approved organization. And how to manage the risk introduced if you see additional elements compared to probably current practices. I don't know if you want to start, Tiziri?
Yeah, so maybe one of the main risks that rise even with the AI-based tools, whatever the kind of AI, it's always related, as I highlighted on my presentation, with the tools that we will need, that we will use, in fact, to qualify the AI systems themselves. So there is a process, there is a list of guidelines for the verification, what we need to verify. It is our SMART objectives, go straight forward. But the tools that we will need, if these tools include even AI, there will be some uncertainties related to these tools. And when we go from one kind of AI to another, today we are not only talking about AI embedded systems, even other operational tools for decision-making assistance, or even other kind of toolings to do other tasks to help the operators. We need to make sure that the AI is still performant, and the different scenarios that can raise on uncertainty behavior that have been identified and analyzed. And the other questions related to the use of generative AI, I think I will let my colleagues give their insights, and then we can continue commenting on this topic.
Thank you, Tiziri. Maybe turning to you, Martin, in terms of generative AI. I think you presented extensively a number of things this morning. I don't know if you see additional considerations related to AI-based trustworthy tools.
Yes, I mean, within the process of ramping up in those AI level applications, I think it's very important to, let's say, reassess the operational domain and the use case on a regular basis, because just having one, let's say, consideration and one, let's say, assessment done, it doesn't mean that you can go forward without, let's say, thinking further then.
Thank you, Martin. I don't know, Erwan, if you have some thoughts about specific risks from your data scientist perspective.
Regarding LLM, it's the main risk is on the usage for us. Is that what do I mean? Is that you can have answers that are really well written and that can, for example, cover 95% of the knowledge that you will have well written as a result of a prompt, but you will need 100% of the knowledge to know if it's good or not. So for me, the main issue, one of the issues, is on the usage of LLM in general, by the way.
Okay. Okay, so it comes down to expertise also and domain expertise, as we were discussing also this morning. And maybe with you also, Erwan, one interesting thing, what considerations are important when deploying these kinds of solutions? I would say LLM or AI in general. We don't have to stick to LLM for everything we say, for being accepted by end users in terms of change management, trust. That's quite an interesting topic.
We only use those kind of tools for humans. So it has to help humans. So you have to bring as soon as possible the users and the key user and the expert the soonest as possible in the project to make the tool, the result, the solution fit perfectly what you need. And it's really important also in terms of UI or UX that it is easy to understand, easy to manipulate. And the key point is to ask the user to be part of the project of building this tool as soon as possible. It is not an IT project. It is not a data scientist project. It's a project for users and for being used.
Very insightful. Thanks, Erwan. Maybe skills are also a topic. I would turn maybe to you, Maxime. What are your anticipations, maybe based on your domain expertise, maintenance in particular? You were mentioning tools used for training, but using tools, does it trigger specific need for new skills? How do you think we can manage that?
Yeah, I think one of the main concerns and topics is the training and the readiness of staff to use those tools, and especially to be aware of the risks that there may be when using those tools, especially in terms of accuracy or outputs that they have to judge as well and be sure that, when it's safety related, are correct and can be reused. And of course, the training should not be like a one-time thing, but should be recurrent, especially since those tools must evolve as well over time. So there are domains where it's something which has not been, it's not fundamentally new, but in ours, in continuing awareness, that's quite new. So the initial part of the training would be also something very important. And clear roles should also be defined, and explainability is also a key thing. So it's a whole set of elements that have to come together, I think, for wide adoption to happen.
Thank you, Maxime. And maybe Martin, somehow follow up on the same question, because you have an experience of deploying an LLM-based type of tool. How did you bring the people to be trained to use it? Is there a real competence gap, or did you see that as a pretty natural deployment?
No, not at all a natural deployment. And I would say within all the members of the project team and all the key users, we all started at zero. And involving them at the very early stage into the development and discussing also the risk from a human perspective is very important. Also to know and understand the end user, how he or she is interacting with operational tools. Also from the persona perspective, I think it's very important to mention that especially, let's say, very highly skilled, highly experienced experts are way more skeptical and towards such tools than younger generations. And in regards to change management, it's then a completely different message and a different, let's say, approach how to address the awareness and how to use then the tool effectively.
Thank you very much. So that was a bit of an appetizer to get to the questions for the Slido. Let me now bring them up to speed here on the screen so that we can turn back to the audience. Yep. So some have come in between. Excellent. So let me read the first one and see who wants to answer it. So on the slide of AI-based tools, pilot training isn't listed. How is it addressed today, and what is the long-term vision for AI in training? I guess the slide was the one that you presented, Maxime. I let you take this one.
Yes, thank you. So, well, the slide wasn't exhaustive, so we didn't list, of course, every possible application. For AI in training, we're already discussing with some different organizations, at least from my side and my domain for continuing awareness. And we're envisioning several uses. So it can be rather to explain the content of courses, for instance, and answering questions of students. It could be simulating situations in which the students would practice for potential upcoming situations in the exercise of their functions in the future. There are many applications coming from the industry that we are taking in and factoring in also the rulemaking to see that we cover every case as we can. So more on that with the development of the rulemaking task, I would say.
Thank you, Maxime. The next one is on the vision for the use of data-driven surrogate models, in addition to high-fidelity physics-based models in a certification by analysis context. I don't know, Tiziri, if you want to give a go at it. It's kind of a development tool perspective.
Yes, I think, in fact, regarding the surrogate models and high-fidelity physics or even other kinds of AI models, this is also a machine learning-based models, whatever the target it is. Same process can be applicable, but the list of requirements and the tools that you will be selecting to verify these requirements should be adapted. So what I put on the W-shaped slide is not exhaustive. You can find a lot of other tools. In my case, I have focused only on completely open source tools that have been developed by professionals, but also the academic consortiums that are providing tools verified on different use cases. But for the selection for these specific use, it is in fact the same case because it deals with certification, it deals with a list of requirements to verify. It's only about the selection of the tools that matches the objective of the requirements. I don't know if I answered the question. If the person is on the here, don't hesitate to interact. Yeah.
Don't hesitate with the follow-up. You can raise your hand if you want to raise an additional one. We'll turn to the audience just after, but don't hesitate to jump on an occasion to follow up. The next one would be, on the approach. What approach is proposed to ensure that the development system is cyber secure, particularly with regard to safety-related function? I would also hand over to you, Tiziri, but if someone else wants to say something, don't hesitate.
So when it comes to the cybersecurity of an AI-based application, on my case, I see it in two ways. So you have the AI core inside a system, inside an application that is deployed somewhere. You can ensure the cybersecurity of this AI-based solution, assuming that the system as a whole is cyber secured. In fact, it is encapsulated, it is secured in a good way, but there is always some questions that rises when it comes to some AI deployed that could be more vulnerable for some kind of attacks, for data poisoning, for something like this. So on this case, from my point of view, but it could be only one idea that answers for this question. One of the key methods is to ensure that the AI deployed is highly robust. You can rely on adversarial attacks, for example, and other kind of verifications to ensure that the deployed AI is robust and can recognize poison data and other kind of data that targets the system in a way to provoke some kind of error, and it deals with some cyber attack.
Thank you, Tiziri. Next one is a very interesting one as well. We talk about risk with AI tools. Isn't it about risk of humans using AI tools? Will we observe another distribution of root factors in human errors? So I don't know, Erwan, you were talking a bit about that. So if you want to take this one.
Yeah, for sure. It's easy to understand for the risk of human using AI tools. There is a topic on the internet saying that rabbits can have eggs. So, and it is really well written, and it's from a prompt from ChatGPT. So a student can easily write that rabbits can have eggs. So if we go further and with using those kind of tools in a specific environment like civil aviation or whatever, of course, there will be a risk of human using AI for sure. So, but there is a risk of human using any kind of tools. So yeah, I don't know if we will observe another distribution of root factors in human errors, but yeah, knowledge and expertise will be the key for the next decades, I think.
Yes, based on the skills gap we were discussing before, probably there is something also to say there. I don't know, Martin or Maxime, if you want to complement or take another one to you.
Yes. So we also, I mean, with the hype of generative AI and all these ChatGPT tools newly arised within the last year, we have a lot of, let's say, funny examples. Even with our tool, we experienced funny questions or funny examples too. And I would say it's still at the very early stage of let's say those behavioral of AI, and with every, let's say, observation and with every, let's say, edge case we identify, we can adjust and also better control the LLM in those tools.
Okay, thank you. Maybe it's time to turn to the audience before we get out of time. I don't know if there are some burning questions from the audience. You can raise your hand. Nothing additional. Yes, Fateh here at the front, please. Thank you, Marissa. Thank you.
Regarding the emerging risk or the increased risk, my question is, if we imagine that we have a kind of shared database, for instance, of incident reports or something like that is shared between different, let's say, domains like ATM-INS and airworthiness, etc. If tools like, for instance, tools for training the pilots and the air traffic controllers, etc., are developed using the same database, and if in this database there are some biases due to, I don't know, collection, etc., do you think that we could have an increased risk due to this?
Thanks for the question. I don't know who wants to say a word about that. Tiziri, you, yeah?
So I completely agree, in fact, with you, Fateh. Thank you for this question, because all the data scientists on the scope of aviation community, especially for developing research, open research projects, we really need that kind of resources, that kind of data. But if I'm not mistaken, your question about risk, it doesn't deal with the risk related to the AI development, if I understood well.
Oh, it's more the, I would say, high-level risk from a safety perspective by having, I would say, bad training for the air traffic controller and the bad training for the pilot based on the same biases. Does this increase the aviation risk in general?
Okay. So I could give my point of view, it is about the handling the biases, because there will be always some biases on the data. And AI is an approach that is highly driven by the data quality. And today we can use several open source tools to verify the ODD coverage, the balance on the data, to ensure some quality of the AI that is trained on this data. But absolutely we need a very, let's say, exhaustive, in fact, testing, verification of the quality of the AI before relying on it for training professionals and deploying it for critical use further. In my opinion, it should be very verified. Yeah.
Thank you. Any other burning question from the audience? I don't see a hand raised, so let's take a couple more questions. We have five minutes. Another interesting one, should users learn how AI works or just how it behaves? Pilots don't know sensors, but engine behavior. Are we mixing developers with users? That's a quite interesting one. I don't know who wants to take it. Erwan?
This was the first part, but yes, I think that the more the user will know the big principle of how it works, the better they will use it. You speak about pilots, and of course they know big principle on how a plane fly. So, and it helps in the way they fly it. So it's the same for user with AI. The more you know how it works, the better you will use it, especially on LLM. It's even a key point, perhaps.
Yes, in fact, it makes a good transition when you talk about LLMs. One simple example, I will let my colleagues answer the second part about the pilots and the sensors. But one key examples, all here on this room, you have already used at least one time one generative AI tool, ChatGPT or Gemini or Cordial or something like that. So if I'm not mistaken, if you read, in fact, the instructions that you write on your prompt, you should, in fact, do it in some way to have better results. So this is a kind of awareness how the AI works. And if you are also aware that AI is prone to errors, you will be more vigilant about trusting the results, trusting the behavior. So the answer, yes. The users should understand how it works. We are not asking you to learn all the mathematics behind it, but understand how it works and what are its limitations.
Yes, I mean, fully agree with that as well. In order to raise the acceptance by our users, we aim really to explain them how it works, especially because they are very critic and very knowledgeable about the generated responses they see. And therefore, in order to give them, or that they have a little bit of an understanding why it is answering like this or generating like that or behaves like that, it is important to know how AI works, definitely. But again, also, it's as I said before, it goes into change management and also in regards of the personas or generations thing. Younger generations, they might not need to know or don't want to know how it works because they trust it even more because they get familiar with it since the beginning. So that's then definitely a challenge, whether we imply or we think that the user has to know. Yeah.
Just to complement on this point, and another challenge I think would be how much you can teach someone about AI, because depending on the background of the person and the role in the organization, for instance, not everyone needs to be at the same level of knowledge about the tool. So that's another challenge to take into account. But yeah, all of this lies in the training on how to use it, the risks, and more. So yeah.
Thank you, Maxime. Yeah, I think it's time to wrap up. It's a question from the audience. Yeah, let's take a last one then. Yeah.
Question: how do you apply AI Act if you use some COTS or open source models?
Can take this one. Yeah, Thierry, please.
You mean how to verify that your AI tool is
compliant to AI?
Okay, yes. It is the same thing, absolutely, for the certification. In fact, you have a list of requirements that you will translate into some verifiable features, some verifiable performance of your AI model. And before going into all the system verification, at each stage, you have this. The difference is that for the W-shaped learning assurance, you have this list of requirements well-defined. It's more detailed than on the EU AI Act. When it says that you have to ensure your system is not misogyn, for example, you should translate this into some data feature that says that your training data set must
be balanced. You should ensure that there is not these biases related to gender, for example, because you understand that the feature about this criteria is related to the data you translated, then you verify. And then there is this list, in fact, of scenarios for each feature on the AI Act. You translate it into verifiable requirement of your system in order to verify it experimentally.
And especially like GPT,
okay,
large language models.
For large language model, how to verify that these are AI compliant? Yes. Okay. It's the same complexity, in fact, when you rely on some generative AI that is very huge, that you cannot handle from end to end on its development. You rely on a tool that is not yours. When we use ChatGPT, we are not the owners of the ChatGPT. It's like a black box. So you cannot ensure that it's EU AI Act. We are, in my opinion, we are not the responsibles to ensure that ChatGPT is reliable on the EU AI Act. It is for the provider because it's not your tool that you have developed. I think it's the same principle as for the certification process.
Yes, and I think
could be mistaken.
No, that's absolutely right, and that touches upon another part of the AI Act, which is about general purpose models. Which we will have to live with for sure. This is not part of what we are developing because it's not part of the articles that were brought to us through the Article 108 that we were discussing before. But there is a clarity also to bring. What we anticipate from EASA side is that we will not qualify from an EASA perspective in aviation a general purpose model that will be on the side of the AI Act perfectly, I would say, already framed by certain articles, but more on the use of a general purpose model for aviation. And that's exactly the scope where we see a need. Now, this scope, again, and to wrap up the discussion, because we need to go to the coffee break now for everyone, we really want to approach it with proportionality and care, meaning we don't say at all that everything needs to be qualified just because it's called AI. What is AI matters. How we deal with the different techniques you saw in the past day and a half, that we have to deal with different techniques, and the W shape will not apply to everything and not at all to large language model. So we have to carefully say, what is the qualification we can do, and is the qualification needed? But the clarity, at least we see from a rulemaking perspective, it's not only an anticipation in concept paper issue 3. We will do that for sure. We'll pave the way on what are our concepts, but it's also kind of a rulemaking element from a scope perspective. And why? Because if we can kind of leave this risk assessment outside of the aviation domain, meaning outside of the EASA and aviation basic regulation, we will create uncertainty, in fact, for you as applicants. It's much easier for us to tell you, you don't need to qualify this from an aviation perspective, from an aviation safety perspective, and you can freely go, and that's okay, and you have every, let's say, proof to show that you were not having to go through an AI trustworthiness process. It's different to say, we are not dealing with this, therefore go to the AI Act and all the competent authorities behind, and deal with them the way you want. But after, where is the aviation safety touch in that? And that's exactly why we are saying it matters, but we are very careful on the fact that it's, let's say, a certain journey to go to define the scope, first from the rulemaking perspective, but also from a qualification envelope perspective. And domain specificity should be extremely carefully weighted. Not every domain will have guidance on this, not necessarily, and not every domain will qualify the same type of AI, the same level of AI, etc., in the same way. So that's extremely important. That's one part of our anticipated scope, but just anticipate it for now and more to come also on this topic. Thanks so much to the panelists and to the audience again for the questions, and enjoy the coffee break. Thank you.
All right, good afternoon, everyone. Can you hear? Yeah. And thank you, first of all, for the invitation. Pleasure to be here and to have the opportunity to share the work that we do at CESA about automation and the work on AI, obviously. I will start with a quick introduction of of CESAR. So, because I realize that maybe not everyone knows who we are and what we do. So basically, CESAR stands for Single European Sky ATM Research, right? So we are, in fact, we sit below the Single European Sky policy of the European Commission that defines, in fact, the modernization and harmonization of the ATM across Europe, defines the objectives to reach in terms of capacity increase, in terms of safety improvements, lowering the costs, lowering the footprint. And basically, CESAR is the technological pillar. So we aim to deliver the means, in fact, for reaching these different objectives. So we deliver solutions, very varied, in fact, solutions. Could be remote towers, can be trajectory-based operations, or AI in ATM. So in terms of work, we mainly have 3 tasks, okay? As you can see in the center, CESAR definition, CESAR development, and CESAR deployment. In the definition part, it's more about the strategic aspects. And the main work there is about defining the ATM master plan, so the roadmap to achieve the vision of the CES policy. The second part, so that basically derives into a number of goals and therefore projects that will work on different solutions. These solutions are part of the CESAR development activity. So these solutions are research and development activities to realize this roadmap. The solutions are of 2, well, the activity there is of 2 types. In fact, we have exploratory research, so more innovative ideas, lower maturity, and industrial research, looking at more mature solutions up until deployments. So when these solutions, the CESAR solutions are ready for deployments, we facilitate that deployment. So we work on local deployments and we facilitate the market uptake. We work with standardization and regulation bodies to make sure that they are fully industrialized. So in a nutshell, this is what we do. Now, if we focus on, so if we come back, in fact, on the master plan, if you haven't read it, it's a good way to know about the vision. There is a part, obviously, about automation, and that is where we actually define the automation capabilities that are required, in fact, in the air and on the ground to achieve these objectives, right? And where we determine actually what is the intention in terms of what parts of the operations can be automated, will be automated, in fact, during the different phases of the flights, and also the role of the human, in fact, in that human-machine teaming. So if we look a bit more in detail, again, this document defines the so-called automation levels, right? So you can see 5 different automation levels, 0 to 4. We talk about automation because it doesn't necessarily mean that we have AI embedded into such solutions, but obviously AI will be most likely part of them, especially as you go to the level 4, for instance. The good thing is it is aligned with the EASA AI classification. So at least there we are aligned on the goals. It's just that this actually serves a different purpose because we are looking more at the operational aspects. So EASA, if you like, define the classification more as in the trustworthiness of the solutions and how they can be certified, or the requirements, in fact, to certify them. Whereas we're looking at translating, in fact, those different concepts into operations. So this is guiding, in fact, this is breakdown, if you like, of how the tasks are distributed between the human, the operator, and the machine. Now, if we look now at the timeline, again, an extract from the master plan, you see the vision for the next 20 years. By the way, the master plan is a document that is not fully fixed. I mean, we review it on a regular basis. The previous version was published in 2020, and there was a new one published at the end of 2024. And obviously, we can expect some revisions. Here we expect obviously to see some evolutions on a lower level of automations in the coming years, especially on level 0 and level 2. Some of these evolutions will come through, different actions. CP1, so Common Project 1, is enforced, in fact, by EU regulation. These are solutions available already for quite some time, and that will be forced for deployments across Europe. Things like, airports, collaborative decision-making, for instance, is one of them. And for level 2 and level 1, as you can see, you have what we call SDOs. So they are, that stands for Strategic Deployment Objectives. So these are solutions that were produced by previous phases of CESAR, which have reached the required level of maturity and readiness, in fact, for deployments. And they have been selected as sort of priority for deployment to start building that vision. The part you see at the bottom for level 3 and level 4, obviously these are higher level of automations and typically heavily relying on AI. And those are subjects of IR4 and IR3, which are more innovative research, right? And again, this will trigger some activities, different projects. To give you an example, we have a call actually ongoing. It's going to be closing in a couple of weeks. So it's a bit late now to start building consortium and try to answer. But this is just an extract of what is actually about AI in the current call for tenders. Like I said, 2 different parts, exploratory research and industry research. For the exploratory research, as it was actually mentioned this morning or yesterday, I can remember, we at CESAR are trying to help or collaborate, in fact, with EASA to shape, in fact, the guidelines, right? So you can see here all the topics that are candidates, in fact, for these for proposals. You will recognize a number of topics that have been severally discussed a number of times over the last 2 days. As for industry research, obviously this is building on solutions that are a bit more mature already, and that we want to push forwards towards implementation. And again, it touches all the different aspects of it's not just about ATM per se, let's say, because you can see the future airport platform, for instance. You have ground and airborne systems, and you have cockpits as well covered. And don't worry, I will not go through everything in these bubbles, but this is just to show you the work that we've done so far. In fact, in CESAR, this is not something that we've just started. In fact, the work on AI started already in the previous phase, or 5-6 years ago. The green and red acronyms are actually projects. So the green ones are previous projects are completed already in a previous phase. The red ones are the one ongoing. And as you can see, we have about 30 of them already. So, and each project can deliver multiple solutions. And you can see that we are also touching on very different topics, airports, runway delivery, use space, and also even multimodality is also one of the topics. And that's it for me. I hope I was okay. So, thank you very much. Sorry.
Shall I start? Shall I introduce myself? Okay. Okay. Hello, everybody. I'm Dmitry Kirov from Collins Aerospace. It's a pleasure to join the conference this year, also from the other side of the stage. I'm going to talk about the JARVIS project. Three things I can tell you about JARVIS are the following. So JARVIS is one of the flagship projects in AI in CESAR, along with other projects represented today at this panel. JARVIS stands for Just a Rather Very Intelligent System as an acronym. And the third thing is that we are not the first who developed JARVIS digital assistant, right? We were Tony Stark when the Iron Man was the first, right? So, but good news is that we're first doing that in real life. Okay, so I'll give a project overview, then I'll go over do some spotlight onto some of the digital assistant features we develop and share with you some current validation results and lessons learned. Validations are still ongoing. We are in the third and last year of the project now, but there are some interesting things I'm happy to share today. Of course, I'm going to touch on assurance and certification considerations, which is very relevant, I guess, to this conference and to this audience, and conclude with some takeaways. So how about that? We are 16 great partners here building JARVIS, and we also work together with the EASA research team, which is great. We advance together the AI roadmap, and we inform the next issues of the AI concept paper. So, as I said, we develop AI-based digital assistant. There are three of them: airborne digital assistant, air traffic control digital assistant, and the airport digital assistant. They are for now separate, not connected with each other, but they share the key objective is to increase human performance, to improve situational awareness, and to decrease the workload in complex situations and complex scenarios. And with that, we're taking steps towards higher automation levels, towards concepts such as enhanced ground operations and single pilot operations. So I'll walk through several features. I don't have time to cover everything. So one digital assistant is airborne digital assistant. We have three features there. One is called feature A. It's a deep learning based speech recognition feature. It's an assistant for pilot ATC communication. The feature, so the system transcribes the ATC messages and displays them to the pilot on a dedicated interface. And it also matches the readback of the pilot semantically. So it extracts keywords and matches it against the ATC message to detect possible mismatch and alert the pilot if this is the case. It can also automatically identify if there is a standby frequency request in the message and insert it automatically in the communications processor. And this function brings the feature to level 2A of EASA classification. Feature B is instead related to assessing flight strategy risk. It's based on AI technology, which is not machine learning. It's logic reasoning, so-called the good old-fashioned AI in the AI community, right? It assesses the risk of the current flight strategy with respect to different incoming events, such as failures of aircraft systems, weather events, and suggests mitigations, such as proposes, for example, set of nearest runways or airports to land. And since it's logic reasoning, the operational explainability is relatively easier to do with respect to machine learning-based solutions. Feature C supports the pilot with more predictive arrival and runway prediction. So it predicts the most likely runway which is going to be assigned to the aircraft, which is very useful for complex busy airports such as Frankfurt, for example, or Madrid. It's a machine learning based solution. So some of the current results, we had our first validation exercise at Leonardo in Italy. 7 pilots participated in it. It was done on the flight simulator for regional aircraft. So some takeaways that I wanted to share. So on the performance side, so on the transcribing of ATC messages, we found out they were often not accurate, and the system was also struggling to match the pilot readback to the message because pilots tend to rephrase the message quite a bit, even keeping the main semantics. And so the system was struggling. So there is a room for improvement for us. It's an important finding. Usability, or better say here, usefulness. So in many scenarios, the pilots provided feedback that actually they were in full control of the situation and they knew what to do, and features were providing kind of obvious recommendations, which means that we need to consider more complex scenarios where AI would show its value. Explainability, as many pointed out in this conference, is crucial. I concur with that, and there's a room for improvement here. Interface design is crucial to gain trust and to make the features usable. Everything from fonts, font colors, font sizes, visibility of symbology, and so on. And training material is equally important to be available and detailed. The other assistant is air traffic control digital assistant. I want to talk about 2 features. One is conflict resolution assistant, AI Cora. This feature is based on reinforcement learning technology. So it proposes recommendations for ATC to resolve tactical conflicts. And we're having an ongoing discussion with EASA, as Francois was talking about yesterday, the reinforcement learning aspects and considerations with this feature. Some of the results, we tested 2 solutions. One was without AI, it's like baseline solution based on expert judgment, and the AI-based conflict resolution. And it turned out that also here in like 90% of the situation, ATCO knew perfectly what to do. They must keep perfect situational awareness, and when an assistant provides obvious recommendations, it might be rather distracting than helpful. And which means that in the short term, again, we need to consider that AI features can rather fine-tune complex scenarios, so proposals for complex scenarios, and can also be used post-operation to analyze the ATC actions. But in the long term, it can take more responsibility, but it's the long term because trust, as we think, must be built incrementally. The other feature is Tactical Opportunities Recommender, which proposes DCTs, so direct routes recommendations to ATC, and they can either accept or reject. There are several AI algorithms we use here. One is, again, based on reinforcement learning, and we also have a heuristic algorithm here. Similar takeaway, so many recommendations in validation exercises, the ATC operators found rather marginally improving the situation or obvious, and also the heuristic algorithm, which has benefits on the explainability side, performed really well. And to justify the use of complex AI algorithms, we need to find the scenarios more complex where they can show their value. I'm happy to provide more details, but for the interest of time, I refer you to a great detailed presentation of our Indra colleagues from a Fly AI forum on this feature specifically. The airport digital assistant is the one that focuses on computer vision, object detection algorithms. There are several safety-related features related to detection of foreign object debris, wildlife, and taxiway incursions in the airfield. And it's safety critical because if the system, so the operator keeps monitoring the situation, so it's not full delegation, but what makes it safety critical is the possibility of many false alarms, which can increase the workload, increase the stress, and reduce the overall safety margins in the existing operation. Some current results are maybe more technical here. So the project has its vision-based system perception. It actively used synthetic data to develop the models, and there have been several discussions today, and we'll hear from the Synthair projects about synthetic data as well. So about the difficulty to close the seam to real gap. It might be very difficult to produce physically accurate images. It can be very computationally expensive to do that, and advanced tools are required. Nonetheless, in this project, the synthetic data was used, and it provided some improvement. The vision-based models used are transformer-based. These are very complex neural networks, and they are optimized for accuracy and better generalization, but not for real-time inference, which is the current challenge the team is still facing. I want to switch now to the certification path for AI assistants, which to make them real, to deploy them, we need to certify them, because as you have seen, many of the features I presented are safety critical. And the guidance, as we know, is emerging from global certification authorities, from EASA, from FAA, from the Working Group 114, the standard. And we define a set of, let me call it overarching properties for AI assistant, right, that they must meet, and this is very aligned with the AI trustworthiness building blocks of the EASA roadmap. Assistance must be assured, explainable, collaborative, and ethical, and I just want to cover these steps with you. So as I mentioned, we collaborate with EASA, and overall we think that to build certification path, we must start early, and we must interact with certification authorities to understand together how to make it happen. So let me talk a bit about AI assurance. I'm biased. I'm doing this most of my time, so maybe I'll stay a bit longer here. So I'll split it into the component level and system level assurance challenges. So this project deals with AI technologies which are not yet covered by the concept paper. We expect it to happen in the issue 3, and we contribute with our discussions to identify challenges and considerations for this technology, which is logic reasoning and reinforcement learning specifically. And you can see here some high level, but some challenges we identify for logic reasoning in terms of timing, because these systems are technically speaking, so they solve NP problems, which means that it's not guaranteed when the solution is gonna be found. It can be very short, or it can be very long, and how to mitigate, how to provide a timing guarantee for such systems, it's an open question. Definition of operational design domain, we consider a key step, starting point for many things. Specifically, it's challenging for open context perception systems to define the ODD, such as voice to text. Synthetic data generation seam to real gap is something I already mentioned, so I move on to the system level. We have to understand that AI models, AI components will not be standalone. They will live together in a larger system. They need to be integrated into often existing systems with traditionally developed components, and just measuring the performance and providing guarantees the performance on something like a neural network is not enough to get there. It is also might be challenging, and we face these challenges to assign carefully accurate to the AI level. For example, is it 1B or is it 2A? It depends on the boundary that we consider, a user point of view or system point of view. Specification is, so assurance actually starts at system level. So specification of ConOps, of requirements of AI-enabled system is an open challenge as well, specifically for perception. And finally, safety assessment. So how do we link performance limitations of AI ML components to system level safety requirements? This is something we still have to understand. Human AI team and I just focus on one single point. So we speak a lot here about over-reliance on the technology, but how about under-reliance, for the lack of a better word? So over-reliance is definitely a challenge, but it will come later. under-reliance, so how to gain trust, how to actually let users trust and start using the technology, is a more near-term problem to be solved. And there's also a lower bound for usability of the features. So it has to be useful. Otherwise, as I showed in many takeaways on the features, it works, but it provides marginal improvement or it provides destruction. So this has to be taken into account. Ethics, finally. So we do consider ethics, and we do AI ethics research in the project. We conduct ethics assessment in the project together with EASA. We'll start next month. Maybe I'll just show you, I'll jump over some slides. They will be available offline. So just for the interest of time, we consider, Altai checklist, EASA guidance objectives, and we developed this approach tailored to aviation needs, which considers these different gears of AI ethics. And I specifically want to acknowledge our partner Deep Blue, who is leading this task here. The approach is based on general AI ethics principles, but it's adopted to aviation sector, and it's multidisciplinary, including viewpoints of engineers, safety experts, human factors experts, to measure different ethics aspects for a specific function on some scale. So here's a scale to see if it's makes low impact, high impact, moderate impact. So we made our preliminary analysis on the speech-to-text feature, and this results in, I know the visibility is unfortunately not perfect, but there are different dimensions here related to different ethics gears. And with blue, we measure where we want to get, and with green, we assess where we are right now. So this is our initial analysis that we conduct, and we identified some challenges related to accents, related to data ownership, related to using the data for other purposes, privacy, and so there are multiple factors we already identified, and there are many takeaways, lots of things, but I'm going to takeaways now. So I want to leave you with these messages. Gaining trust in AI assistants is a shorter term problem than over-reliance. We first need to start trusting them, and then we can start over-relying on them. And trust is achieved incrementally. It's difficult to jump directly to level 2B, 3A and start, trusting and using these systems. But on the other hand, features cannot be too simple, otherwise they will not be useful. So the trade-off that we are looking for is to identify these complex scenarios where the even simple features can help. AI assurance starts at system level. There are challenges both in system level and component level. They're both important. Specifically, how to specify AI assistant is an open challenge for us. Ethics can impact different groups of users. It can also impact the safety. Ethics includes various principles, and some of them actually overlap with objectives in the learning assurance part, like technical robustness, for example. And we would like to understand better how to, whether evidence for one can serve as an evidence for the other. And start walking certification path early. That's all I can say. I keep repeating it at every event, and I still think so, as all of us do. So thank you so much. I hope this was useful. Thank you.
Good afternoon all. Just a question. Who has seen the movie Dunkirk? Come on, aviation guys. Did you know that in that movie, and probably in others as well, but in that movie there is an answer for the questions that we have today on our plate here? I'll come back to that in a second. It's amazing because it's old. Yeah, it's an old aircraft. No, so I'm Yuri de Ruiter. I work for company Honeywell. I'm not here alone. Actually, I'm here representing a colleague who has all the credits for the project DARWIN. Project DARWIN is a brother or slash sister, there isn't actually a gender, project to the sector colleague Dimitri, who kind of just gave the presentation on JARVIS. As you can see, we're talking about digital assistants here for reducing workload. So we'll get into that. As I said, I'm not alone here. I have a guardian angel with me. You can't see it. That's typical for guardian angels. But online is available, a colleague of mine, Martin Dostal, who is actually a guru in the area of AI and human factors. So we go through things. So Project DARWIN, for the ones who have been here in 2023, the first AI days from EASA, we're very happy we're now already in the third, may have seen that slide as well, because right at that time we kicked off Project DARWIN and we're wondering, why do we actually talk about AI in the cockpit? I mean, we may be probably a decade or more away from really starting to have it on a certain level in the cockpits. Well, there are, of course, as you may know, and some of the presentations have already given that, already some applications that are nowadays with current cockpits possible to be used in the cockpit, as they are named there. There's also for the next level, when you go towards simplified cockpits, and I'm thinking about, for instance, the urban air mobility, air taxis, innovative air mobility, advanced air mobilities, this bag of, what do you call that, platforms, right? So also there we're looking into, this is actually pretty complex to operate, but can you simplify it and use maybe AI techniques to make it more human to operate? And then further down, of course, can this crew resource, currently we have still 2 in the cockpit, can we then have an extra third in there or 1.5, right? So in terms of the next level, more autonomous cockpits, can AI there be a function as well? So when looking through this, we looked at, there we go, the setup of Project DARWIN. So Project DARWIN kicked off, as we said, at the beginning of the AI days, 2023. We're about to finish it next year. There's quite some things we learned. So if you stay a little bit awake, the end of the slides have lessons learned. There's a good movie in the middle, so they kind of keep it up. But you see, there's a number of technology enablers that we're working on. Particularly the whole pilot state monitoring has been addressed a little bit already today, but that's a very important part, because when you start teaming with someone, you got to kind of have a feel of how that person interacts with you or how you together could form a team. Right? So also when I stand here and look at the audience in front of me, I see people who are very attentive and really listening what's going on. And some said, oh, wait a minute, I've got a much more important email coming in, which is good, but you could see that. So that's kind of talking about, you kind of have an interaction with the audience, with your crew member. But when you play football, you can, even from a side here, there's quite some interaction between the players shouting at each other. So that's the same that needs to happen in the cockpit. In crew resource management, the state monitoring, the task load and in between is a very important part. We're looking also on how this could all be trustworthy, and actually there in the direction of level 2A, how can that teaming take shape? That's what this project will be, are still looking at. I'm here today, of course, with my Honeywell badge, but I'm representing, as you see at the right-hand side, quite a number of very intelligent blokes working on this, including even company Pipistrel, who was so friendly to make some aircraft available and say, you guys, you say you can do it, and let's do it. DLR worked on this project a lot about the load monitoring, which is also not an easy task. If you are together playing football, you can say, all right, this is a guy who is very good at sprinting, so you put him somewhere in the middle and you go. You can't ask him to do another task because it's actually his biggest skill. Yeah, so load monitoring, again, there is something that in crew resource management is an important factor. So our DLR colleagues could have been here as well. But since I'm here representing Honeywell, I go a bit more in detail on that pilot state monitoring and the human AI teaming. What you see on this slide is it being broken down a little bit into the building blocks. You see on the top part, the monitoring part, trying to intercept, so to say, what is the crew, maybe the single pilot, what is his state, pilot state monitoring. Is he loaded, not loaded? We've seen as well from other presentations early in the day, there isn't a linear relation between the two, how stressed you are and how your workload kind of comes together with your performance. that is a very important part in the middle, that together also with the vehicle state monitoring, it's all good and well to kind of keep giving tasks to a pilot, but if when you consider that the engines are actually no longer functioning, and I should have functioning engines, you may think of other solutions, right? So there is that part of monitoring, trying to understand what is the current state and what tools, what capabilities do I have on board, either in a human form or in a more digitized form in order to accomplish the mission. And then you go into the assistant part. As we said, we go in a direction of 2A, then you have to start being of a certain assistant to the crew. And also Dimitri gave some examples on that. What you can see here also is best alternate, cross-checking, pilot state in total. And somebody put a cup of coffee on there. So you could say in terms of being the assistant, you serve the coffee to the pilot in order to wake him up. That's a little joke aside. We didn't do that in the project. But since we're like 5 minutes in, I thought it was good just to. But here's the point as well on ATC communication. That was also in Dimitri's presentation, but I'm not sure if you're aware, ATC communication, why is that there? Is that big of an issue? Well, there was a report by NASA and also Eurocontrol on the communication errors being made in RTC communication. And 2 to 4% of that time, actually, you are between the controller and the pilot, you're correcting misunderstood messages. 2 to 4%. Okay, and then, well, that's 2 to 4% of your airspace capacity that you can't work. Okay, cool. But then from the other communication messages, I'm not sure if you're aware, but 25%, there is just no readback from the pilot. Did he actually understand it? You don't know. There's no readback. There are accidents that happen just because of that. And accidents, you know to what this leads. We want to avoid them. There is 18% of the communication errors that the controller didn't actually capture that the readback of the pilot was erroneous. Okay, probably this ATC communication thing there becomes a bit more important when you have like third member in your crew that can probably better understand what's going on and say, well, wait a minute, guys, I think you're missing something. And avoid an accident. So it looks like a small little bottom element in there, but it can become very important. Now, when we go up to the human-machine teaming, you think, well, wait a minute, that's the same pilot that forgot his readback. Will he then also look at the instructions or the alerts that I'm giving him? You see, so some of the human aspects become very important once you start talking about your digital co-pilot. And that's also here when we looked at the monitoring of it, that's a big deal that we spend time on in that particular project. On how do you go along with that and how does that teaming come along knowing that we're not flawless as human beings. And we did that in steps. You could do in test aircraft a lot of things. But there are the whole thing about the sim to real gap. There are a couple of things that you may need more simulators for. What we did in the test aircraft is what you can do very well. You can put tons of equipment in there. Nobody cares by means of saying, these are test pilots. These guys are well trained to work with tools that are sometimes not functioning by design because that's what they are supposed to do, to simulate something. But then here also we kind of put more sensors in there. You all know that sometimes you miss a call. Is it because you can't hear? For some people that could be the case. It could be because your volume is low. Or it is low considering the circumstances or the environment you're in. So low is, again, there a very relative state. So we tested there all of these alerts and see through phases of flight, through particular situations in a flight, are these alerts actually coming over? Does the pilot see, hear, feel, smell the alert? You can smell some if your co-pilot is getting stressed and you get sweat pit, right? Right. So this is an important part as well. So it's nice to come up with a very academic exercise and say, yep, here's my alerts done. No, you got to really test it out, and we found out there's quite some things that we still need to work on in order to get this along. There's already quite a number of different sounds and beeps and whatever signals in the cockpit, and then what does that mean in addition? Sorry, I pressed the slide too fast. On the normal operations, so okay, get in an aircraft and go and test it. That's what I was just about to show you in the next video. Go and test it out, and then look particularly, can the system detect the pilot state in many different scenarios? The cockpit isn't a very real good thing in there. You could do a lot of things in your simulator where you can start working with, oh, here's a lightning strike. Oh, here are, as you can see there as well, there's turbulence, and yeah, we can't simulate it, or it can happen, but maybe not in your real aircraft. But you could still try and see for whatever you could simulate if you can actually detect the state of the pilot. And that's what we did in that phase. So if I now try and get to, I don't know how that works. Yeah, the video, I'm just trying to get it in.
Let me try this. Oh, it's a private video, it says. My goodness.
Yeah, that should be okay.
So can you sign in?
Well, we'll just skip it then.
No, let's try again. Wow, that was not foreseen. It was not embedded in the presentation.
No, we will do 2 hours. Okay, we'll skip it. We'll skip it.
I will try. Just a triangle, but I'm not sure. Not even sure I remember that thing. No.
Yeah, that's okay. We'll skip it. I think we have more time for Q&A then.
Yeah.
There's still some slides to
just a triangle. No, it's unavailable. I'm sorry, I don't know what's going on. Okay, good.
So we were just testing some interface issues. We're on a research project. But indeed, so what was in the video, and probably will be available afterwards as well, as you can see, it will be posted on YouTube. It's not yet available to all at the moment. Is that we did indeed earlier this year did some nice flights in Italy, and then we used those pipistrel aircraft to really get some good test pilots in there and let them simulate sleep. Try and do that. It's not easy to simulate sleep, but they did their best. So on the impact in a broader context. So one of the things, and so this is already the introduction to the lessons learned. So what are the things you learn from this project? And as I said, we started at the time also the AI Day started, and then the whole roadmap was kind of just about available for a year at that time. And there are many things that are by very brilliant people put into that roadmap, but now we start to kind of put it to the test. In how far are we making the right predictions in that, and how far do we understand the right challenges in there? So there's a lot that we did, and so as well for Project JARVIS and the others from the SINTEF proposal, that through really doing it, you start finding out things that otherwise we didn't think of. It's also, in the terms of standardization, a very good thing to go and work through those standards, so that into the EuroK working group, that you can come up with standards that actually make sense, or that can be applied in a broader scope of things. You go also in this project, we also went beyond what was the guidance scope. That's the fun of it, right? In research project, you can go beyond and I try and find out what do we find there that you may not have yet into the document itself that could potentially lead to answers of the questions we have at hand. I'll quickly go through it as I see time is going on. So some of the reflections and lessons learned. So go back to the human factors element here. It is a disruptive change to CRM. CRM, crew resource management. Every pilot in the commercial environment has been well taught that you're not alone in this world, you're not alone in this cockpit, and then how to kind of get along in every state, or even in stress moments, right? So that's again, here you have an extra partner on board. How do you integrate this all? And how do you mean that, how do you actually make sure that at the end of it, you have a safe execution of your flight from A to B without quarreling on board of the cockpit? There are lots of interactive and dynamic aspects, which is very difficult to simulate. you know that you can come up with scenarios and then you think like, yeah, but wait a minute, today this isn't possible, or this isn't even realistic. And in there you find that the human has a very interesting thing. And I will go back to the Dunkirk movie. Did you see in the last scene that very nice Spitfire landed on the beach? Did anyone spot where actually he was landing? So, and at the beach, you say, right, there's a ton of dry sand where I can land, and I have the part very close to where the water line is. This is harder sand. Somebody of the years, I think about maybe 25 years old, that pilot at that time, would already know from his childhood, when he was playing on the sand, that this is the harder part. In his pilot training, when landing on grass, he found out like, yeah, if I land on grass or if I land on a solid paved tarmac, there is a difference. I have less chances to kind of tip my aircraft over if I land on proper solid surface. So that knowledge from his childhood came into play when he was there. There was no more fuel on board and he had to land on the beach on purpose. And I'm not sure if they were in the movie. He didn't land in the soft part of it. So what's the link with AI? You think, oh, okay, I don't get it. Now, you train AI for the events that you think it needs to be able to handle. And then here as well, it's some of the disruptive elements. And now you can see also the learning there on long and short term. You probably give it 2 years of training, 5 years of training, but probably not 25 years of training. You expose it to all elements that you think you will need in an aircraft for the scenarios you could think of. We as human beings, we've been well outside of the cockpit. And we've learned that that branches of a tree are softer than the what's the other part of the tree? The trunk, right? So if you have to crash land, you better try and head for the top of the aircraft, of the tree, and not the trunk. You know that if you land on the beach, you better go for the harder part than the soft part, because you've seen that in your childhood, that this is the more solid. So you see that the things that we as human beings learn outside of our job, even in our childhood, will one day be instrumental information that you can use to get out of an emergency situation. And that's the part, again, there, where for AI, if we train them well for 25 years, they will do exactly the same job, but probably won't be able to get there for 25 years. So there's a lot you could kind of find out once you start doing it. You find out where there's a lot of dynamics, there's a lot of situations you could think of, but it's not always the same case. You can also see, and I'm looking at the time there, by the way, that the design of the HMI, again, is a very particular thing. Look at your phone, look at the phone of your neighbor. It's probably the same brand, but it looks different. Why is that? Because people like different colors. Maybe they like their brightness a bit more than you want, and other things. So every human has a different interaction, but you have to make sure that your cockpit is designed that many humans can work with it. You also see that there are cultural differences. When you look at a phone of a Chinese person or an American person or a European person, probably you see differences again. If you look how people park their cars, even within Europe, there's a difference between how you park your car in the south or in the north of Europe, right? So there are, again, there in the interaction of the human with the machine, there are very differences that you would like to work with, so that at the end you have a teaming that functions. So that's what you have in there. I'll speed up a bit. The other part is on TRL 4 to 6. What's so important about TRL 4 to 6? What's the difference between the TRLs before? Is that you start coming in the zone where you go and test and validate your models, your design, your prototypes in a representative environment. And there you hit the reality, or close to reality, right? And there's so much you can learn on it. But it's also the zone, particularly for these type of projects, where you will go through lots of frustration, where you go through a lot of domains where you just don't know the answer. And you have to go through it, because you want to get to the solution. And what we learned already so far is that by being able to mature this, you'll get a reward. You get to a solution where you said, wow, if this is working after all the things I've been putting into it, I'm quite sure that somebody else will have a very difficult time getting to the same performance. So maturation is very important, and it's the only way forward, even though there are many unknowns. Another thing we know that in the many unknowns is a theory that you get from survival techniques. In survival techniques, it's well known that if you are there with a group, don't have one person decide what is the next step to do. Make decisions in a team. And so, because you don't know, you're in the middle of the desert, you know, your camel has broken down, and then you're there. Oh, sorry, you had multiple people. So you have a couple of camels, and you have to get through it. But this is not a situation we are every day faced with, right? And so you think of what is the first thing to do. You have an idea, your colleague will have an idea, your best friend who is with you will have an idea, and it may be different. But together, and this is proven scientifically, if you together kind of put it all there, you will come to a much better plan. And that's the other part here as well, is there are many unknowns, and also in the direction of certification. But if we do it all together, and thanks to the AI days again, and I said this to Guillaume and Ines already 3 years ago, is by doing this together, go together through this unknown terrain, we will get there. And I think with this, I'd like to close my presentation.
Can you hear me? So first of all, good afternoon. It's very nice to be here. My name is Massimiliano, and I'm here with Martina, my colleague from Norway, as you can guess from our names. I'm joking, of course, representing the CINTER project, and I'm the coordinator of the CINTER project. And I will not go through this name because this is the last session of the last day, so I will show you a bit about the project during these slides. Yeah, first of all, just few information about the project. As you can understand, this is a project under the framework of CESAR 3, and this is an exploratory research. It means that the TRL is very low. So we are doing very basic research. We are playing with the models, architecture, data, and things like that. And we are trying to understand if those things have an impact in the aviation. We started 2 years ago, actually 2 years ago, because we started the 1st of September of 2023. And we are now in the phase of dissemination and of the dissemination of the results of the project. When I start creating this presentation, I was thinking about last day, last session. So I will try to have something very soft and I will try to give some insight about the results that we're getting. Of course, you can get more technical details in our public deliverables. There will be also a URL of our website where you will see some of our results. Yeah. I think that the most important things to start with, and that was basically the motivation of, first of all, my experience in the last 15 years of working in AI with the industry, but also what is going to happen what has been happening in the last almost 20 years in artificial intelligence and machine learning. This is a very nice graph that you can play with in this fancy website, Our World in Data, that is basically showing to you on a time scale the data points needed to train the most notable AI systems, AI models in the last more than 50 years. As you can see, in the last 15 years, due to some breakthrough in the technology, I don't have time to explain that, there has been something was happening. So basically, we have been moving from models trained with millions of data. Training means learning the model to do something, to react to something, to models, including the GPT-4, the ChatGPT that you're probably currently using, of trillions of data. So, and considering that you are currently, or we are currently interacting every day with systems that have components, AI components like a voice assistant in your iPhone, or maybe Netflix, the recommender system behind Netflix, or many others that you can really not imagine. What makes those systems very powerful is the data. This is a very simplified answer, but it's very powerful. The data is the core of the most important, the things that make powerful those systems. High quality data is the key. So you can see from millions to trillions of data points to train your voice assistant, to train ChatGPT, to train whatever that works well. More data, smarter models, more high quality data, smarter models. But of course, what is the problem? For those that are working in machine learning, the problem is always the same. In the last 15 years, I've been talking with tons of industries. They come to me and say, we would like to do AI, machine learning. We want to do this. Okay, let's sit together. Do you have the data? There are three kinds of questions. Answer. No, I don't have. Okay, what can we do? Second question is that, yes, I started yesterday to collect the data. Third question, yes, but most of my sensors are not working properly. Okay, so this is in many, many, many cases, the situation that we figure out when we want to develop something. And this is the main idea that drives us to the Syntair project. And this is what we observed also in aviation. There is this persistent barriers in developing complex AI systems. And this is due to the data access problem. Many of the stakeholders are reluctant in sharing the data, airport, airlines. And this is due to the fact that there can be data scarcity, so limited access to comprehensive operational data set. Of course, privacy constraint, like in healthcare. Can you share my data? Can I share your data? No, privacy constraint. And also there are, of course, some regulatory barriers that impose some strict compliance requirements limiting the data availability. And in the last years, it happened that to sort of tackle this problem also in other domains, one possible solution that has been tested, it was to use the synthetic data. When I talk about synthetic data, and specifically to the scope of our project, we are talking about data that are generated by AI. That means data that are generated by generative models trained from real data, and those models are able to understand the patterns from the real data. And of course, those synthetic data must be plausible, are plausible and rich. That means that maintains the statistical properties of the original data, of the real data, and also the correlation among the features. And this is very good because synthetic data are accessible to all the practitioners, researchers, and all the stakeholders, and are freely available, and also can be used for train any kind of predictive model or any kind of model that want to perform a machine learning task, anomaly detection, prediction, or whatever you like. That's why we land into this project, given this urgency of having high quality data whenever the data are not available or whenever accessing the data is very hard. So the mission of Syntair is to increase the level of automation of ATM systems by delivering novel generative models able to generate plausible ATM aviation synthetic data. This kind of mission as a sort of side objective, side effect. First of all, can improve the ATM efficiency. Then, of course, it supports the adoption of AI in ATM. The main barriers, data access. And also what we are doing is support innovation. That means that we are delivering also recommendation on how to use those generative models that we are developing, and also how to use the synthetic data, sharing code, models, data set, and things like that. That people, researchers, can use for their research, for their any kind of use. Okay? Of course, again, TRL 0 to TRL 1 means that we are playing a lot with models, architecture. We are using the most advanced and complex state-of-the-art methods, transformer, for those that are ML enthusiasts, flow matching, diffusion models, things like that. We are tweaking those models, and we are working on this stuff. But we want also to see the impact of this stuff, of the synthetic data, of this generative model generating synthetic data on some selected use cases that have some impact in aviation. For this reason, we have been selecting 6 specific use cases: the turnaround time prediction. You can see mostly prediction task, flight delay prediction, passenger flow prediction, the synthetic traffic generator, the flight diversion prediction, and the schedule prediction. It was quite ambitious because 6 use cases in a 2 years time was quite a lot, but we have been getting some results for all of these use cases. Of course, today I don't have the time to give you the details on the results, but I want to come to you with some takeaways from some of the results of some of the use cases. Of course, again, at the end of the presentation, you will have a QR code and URL that you can get in our website, checking around our papers and see what was the result. But I want to give you 3 main takeaways. So for the flight delay prediction, we've been developing some one thing. When I talk about generative models, I'm not talking about ChatGPT or things like that. In our model, we are using the same backbone technologies, transformers, diffusion models, things like that, for generating aviation ATM data that can be tabular data, spatio-temporal data, temporal data, events, and things like that, right? Same backbone, tweaked for this kind of data. So again, flight delay prediction. I don't have to explain you what does it mean that. So some practical prediction of departure and arrival delays using the scheduled flight info. And what we have been doing, basically, we have been training, we have been checking the utility of the synthetic data for this task. What does it mean, the utility? We have seen that the predictive power of synthetic data is almost the same of the predictive power of the real data. Means that if I train a predictive model with the synthetic data, is the same as training with the real data. That means that, okay, our data, our generative model are producing good data for a downstream task. Yes, okay, but those data are really plausible. We've been doing several experiments on that, and among them, we have seen that the synthetic data that our model are generating preserve the same operational drivers as the real data. In some way, there is a sort of good operational impact on what we are showing. First of all, make possible to have a proactive delay mitigation strategies. Second, you can have an optimized crew and resource allocation. And finally, of course, you can have an improved passenger communication and network flow management. Okay, so synthetic data in our experiment works as well as the real data for the prediction of in terms of predictive power. The second message, flight diversion prediction. Flight diversion prediction is a very hard problem. One can discuss about is deterministic, not okay. It's very hard in any case because basically the idea is just to predict a situation in a rare situation of a flight diversion before landing. The problem is that in all the data set that you want to use, or in general, diversion is a rare situation. In the data set in general, you have less than 1% of diversion, but it's highly disruptive. What we have been doing in this case, we haven't substituted the synthetic data with the real data, but our generative model, trained on some kind of data, were able to generate those rare events, making the training set for this predictive task more balanced. Right? In this case, we have been observing that this is called data augmentation, means that you have a training set for training the predictive model, and you augment you add on the top of that also the synthetic data. And we've seen that with augmented data, the predictive power was better. And again, okay, but these data are good or not? We have seen that the generated synthetic data were achieving a very high realism and were hard to distinguish from the real data, demonstrating at the end with this set of initial experiment that there is a value in augmentation with synthetic data in tackling scarcity of data, okay? Finally, in the last case, when you talk about flight schedule, and when you check this kind of data set, you have often a problem of incompleteness. When you check this kind of data, there is a lot of hole. So there is a lot of data column and row missing. Generative model in this case and synthetic data can be used to fulfill this kind of gaps and to impute missing schedule entries in the specific case, preserving operational constraints. Again, perfect. We have been testing this reconstructed data in a spatial density estimation pipeline. And we've seen that in a couple of experiments with some data from US, that we've been a reduction in error of almost 10%. So we are more or less seeing that from different perspectives, synthetic data can add value in case of problem of data access. Again, I remind you to our website and our deliverable to see more details also related to the other use cases. Now I will leave the floor to Martina.
Yes. So I'm glad that most of you are still here, despite this is the last session, despite it stopped to rain. But also I'm glad that our presentation arrives at the end of this 2 full and intense day of discussion, because I'm quite sure now that you fully understood the challenges that we are facing for introducing AI in aviation. And I'm quite sure that also this brief overview on synthetic data can help you in appreciate what we are trying to do to turn these challenges in opportunities. And as we discussed in the past days, there are a lot of issues and challenges that we need to resolve. And from our perspective, we can start to address some of them. In the workshop also yesterday, we discussed about privacy and compliance, and our synthetic approach protects sensitive information by design. We don't rely on real personal or operational records, and this helps in minimize the risk of re-identification. And this make our approach safe for sharing information and ensure collaboration across different stakeholders. Moreover, synthetic data are aligned with the current GDPR rules, and they support privacy by design, and also they are aligned with the EU AI Act that entered into force in 2024, because they help to provide more transparency, safety, and quality foundation that regulators demand. Of course, compliance alone is not enough. As we learned in this past day, we must also ensure trust. And EASA set out a framework for AI safety and oversight. We got also this nice book yesterday, so we will go through it again. And these include explainability, ethics-based assessment, and governance principle for automation in air traffic management. So here synthetic data became a key enabler to allow us to train and test AI system in under realistic but controlled condition. This bridge essentially the gap between principle and regulation, and helping us to shape concrete certification pathways for AI in aviation. So just let me summarize the impact and the value of our approach. First, synthetic data, as Massimiliano said, accelerate AI innovation by reducing dependency on scarce and real-world data sets. Second, they enable safe experimentation for some rare use case, as you have seen, fly diversion, for example, and it helps also to train the pilot, the air traffic controller for this use case that cannot be tested in reality. They reduce the bias. Yesterday also we talked a lot about bias in the real data set, because we can with the help of synthetic data, we can reduce this bias by creating balanced data set. And last but not least, they help to build trust and resilience in AI for aviation, aligned with the EASA trustworthiness framework, and it helps us to foster collaboration by allowing secure data sharing across stakeholders. So just before concluding, I would like to mention that also this QR code give you access to our GitHub page, where we have tried to simplify all the fancy word that Massimiliano use for more generic public. But also if you are AI and ML fan, you will find also some interesting information, technical information for you. And we have also developed a demonstration app that we have a video. If you want to see synthetic data in action, we will be happy if we have some minutes to share it. I have to ask the boss of the session. Or we have Q&A, so... No, the video, we want just to show one or two, yeah, 1 minute, yes. How I can access to the video? Let's see if this works. We are a little...
Should be on the next slide, by the way.
Okay, yes.
As you click space whenever you
want. Just to say, this is related to one of the use cases of the synthetic trajectory generation. Please go ahead, Martina, sorry.
I'm sorry, then let's go back and probably we have to...
Okay, yes. Maybe it's... Yeah, it's working. Great. Yes, this works.
No,
yes, it's working. Yeah. So this is just a real initial version of the app that we have developed, because when I worked with this professor of machine learning, for me it was very hard to understand what they are doing. So on the right side, you can see trajectories that are created from real data. On the left side, you can see the one that we can generate with synthetic data. And also, you can play with this app by clicking on the different features on the left column. But also, if you are not an expert of this kind of tool, you can just input, like you interact with ChatGPT in a natural language, what you would like to see in here, for example, there is a screenshot where you can see for example, text, and this is under development, and we wanted just to provide you with an initial overview of this.
So coming back to the bias in AI, we are developing also something called conditional generation. That means generate trajectory according to some initial parameters, weather or some other parameters. On the left side, in fact, you see that you can play a bit with wind speed or things like that. And if you don't want to play with the left panel, we are also building a sort of large sort of layer so that you can interact in natural language. So you can write, I want generate 100 of trajectories with this characteristic.
Yeah. Okay. If you will be here after the session and you want to see this, we will be happy to share again. Thank you so much.
Thank you. Okay, so checking, but I think no, we don't have Slido questions. I think people are probably tired using an interface, so we will have some from the room directly. So we have less than 10 minutes, but let's take some questions from the room. Yeah, you will get a microphone. It's coming to you, Patrick. Yeah.
This one. So I was just typing the question on Slido. I'll try to be quicker in formulating it. You've shown results, very interesting results from the Sinter project with generated synthetic data that is in relatively low dimensionality. And so this allows you to study, analyze, compare and balance the biases in the distribution, the probabilistic distribution, because this probabilistic distribution is accessible in much higher dimensional spaces. This is not the case any longer, and maybe this is the reason why the guy this morning from Boeing was saying that using synthetic data for images is a nightmare, because you cannot manage the unforeseen objects or the unforeseen effects of objects. Can you elaborate a little bit on what you've been studying in this project about this problem?
Can you hear me? Maybe it's not. Yeah. Now? Yes. Basically, regarding what you're saying regarding the presentation of this morning, we are talking also about two different domains of data. They were talking about images, and probably they were working about the sim to real gap in a reinforcement learning setting problem. We are talking about something different here because probably the technology behind is the same. We are talking about tabular data. We are talking about spatiotemporal data, so different dimensionality. We, of course, with our model projecting to an higher dimensionality that is more readable, interpretable from the machine and also from the person. When it comes to the bias in the data, we have been doing some experiment. I was mentioning a bit before on the conditional generation. That means that in principle, projecting those data into an higher dimensional space, you can also observe where you are missing the diversity in the data. And in principle, sometimes you can also augment the data set, specifying which kind of space you want to augment and reducing the bias in the space. We have been doing some initial experiment on that, and we have seen some interesting results, but unfortunately, we didn't get too much into detail on that. Maybe that's a good idea for our future project. I agree definitely on that. Thanks for the question. And I also appreciate the fact that there are face-to-face questions. I really love that.
Just if possible, I also wanted to compliment. I really like the question, and I concur with it fully. So when we get to high dimensional data for trained perception systems, so things like seam to real gap and the amounts of data, the dimensionality explosion become crucial. So I don't have a solution for you. Though I have idea to give you hope, let's say. There are techniques to, yeah, definitely we cannot maybe ensure that we generate enough volumes of synthetic data to cover the entire high dimensional space, but there are techniques to explore the space and to understand where we need to generate, where we actually need the data and where we don't, to navigate there. There are quite some research work there. Like one example is dimensionality reduction of high dimensional data to see on the clusters. It does not guarantee, but it's one way of doing it. There are some other ways using scenario-based approaches, being able to measure the high dimensional spaces. So this kind of brings hope for doing research in this area to possibly solve this problem.
Thank you. There is another question from the floor, please.
Quick question for Dimitri and/or Yuri. 2 months ago, EASA came out and said that they're going to potentially pause single pilot operation regulatory work. How does that come down to JARVIS and the work that DARWIN is doing? Has that impacted you guys at all, or is it just full steam ahead?
Thank you. Yuri, what do you think? He's not here. He had a meeting. So yeah, I can answer for JARVIS side. So the features we develop in JARVIS are quite minimalist and with respect to single pilot operations. So we say that we take steps towards SPO, but we take very incremental steps to gain trust, as I was saying. So I don't see any immediate impact on JARVIS or its continuation for these features to have this impact for the moment. So for JARVIS side, that's my view.
And I think I'm going to give also the floor to Martin from Honeywell. Martin, would you like to participate, please?
Yeah, good afternoon. Can you hear me?
Yes, loud and clear.
Okay, very good. So from our perspective, we don't see that as a real threat, right? Because the technology that we are working on is potentially applicable both to the CS-23 or CS-25 aircraft, right? Both for the single pilot and the dual crew operations, right? So I think this is more of a business threat. So how you basically orient your product, but technology-wise, we don't see that as a big threat for us because we can address several kinds of operations with the underlying technology that we are working on.
Thank you, Martin.
Maybe, I don't know from the floor, but one question came on Slido for you, Martin, from DARWIN side. Can you provide more elements about tools and methods used in the trustworthy machine reasoning platform? Which methods makes it trustworthy?
Yes, basically, the trustworthy machine reasoning platform is a reusable tool that we are applying across the whole DARWIN, including the human AI teaming component, the digital copilot, and as well as a couple of the assistants. And it's basically a tool that is using propositional logic-based reasoning, which by definition has some properties that are welcome for the transparency and explainability, as could be opposed to, for example, machine learning-based techniques, where you have to deal with some aspects of the technology, which is basically not present with the approach that we are taking. Our approach also is 100% deterministic, and since it's not based on machine learning, there's no possibility to have, for example, hallucinations or other aspects typical for the generative AI. Maybe one more comment on the platform itself. It's heavily performance oriented, so we have demonstrated also the capability to reason about very complex problems. So we are able to make like thousands of intermediate decisions per second. So the tool is, or the platform is highly scalable and is based on the propositional logic reasoning.
Thank you.
Thank you.
Romaric, you had a question or I misunderstood? Okay, thank you. Any other questions or comments? It's now or never. So I think we're fine, right? Thank you very much for the panel. Lovely. And let's go for coffee break, right, Janet?
Okay, so I'm now introducing Guillaume, who's standing next to me, obviously, and will now do the wrap up when he's got to the right moment on the right slide so that you really know that it's him. So, Guillaume, straight over to you to wrap up the event. Yeah.
Thank you. Thank you very much. Maybe for the wrap up, the EASA AI team, if you can come up in front, like we were on day number 1, just to have you also here. I mean, I'm talking on the behalf of the team. Well, while people are coming here, I will do a wrap up, meaning just reflecting on what we've lived for 2 days and 2.5 days, in fact, together. And then I will give the floor to David Solar for performing the conclusions. From my side and perspective, from an AI program management perspective, what I see, it's an enormous, I would say, preparation work from the team. That's why I want them also to be here on the stage. But it's also extremely rewarding. We get to engage with all of you. As we said on the first day, and you had slides to represent the whole community, but we really engage with a wide spectrum of stakeholders. So we had an extreme large participation from international aviation authorities. That's extremely appreciated. We all engage in different activities and roadmaps and initiatives on AI, and it's great to come, reflect, discuss, and find ways for synergies in preparation of what we call all harmonization, meaning next steps, but very important steps so that everyone globally and worldwide are speaking the same language, or at least dealing with the same requirements. We got also, of course, a lot of chatting, meeting, getting to engage with new people. We met, I think I met a lot of new faces. You met people also on all sides and all fronts. That's why we keep also long and large coffee breaks as long as we can, when we don't eat them with Q&A remaining sessions. And the workshop format is, for me, a very important, on the human factors side, I would say it's a very important element we added this year, which we didn't have in the past. We promised it end of last AI days as a takeaway. We need to engage also bidirectionally even more into reflection, not only exchanging, sharing information one way and getting the feedback. So it's quite an important element. We got also feedback on the way to deal with this exercise. I think for next year we'll be even better in length maybe of sessions, and probably for the WebEx participation. I know some people are still awake and online. It's important probably to not create kind of a bridge, so maybe to stop at the end of the day with a workshop and then to debrief more on the morning of the next day. We will find out better ways to do that. From the technical side, definitely that's what triggers our interest on the AI program side. For sure, it was a big information sharing. I think you got a lot of information, and probably too many when we see we are all a bit tired probably today. But it was quite an important, let's say, occasion and opportunity for us to consolidate our views, bring new things. We didn't want really to repeat, but bring new things and bring perspective. So that's really what we wanted to achieve. We have the feeling that's what we could do. And we gathered a lot of feedback through the Q&A, Q&A sessions are as long as we can. We never come to the end of it because the Slido keeps piling up anyway. So all of these questions are stored. We will take them on board of our reflections also for the next steps. From the workshop, we got results, we got directions also on what we need to work on concretely, technically, refining the classification scheme. We got a lot of discussion on 2A versus 2B, and there is a lot to say. We are creating a gap between 2B and 3A, even if some people don't feel like it from certain perspective, but other I would say domains like drones bring us a very clear gap between the two. So that's all things we need to think, reflect, and communicate on. The ethics-based assessment guidance needs, of course, to be pushed forward. We have an excellent, I would say, survey report. From that, we need to see where we go, but pragmatically with this notion of possibly a checklist, but seeing what is behind and beyond the checklist and who takes it. AI assurance, of course, a lot of, I would say, progress, maturity, as you could see. Still a lot of remaining challenges. We know them. François gathered them with the workshop together with Florence. And on the human factors side, evaluation and testing with use cases will be our key, clearly to mature further, clarify also, delineate this classification scheme to the best of the proportionality of the objective. That's the tool, in fact. Criteria for classification are there to proportionate, to bring us also to a better understanding when we talk to each other internationally. The risk management strategy, you see two big challenges, one on the level 3 itself, type of AI, so less human, more AI, more kind of smart, intelligent systems, reasoning element, so technical challenge, but also the risk management challenge is there. And tools, trustworthy AI tools, a lot to do. We just initiated a discussion today, and there is a lot on our plate. One acronym, because you had a lot of them, probably the second most used acronym in the conference beyond AI was IPC, or beyond AI and machine learning, ML, was IPC. You had a lot about innovation partnership contracts, for sure, from the projects concretely going on, and surely also with the reflection from Jean-Marc on how we came there and how this tool came to life. But it's a very important tool. I will not say more because you know everything, but I will just say one thing. Every applicant or industry we are engaging with in IPCs is taking a certain, I would say, level of risk, and so far they all took it to publish actually the report of the IPC. It's not a given, it doesn't have to be, it can be just a partnership between EASA and the applicant to get to some understanding and then take it away. But actually in all IPCs we did for AI, there was a final report. You all benefited from the two Codan report, the formula report, and now you will benefit from the Beacon one, and surely in the future the Lufthansa Group one. And that's exactly where we want to go. That's feeding the community as well, and that's key elements. After to feed not only the community, but as we were saying with one question from Tiziri, the research community also, because there are topics that needs carefully to be deepened. Well, that's what I wanted to see to close my wrap up. I would say safety first, as we know. We see also other dimensions we need to take on board. Trust is the second word, maybe also beyond safety, because we could think it's only about systems and AI assurance. No, there is the human factors case or part. It's not only about human factors from a traditional way, it's also about ethics considerations. How far, again, to be all discussed with the community. So trust and trustworthiness of AI, we didn't create the term, but I think it has a real merit, and you see from the building blocks logic of EASA, we try to give to it a shape. That's a very good also tool for communication and further refinement in the framework of concept papers and throughout the rulemaking effort. So many thanks from my side to all, to the team in particular for all the preparation, but I let all the conclusion words to David Solar. Thank you very much.
Just a last word from me before David comes up. We do a survey after these events, and we're very happy to have your feedback. It enables us to improve and work out what we should be doing better next time. So if you could look for that when it comes in, that would be great. Thank you. And now I'll hand over to David to close. Thank you.
Thank you, Janet. It's always a challenge to close the sessions after 2 days of intense work. And I'm glad to see that most of you stayed up to the end because it was very, very interesting. First of all, I would like to thank the AI team and the AI Days organizers. I mean, it's an amazing job to do so and to make it happen. That's really so. Congratulations to Guillaume, Ines, René, Giovanni, François, Andrew, Maxime, Axel, but also to all the people that made it happen. Also, Janet as Master of Ceremony, but also Manuela, who is in upper floors, Marisa, who's here, Tom, who took non-aviation compatible risks to take pictures, John, and for the communication, and Jasper, but also our colleagues from international cooperation who made some of you able to come to this conference, Rodrigo and David in particular. Obviously, I would like to thank all the presenters, all the people who contributed actively and their associated companies who enabled them to come to present and to share. That's very, very important. I would like to thank the technical team also. And finally, Florian, our executive director, and Maria, who was supporting this event and the AI development within EASA. Of course, I would like to thank you, all of you, for being here today, to make the effort to come, and for the one online to stay online for long days. I would like to thank for your contribution, your active contribution and engagement. Workshops are not easy. You have not been passive. You have been very active. Questions, and that's key to make things, moving forward. And I can say that you made this conference fly, and I would like to thank you for that. I would like that we give a round of applause for the AI team, the organizers, and for all of you. I try to make it short. You are lucky. I'm not planning to retire. At least I don't know, or cannot afford to retire anytime soon. So I will avoid some anecdotes. I will reserve them for a couple of years down the road. And I promise also, I've not used AI techniques to summarize my take of this conference. We have seen that AI technologies, and you are all aware of that, is very promising and dynamic. In my opinion, aviation must leverage all the potential benefits, mitigating the risks in a responsible manner. We have seen specific challenges. You named human interfaces, explainability, ethics. I would like to take a bit another perspective. For me, they are great opportunities. If I take human interfaces, our cockpit interfaces or ATM interfaces are dated, from the 70s, 80s, a bit of the 90s, but you have a lot of legacy into it. And we've seen some issues associated to that. Introducing AI, having a new perspective with the new human factors and interfaces studies that we have benefited from the last 50 years is an opportunity to reshape the future of the cockpits. So let's leverage it. We can really start to some sheet of paper that are fairly blank. Explainability also. What we have been struggling with in the last decade is explaining automation to pilots. And if we are able, using AI, to explain what the system is going to do without having, tons of manuals that they are not reading too much or they are forgetting the day after, that's also a very big step forward that we could make into the safety. So here also, it's an opportunity of transforming a challenge into an opportunity. Ethics also is an opportunity because it helps us to rethink about how we design the systems, how we interface, what is at stake, what the people perception could be, and why they trust or not a system. So that's really also here something that we could leverage much better than looking only at the challenges or technical challenges behind. AI Act is a foundation that has been published by the Commission. And it was the starting point of our journey a bit, and we participated to that with the key objectives I would like to remind is support safety, obviously, support innovation also, protect citizen, and I would like to, a fourth one is to enable sustainability. Sustainability not because AI is very energy consumer, but also optimizing trajectories, optimizing waste in aviation, optimizing maintenance, all the stuff where we can gain is going to have an impact. We have thousands of aircraft flying. Each time we are gaining 1 or 2% or 3%, it's a huge gain at the end of the game, and that's where we can decarbonize step by step, little by little, sector by sector. And that's going to be key because with the amount of data that we are handling today, it's not possible for a human being, and it's also something we need to take into account. I would like also to remind something, certification. Some people are looking at that as, big words and very challenging. Certification, the basic of it is common sense. And going back to common sense, that's also something I would like that we emphasize. And sometimes we are locked in our technicalities, locked into our deep, I am in my working stuff, and we do not take the step back. And actually, it's pretty much going to be my job in the AI team. I'm the newbies on the block, so I will probably ask naive questions, but challenging and asking why a lot. And asking why, we are doing things is always something we should do and self-reflect upon. And certification is only, why questions, almost. I would like also to emphasize something which was striking to me. It's that AI is relevant for all aviation ecosystem. Each domain of aviations, which used to be and still today is a bit separated. We are speaking about maintenance on one side, we are speaking about aerops on the other side, we are speaking about aircraft design on another side. And actually, if I take a simple example that we've seen, two examples that we've seen today where we can leverage and enhance what we can do, we've seen some aviation, also image processing on the runway, and two types of them, on board and on the ground. And guess what? If we made it compatible to have the onboard and on the ground talking to each other on time, we may not be needing this bloody ADS-B that is anyway very limited. And probably we all know that the ADS-B is at the edge of its capabilities. So we have to make that as an entire ecosystem stuff and not only it's my own backyard. Thinking about compatibility of data, compatibility of how I do my data processing so that, the guy on the ground may also be able to use it or may feed me with what I could need in terms of also enhancing the overall ecosystem. And that's really maximizing the benefit across the board. Don't think in silos anymore. And we are going toward more operation-centric certifications. And it's blending the end-to-end, from design, productions, operations, ATM, maintenance, maximizing the effect. We can also think about recycling. If using AI that this material that you have sourced somewhere has some specific characteristics, if you blend with some others, and I've seen some companies already recycling carbon, using AI technology to make it, to ensure the consistency of the recycling material properties. That's simple, but if we are not leveraging that, we are going to miss the point. I would like to also emphasize that it means that it's via dialogue among each of us, and something that we really have proven very useful during these 2 days, and also that a high-level framework like the AI Act, but to more specific to aviation, like the RMT.0742 could be an enabler of this, enhancing the ecosystem, making sure that all of us are speaking the same language and try to match what we are. Now, we need to keep it simple, pragmatic, proportionate. We cannot ask the same for highly safety critical to non-safety critical at all, or to a CS 25 aircraft with a general aviation. That's also a point where I want to link the whole work that has been done. Thanks to IPC, we have progressed a lot. We have learned all together. It's a common journey. We are learning all along the side. And you've seen the outcome is fairly promising and it's very good. Now we need to learn more, obviously. And beyond having other IPCs, we need to probably start real operations. When I say start real operations, we've seen that data is key. And guess what? The best data is the one you are collecting into operations. That's a fact of life. We all seen, you know, as a design, aircraft design, customers that are using their assets in a way that nobody thought about. And I can speak about it when I was designing aircraft. Guys doing some, you know, Mach 1 crossover that they were not supposed to do. But, you know, going beyond the boundaries even of the operational envelope. And for that, we probably need to be able to start developing this tool for some part of aviation where there is limited risks, or where the risk is already higher than in the very commercial top-up aviation. I'm coming from the GA world and rotorcraft, at least from my recent past. Before I was more large, but it's a perfect ecosystem to test. We have a very critical kind of operation in some instances, very less mature organizations to handle them, less training associated to that. And guess what? They are not two pilots, but one pilot. And I can tell you, when you are a single pilot IFR and you start to have an engine failure and it's dark outside, you better have, you know, maybe some hint about what are my trajectory, where I could optimize, something that is pre-processing already, avoiding the tunnel effect that they are all ending up into. And we can learn a lot out of it. We can really learn a lot. And enabling collecting data. By the way, in this arena, we have developed net safety benefit concept, which also is translated into the AI, the RMT, to make sure that we know we can enable this system without having the certification lock-in that we could fall into. And we could have a fast iteration to improve. Collecting data, retraining the system, re-putting the system into operations, that's going to be key. We could have, you know, limited operation, limited ODDs, limited scope, with restrictions, not under any condition, whatever, but still move forward with real stuff. Where it's also going to add some positive effect is that it could get people used to it. And if we start, you know, from the scratch, here is the AI, it's going to be doing plenty of stuff that you may not understand. And they will see also some of the limitations. Somebody was telling, yes, if it's not doing the performance, it's not good. The pilot will probably get it out. But, you know, we could show also people that it's not perfect and it will never be a perfect system. So there are limitations associated to that, and pilot needs also to get you to and to train them to challenge sometimes the outcome of what the system could do. And it will help us understanding the other challenges, because the devils are in the details into that. I've seen that with the Boeing case, you know, the clouds, and you must experiment that, okay, the shadow of the cloud is probably an impact, or the grass is too green and it's messing up my system. So, and last, I want to say, and Guillaume addressed it, that it is a sharing. The more we share together of the pitfall we could fall in, the better as a community we are. And I would like to thank the companies that really agree to share their outcome of IPCs. It's very important for everybody to get up to speed and to not do the same pitfall, and that moving all together forward. That's how aviation has been built on that, on sharing of experience, and that's where we ended up with these excellent safety records. And for that, we need also a global dialogue, not only European, but much wider. I think, we may have some, I won't say divergence, but, ethics, is it part of aviation stuff or not? At the end of the day, it's common sense. So whether it is in aviation, but we are all addressing that together, and we extract, but we agree on the technical aspects, that's going to be key. And that will be a big part of the job. I think we will have to engage and reconcile further. I would like to then invite you for the next steps of the journey, and which will be the publication of the NPA as a milestone. We will review the comments associated. Don't hesitate to comment, say if it's too cumbersome, too complicated, whatsoever. We will take the time. We will take the time to review all of them and make sure we are nailing the NPA to the point. Now, it's a first step. So, you know, it's touching the water because then we will have much wider audience at the working group. It will be also leveraging the concept paper issue 3 that will come later on, addressing the higher levels, but also new type of AIs potentially that are techniques that are going. And last but not least, if you have, you know, innovation or AI type of applications you want to share, either bilaterally or a much wider approach, don't hesitate. IPC is a tool. We can engage also in parallel and have some engagement. Thanks a lot. Thanks again for the team. It has been a fantastic 2 days. I've learned a lot. I hope you've learned also a lot. And I give you, you know, meeting in next year, probably same period, not same time, I don't know, but at least same location, probably, yes. Thank you very much.